participated in this challenge. So you can see the public entries. We have like 110 for these public entries. And for the participating teams, we have like 277. Okay, so finally, I want to thank all the organizers from Shanghai Lab, Tsinghua, and Motional, and also our sponsors, our partners, and all the very amazing participants. So let's welcome our first speaker, maybe. So our first speaker is Deva from CMU. So Deva is a professor in the Robotics Institute at Carnegie Mellon University and the director of the CMU Argo AI Center for Autonomous Vehicle Research. So his research interests span computer vision and machine learning with a focus on visual recognition. So Deva's talk title is Multimodal Perception of the 4D World for Autonomous Navigation, Flexible Maps, Fusion, and Forecasting. So let's welcome Deva.
So now I'm going to share my screen. Hopefully folks can see my screen. Okay. You're sharing? I don't think it's awesome. Okay. So now I'll go over here. Okay. Thank you for the setting up this workshop and giving us all a chance to talk about stuff. I'm sorry for the mouthful of a title, but what I really wanted to do was talk about. We were fortunate to get the review gods smiled upon us. So we have a bunch of papers from our lab in the space of perception and autonomy for self-driving vehicles. So my goal in the 30 minutes was to really just give an advertisement for a bunch of posters and talks. And hopefully, if you guys are interested, you can go off and dig more into detail. Okay. So roughly the three kinds of topics that I'll talk about is, I won't really talk about end-to-end end-to-end autonomy. But instead, I'll spend the first, let's say, 10 minutes talking about building world models, in particular 4D world models, something that we've been kind of pursuing for a while. And one piece of work that we're pretty excited about is trying to build a 4D world model at scale. So Haitham will present this, or we'll give a poster on this on Wednesday afternoon. And essentially, what this is, it's a NERF of Pittsburgh, built from, I think, the largest available sort of data set. I'm sorry, this is not available, this is private, but it's essentially built from a self-driving data set of millions of frames collected over a year spanning thousands of videos. And importantly, the things you wrestle with here are we want to reconstruct the rigid environment, which is essentially a map. You want to also have to deal with the movers in the scene. And I'll try to show you essentially some efforts of trying to build neural models that can synthesize how not just the static world looks, but how it moves. And I think one of the secret sauces that we've been pushing on to try to do this sort of dynamic 4D world reconstruction is, I'm assuming everyone in here has kind of seen NERF-like models before, but the thing we've really been emphasizing is trying to not just reconstruct image pixels in terms of RGB reconstruction error, but really trying to understand motion. So you could imagine, given a whole bunch of these logs collected at scale, you extract pixel intensities, which is straightforward. You also extract motion vectors of how pixels move over time. And then we also throw into a mix self-supervised features. So I've heard the term used before when you have losses that suggest you want to learn 3D representations, or in our case, 4D representations that then project to the image pixels, we call that a photometric loss. When that projects to motion vectors, we call that a geometric loss. And when that projects to self-supervised features, other folks have suggested calling that a feature metric loss. So you can put this all into a big mix try to learn a model that takes as input not just spatial position, but time. And in this case, we also had to deal with timestamps over different resolutions. One of the tricky parts here is that sometimes clearly a part of the world is very static. We want to lean into that. There's other parts of the world that are very dynamic, people walking down the street. And there's also parts of the world that are what I call transient, like parked cars. And when you're trying to learn 3D or 4D models at the scale, you have to tease apart all these three. So we can look into sort of detailed models for how to do that. And then finally, one of the tricks for really learning at this scale was kind of revisiting old techniques from graphics. So this is from Thomas Funkhauser's thesis in 1990, where this was, pre-heavy duty GPU days. Folks also built walkthroughable renderings at scale for large scale buildings. And one of the crucial tricks of making that work was really employing visibility reasoning. And it turns out you can apply these same kinds of techniques of partitioning the world into cells and seeing what data is visible from what cell as a way of constructing data parallelism. So you can end up essentially building little NeRF models for different parts of the world, and you can allocate the pixels and rays that are useful for training that NeRF model for a particular neighborhood. So I think it's kind of fun to revisit some of these old graphics techniques for learning models for efficient rendering at scale, and I think they can be useful for doing things with this kind of urban scale NeRF 4D modeling. And another thing that I think is kind of fun, and maybe if you come from the self-driving world, this is obvious, but I think if you come from the NeRF sort of view synthesis world, this might not be, because usually view synthesis is thought of as a technique for creating pretty pictures. In the self-driving world, actually, there's a very important use case for this called resimulation, which is you collect original data, which is shown in the top. Unfortunately, this is a re-rendering, not the original pixels. But what's incredibly useful if you want to really build a kind of 4D simulator is being able to say, well, what would the world have looked like if I had moved differently, if I had moved over to the left lane, if I had slowed down? And essentially, this is a view synthesis problem. So I think this is a beautiful, use case for NeRF models, except that, of course, the crucial thing here is the world is dynamic. If it was just a static thing, it's not so interesting to model because we want to sort of understand how to move in this dynamic world. So you can do things like, simulate what it would look like if I'd moved to the left. You can even do what I think is neat is not just extrinsic view synthesis, but intrinsic view synthesis. So you can imagine that I have the same location of a camera, but I swap out my sensors, a near field fisheye lens for a normal lens. And all of this kind of just falls out of the NeRF framework, which I think is a pretty kind of effective way of looking at this kind of data. And I think one of the things that to me is super attractive about really embracing this 4D view is that now, if you could really build 4D models that understand 3D structure and also how that 3D structure changes over time, you should be able to use those models to forecast, to predict how the world will unfold in the future. So essentially forecasting 4D models. And I think this is, I think, very evocative of things that we certainly see in language, of trying to build models that predict the next word given previous words. And I think there's a very compelling argument to be made of you could try to predict the next 3D point cloud given the previous set of 3D point clouds. And I think one of the sneaky wins in trying to phrase it in this way is for language, a very practical aspect that facilitates large-scale learning is that words are so compressed, and you can actually store an enormous data set of text, trillions of examples, in a somewhat feasible way, which is still very difficult to do for images. But I think point clouds live somewhere in the middle. I think we can learn at scale with point clouds. So something we've been looking at is trying to build these 4D models, but learning them at scale exclusively on point cloud data. So you can imagine a very simple way of doing this is if you follow this view of like next word prediction, in this case, it'd be next LiDAR frame prediction. Given the previous set of T LiDAR frames, learn a network that predicts the next T set of LiDAR frames. And you can compare that to the ground truth because that's what you observe, and you backprop this loss. But here's a case where just doing the naive kind of machine learning solution, I think there's a place to put envision smarts into this. And that is so much of what we see here, the change in what we see is not due to the dynamics of the 4D world. It's due to the changes of the sensor. And this is kind of obvious when you think about it. You can imagine having a rigid world where nothing is changing. The only thing that's changing is the viewpoint of the sensor. But if you look at the sensor readings, the 3D points that you get out, they will appear to change. But very clearly, the world is not changing. It can be static. And this is kind of obvious when you think about this. Well, it's because the world is rigid, and what these points, they don't represent actual physical things on the corner of surfaces that you track. They just represent intersections of rays from a sensor with the 3D geometry. So in some sense, we really want to tease apart the modeling of the world versus the modeling of the data. And a very simple way of doing that is we nerfify this. So we replace this feed-forward model with something that, instead of predicting points, it actually predicts occupancy, 4D occupancy. And you can represent this with an implicit nerf or some explicit voxel triplane representation. But given this, we can now render it from future positions that we know in the data. And now we can compare this rendered model to the actual future sensor data that we see and use this as a loss. And now what's cool is the model internally will learn this, this representation of the 4D world as it evolves. And when you do this, it ends up being considerably more accurate than previous approaches, because previous approaches tend to directly model the sensor data, versus what we're doing is actually, I think, modeling the world underneath. And one of the fun aspects of this is, because we're modeling the world underneath, we can re-render it from different sensor intrinsics. So you can re-render it from a 32 beam LiDAR or a 64 beam LiDAR. And there's a statement here I'd like to evoke. I remember meeting Judea Pearl at a PI talk on a grant, and he made this statement that always stuck with me. He said, "We should be modeling the world, not the data." And I think from his perspective, he was really pushing causality as a first-class citizen. But here's an example of the world is really 4D. It's not points. The sensors are points. So if you make a commitment to modeling the world, you get all of this, I guess, sort of kind of generality, I think. Okay. Buying my time here. And in the space of 4D modeling, something else we've become very interested in is really trying to model 4D scenes. So we have a slew of work that really focuses on much more dynamic scenes, not in the outdoor setting, but I want to highlight it here because there's a bunch of folks in the lab who have been pushing toward a very large scale code release, which is out this week. And I want to just advertise it for folks that might want to use this. And I'll show some examples on using it on outdoor scenes. But essentially, this idea of trying to model dynamic scenes, we've quite a bit of work on, and Genshen can tell you more about it in his poster on Thursday morning. But one of the sort of take-home messages here is that applying the same kinds of technique that I talked about for modeling the 4D Pittsburgh world, if you do it in a scene of a video collected from an indoor setting, you can still very tailored views, but we actually build 4D reconstructions of the world. And if we can, we should be able to, in this case, we end up using depth sensors as well. So with a lot of sensor rigs and self-driving, we have LiDAR data as well. And if you have that, I'm just going to sort of show off some results of, you can get reconstructions of the world, of the dynamic objects. And now, because we're reconstructing dynamic objects, we can re-render it from arbitrary viewpoints, including virtual viewpoints on the dynamic object. So we'll show a re-rendering of a cat moving around from the cat's point of view, and also from a little camera that's following the cat right behind. So these are the kinds of things you can do if you have a 4D world. This one's kind of nice. This is what the world looks like from the cat's perspective. And some more fun examples. Okay. And so we're essentially preparing a code release for what we call like 4D world modeling using NeRFs. And it should be out this week. So the students have put a lot of effort into making this sort of a user-friendly code base and examples of both indoor and outdoor scenes that are importantly dynamic. So that's the sort of point of emphasis here. Okay. All right, so that was really, let's say, the bulk of the talk on sort of 4D multimodal understanding. I want to keep an eye on the time here. I think I have 10 more minutes. Just want to see here, 10:30, 10:35. Okay. All right, so for efficient perception, so I'll just sort of throw this off as another a kind of natural extension. A lot of these techniques that I talked about for building these kinds of 4D models are pretty compute intensive, because essentially it's solving this it's trying to address vision with this analysis by synthesis view of differentially optimizing an interpretation of the world to match what you see. So this is relatively expensive. It takes hours to do. And so these kinds of models learned from here won't work in an embodied robotic setting, because we have to respond in milliseconds before we get the next sensor frame. And so we were wrestling with this predicament that we can do this very expensive, like 4D graphic style optimization to try to understand how the world is moving around. But at the end of the day, for robotic applications, we really want fast feed-forward models. So how do we reconcile the two? This is kind of a trivial observation, but one is we just distill a feed-forward model from this huge collections of offline models that were trained expensively on large collections of video repositories. So essentially, we've had lots of discussion on, or I assume we will have more discussions on sort of foundation models and what they could mean and implications for self-driving. My own personal view, I think what's kind of needed is something like a 4D foundational model, where this is one of the lessons I took away from my time in sort of the self-driving world, that historically I sort of tended to focus a lot more on recognition problems, but once you're in that space, it becomes really clear that the high order bit is understanding what is in front of you, what's the empty space, and how that's moving and changing, as opposed to labeling things. So I think building this 4D understanding, it seems like we have tools that can do this with a very expensive approach that involves differential optimization. But essentially, we can still do this at scale on sort of, let's say, internet scale video footage, and then try to learn models from there that can be distilled into very fast, efficient feed-forward architectures. We have an example of this that Jeff will talk about on Tuesday afternoon. Okay, I'll skip this in the interest of time. If everyone wants to hear about sort of efficiency and saliency, something that I've always been intrigued at is if you really want to make things fast, one of the first things everyone does in a robotic setup is you take all your sensor readings and you throw them away. You start subsampling frames, you start subsampling pixels. It always breaks my heart because you spend all this time creating this very elaborate sensor rig and you throw away a decent chunk of it because it's too expensive to compute on. But humans don't do this. Humans saccade and foveate. So we have a paper that sort of gives an example of trying to do this kind of trick that's GPU friendly that Chitesh will talk about Tuesday afternoon. Okay. And it turns out by doing these kind of sort of attentional reasoning, you can do much better on finding small objects, which I think is going to be important for at-speed navigation. So, for example, autonomous trucks. Okay. And so now in the last few minutes, I want to throw out just a few, kind of get a discussion going on multimodal foundation models and what they might mean for self-driving. And I want to motivate that by this problem of open world perception. So one of the things that I found curious, I've been interested for a long time, is kind of long-tailed recognition. And what you find is if you look at a lot of these sort of perception data sets for self-driving, they'll annotate a huge number of objects that are relevant, strollers and people and kids. But what happens is during evaluation, they ignore a whole bunch of the rare ones because there's not enough of them. At some level, this has to be the wrong way of framing the problem. So if you take a state-of-the-art object detector, apologies, Philip, are you here? If you take a state-of-the-art object detector, then actually try to train this on these rare classes, you kind of get shockingly abysmal performance. So this to me is almost clickbaity. So you try to train a stroller detector, you try to train a child detector, and it gets less than 1% performance AP compared to these common classes. And it turns out if you do a bunch of fixes, you can improve this by a significant amount to 20 or 30, but that's still well short of what you would like to have. And I argue what we've done in the self-driving world is that we sort of have a semantic blind spot. We focus so much on cars. And in fact, a huge number of papers and work in the space of 3D detection focus exclusively on single objects. And so we kind of forget that there's all these other objects out there. And in some sense, this seems clearly that it feels like this is the wrong way of framing the problem. We can't just ignore children because they don't happen to appear a lot in our self-driving data sets. And I think one possible solution here is really bringing to bear massive pre-training data, perhaps in the form of foundation model. So you can go right now, type into DALL-E, a stroller with 3 wheels in the winter pushed by a man, which is very hard to find images of, and it will generate images for you. So somehow it seems like this notion of trying to deal with things in the tail, things that we have typically low examples of, we should really leverage these massive data sources that are now available to us. And so this is more of just starting the conversation. It don't really have an answer here, but we have one attempt at trying to look at this. And that is really leaning into this notion of these massive data sources. When they're multimodal, they kind of let you do some interesting things. One is, if you want to, so one claim is that that I think I'm willing to stand behind, that in the future, we really won't train anything from scratch. We'll always download a foundation model and then adapt it to our task of interest. So then it feels like a really crucial question is exactly how do you fine tune a foundation model? Is it just fine tuning the way that we normally do it, or do we have to do something special? And I think in the context of when you have multimodal models, you can actually do something kind of interesting where you actually fine tune on multimodal data. And so what I mean by this is there's an example of, if you have visual examples and you have textual examples, a really almost trivial trick for fine tuning is you encode both of these in your normal text encoder representation, your vision encoder representation. These produce features that are all the same dimensionality and are trained to live in the same space. And just think about this as now, instead of having 2 examples, you have 3 examples. So you just get this sneakily additional data and you just train your normal classifiers on top of it. It turns out this happens to be a very effective and sort of state-of-the-art way of fine tuning or linearly probing foundation models. And it has this sort of nice flavor that if you actually want to try to recognize things, you can actually learn representations that are truly multimodal. And we have this fun example of basically by looking at text of dogs, you can build better visual classifiers for dogs. And by listening to dogs bark, you can build better visual classifiers for dogs because you still learn this multimodal representation space. So I urge you guys to sort of take a look at that. All right, and so maybe if I have one more minute, I'll give another fun example of this kind of multimodal cross-modal recognition. That is looking at this problem of, I'll show you like this, looking at this problem of given images trying to produce street maps. And this is something that maybe in the vision community we haven't looked at a lot, but this is clearly a huge component of at least a lot of approaches to self-driving. Is we build maps that tell us what we expect to see in the world. And it's such a powerful prior because even when you have your eyes closed, you can still sort of make guesses about what you expect to see, where the stoplights will be, where the lane geometry will turn. But a very important question is, how do you build these maps automatically and how do you keep them up to date? Because if these maps become stale, you can actually close your eyes and think the wrong thing, and you get you can get very disastrous consequences if you can't trust what you expect to see. And so there's a question of there's a problem that other folks have suggested of, can we give an imagery spit out maps, where maps are this kind of computational graph structure of nodes and lane geometries with edges that connect them. And we just sort of explored a really simple approach based on cross-modal nearest neighbors. So essentially, you can build representations for graphs and build representations for images, and then try to learn through contrastive learning, representations that allow you to match the correct ones and not match incorrect ones. And by doing this now, given an image, we can just retrieve the closest matching graph with the closest similar embedding. So you can essentially think about this as nearest neighbors, but you're doing this across different modality spaces. And what we find is that this actually works very well compared to other more classic vision approaches that try to explicitly find pixels and link lane geometry in the image space. So I don't know if this is the final answer, but what's kind of fun about some of these examples is that this idea of cross-modal retrieval in some ways is even more flexible than typical sort of unimodal nearest neighbor retrieval, because which by itself also works really well, almost comparatively to the state of the art. Here's a chamfer loss. So the idea is that normally if you want to try to apply, let's say, nearest neighbors to the problem of spitting out row geometry given an image, you have to have a bunch of stored examples of images in row geometry. But what's cool about this is you can just have, all you need is a stored library of row geometries that don't need to be paired with image geometries. So what that allows us to do is even create augmented graph libraries by just augmenting graphs, because that's all you're matching to. So you don't need this paired data, and that by itself gives you a huge win. And maybe sort of more fun examples of cross-modal stuff in the generative space, moving from sketches to images. I'll skip that for the time being, but maybe I'll try to kind of summarize the high-level points here. So in terms of sort of 4D understanding, I'm sort of convinced that this is the crucial problem to really solve. Even if you really want to build end-to-end models, I think in order to train them, it seems like training on real data is going to be super difficult. This idea of if we can actually take real data and then build little 4D simulators of it, that seems like a powerful enabler to try to then do more end-to-end learning. And what we find is that for this 4D understanding task, the real crucial bit is understanding pixel movement. I guess there's this more kind of meaningful thing. If you do that, all of these things are very expensive. How can you actually distill them into fast things that can operate online on a robotic platform? We can do things like distillation. I guess that's not too hard, I think. And finally, these open questions that I think we're just starting to explore is how do you really bring to bear these large scale models that might have been trained on much more data, and also kind of interestingly across different modalities, which I think is super interesting and relevant for perception in this setting. All right, so with that, I will end. Let's see if there's any questions.
Question from audience.
Sure, thanks.
Wonderful talk as usual, Deva. Every time I hear you speak, it's like a year's worth of good ideas. I was very interested in the thing about the stroller and the fact that the rare classes are so bad. And it's a little bit weird to me to say that, well, you know, this stroller thing never appears and it's hard to find it in the data, but if you go to DALL-E, it's there, right? So probably the answer is that there's tons of strollers in Lion, but probably most of them are driven by women, and maybe like other things are different. But doesn't this mean that somehow if you just have some sort of self-supervised pre-training of your model, you don't need to go for text. You can, the data is still sitting there. Like there are strollers. All you need to do is just get them out without the label, right? It's the label problem, it seems. It's the text problem, not the pixel problem. The pixels are there.
Yeah, okay. Seems to be a bit more compositional. So I can say, and DALL-E will do this, a car with 2 front doors open and the trunk open and someone getting in. And that just seems super hard to observe. Right. And so this question of how compositional is it really is I guess up for debate, but yeah, you're sort of pushing against it because you really need language in this story.
The composition should be in the pixels as well, but you're saying, I guess, it's harder to get at it.
Yeah. So for example, another interesting problem that comes from this kind of like virtual world stuff is that it's also super important to, it's a bit more mundane from the vision perspective, but like validate these models. So you have something, someone gives you a model, you want to know, when does it fail? Like, is it going to work when there's a stroller that has 3 wheels as opposed to 2? And there's this weird question where I feel like I think some sort of language might help, because it lets you to sort of understand the ways you want to push and poke at this, instead of just being purely data driven. But fair question. Exactly how much language is going to play into it, I think is a super interesting question.
Thank you.
So another question from audience.
Yeah, first, thank you very much for the talk. I've learned a lot. And my question is also regarding this the stroller kind of example and the whole framework of using kind of foundational models to create all of these long tail examples. And is there a concern regarding the distribution shift from this kind of data set that is, generated using generative AI versus what the autonomous vehicle would see in the real world, and how can that be addressed and validated?
Yeah. So at least my own personal view is that at some level, the distribution shift is okay because like the real world is so skewed. Like the natural distribution is that I don't know the last time I saw a three-wheeled stroller pushed by a man. So in my natural distribution, it's almost never been seen. So I think at some level, we need some artificial shift at the very least for probing and analyzing things, for validating, and then maybe for training too. But handling that shift, I think, so I guess at some level, I think we need a shift. It has to be part of the story. But then given that it has to be part of the story, like, does it mess things up or not? My initial thinking is that it's not so bad. Like sometimes we intentionally rebalance to deal, like that's almost one solution for long tail learning is, we oversample the rare stuff or we undersample the common stuff. So I guess I'm not as worried about the distribution shift due to like placing objects. Maybe it's more about like learning faithful models of like how to place them. To me, that's a little bit more related to this world modeling, like understanding where are objects typically, how do they move. If we do that, then hopefully we can take a synthetic thing of a three-wheeled stroller and actually put it in a reasonable place and have that be faithful.
Thank you very much.
Yeah.
So maybe we have time for the one last question.
Thank you so much for the impressive talk. We are very interested in the 4D understanding, and we find that if we go that to the nerve way, it's very like dependent on the quality of the capturing data. For example, the coverage of frames over the scene. And from your experience, it's like nowadays, is there any public data set can already satisfy all the need, or you really need some like industry level, like the recordings and data set to satisfy this for the understanding?
Yeah. So I guess there's 2 points to bring up. So I think one big difference between like NERF and the way that's typically done, and then I guess what we're thinking about for this application is that we don't get crazy amounts of views, in the sense that we have a limited, like normally NERFs you have, I don't know, 100 viewpoints, scattered around an object, and so that's not the case here. You have very associated viewpoints because it's essentially one stream of sensor movement. So I think it's a kind of different nerve problem, but I think it's super interesting. So how do you learn when you really don't have that much multi-view data? It's really the views are not as spread out. And then in my own thought there was that I guess the question you're really asking is that do we need other data sets to really explore that? And yeah, I think I would agree. Like to really push this, one of the things that I would like to be able to do is that, can we build models that really tell us how the 4D world behaves, what objects tend to be there and how they tend to move. And that kind of scale of learning, it seems like it's not publicly available, certainly not in terms of LiDAR data. There's a hypothesis that maybe in terms of video data, it's there. But the thing that I see is that, the reason why everyone is trying to do video-based foundation models. And I think the reason why it's really hard to pull off is because if text was hard to manage, then images are way worse and video is just way, way worse than that. So I think it's not even just a data problem. I think it's like a compute infra problem. But even if we had the data.
In your view, in the future, we'll get there, right?
Yeah, I think so. I guess I'm sort of optimistic, but yeah, we'll have to kind of solve, I think, a bunch of almost like systems level issues, like how do you manage stuff and compute at this kind of scale?
Okay, thank you so much.
Yeah.
Okay, so let's say that again. So we have a student for you.
Oh, cool. Thank you.
Okay, so our next keynote speaker is Phil Duan from Tesla. So Phil Duan is a senior staff software engineer at Tesla. So he leads the autopilot team for occupancy network, object detection, behavior prediction, auto labeling, and online perception. So today's talk title of Phil is Building Vision Foundation Models for Autonomous Driving. So let's welcome Phil.
Let's share from this. Let me figure out the hardest part of the presentation. Sorry. Okay. All right. Thanks for the introduction. I'm very excited to be here with you guys to share some of the progress we have made on Tesla Autopilot for the past few months. So for those of you who are, okay, let me actually hide this. Anyway. For those of you who are not familiar with Autopilot, this is a self-driving feature building for all the Teslas made in the world since about 2016. And the features range from basic autopilot, which has like lane keeping, vehicle following, to what we call a navigate autopilot, which works on highway for lane changes, follow the route, take forks, to our most advanced software package called full self-driving. And this basically takes you from a point A to point B with no human interventions at all. And this is the video from one of our customers driving in San Francisco. As you can see, that it is capable of navigate through a complicated city, taking turns, yield pedestrians and traffic signs. And the uniqueness about our approach is that we are very famous for doing this with vision only. So all this is done with just 8 cameras around the car, provides 360-degree field of view. And these cameras runs on 36 frames per second, and it processed by 144 teraops of compute in our car. And we also do not use any additional sensor and HD maps whatsoever. And this works, anywhere in the world for basic autopilot, and it works for full self-driving with North America, including Vancouver. So, if you go to a Tesla store today, buy a car, you can do this yourself. And currently we have about 400,000 cars driving with the full self-driving software. And cumulatively, they have driven more than 250 million miles. So you can see that it's like a lot of data coming from the fleet. And for all the other cars, autopilot is always running in the background, even though it's even when human was driving. So we provide a activity safety feature for things such as automatic emergency brake. So when human makes a mistake, the autopilot will try to take over and protect the safety. And besides that, autopilot also runs in the background to collect more data to help us to build our neural networks. So so there are roughly about 3-4 million cars running in the world today to do this data collection. And you can think about these are robots on wheels. So besides autopilot, about 2 years ago, we also started to make a humanoid Tesla bot called Optimus. So this is the basically in a humanoid form factor. It has a very impressive hardware platform, 200+ degree frame body control. It is built for a general purpose robotics application. And as you can see that the robot obviously has a completely different form factor than the cars, but we were able to leverage a lot of lessons we learned to build the cars, build the compute, and build the software to bootstrap this project. And the bots are basically, rubbers on legs, and as I said, it shares a lot of stuff from the car. One example, it is that it shares the same compute platform. So this is the in-house built FSD computer chip with a 144 teraops per second compute, and this runs all the tests in the world, and also is used to power the robots. And because we have the same computer platform, it's also fairly straightforward for us to build the same AI software stack. So the Optimus and the automated software team, we work very close together. We share the same repo, and when we build the computer vision models, we try to leverage things so that we don't have to build two separate applications. And this also kind of enforces us. Whenever we build new software, we have to think about, how do we build something that is foundational, that can be shared among the two applications. So one of the network I can mention is the occupancy network. I think ties pretty well with the challenge we have later in the workshop. So we effectively have the same network running on both the bus and the car, with just a little bit of tweaking where certain things are more relevant to cars and certain things are more relevant to the bus. Even though it is a completely different environment, outdoor versus indoor, we're able to actually kind of build a network from like exact the same model with just a little bit data difference. And I think we showed this occupancy network the first time at a CVPR last year, and since then we're kind of very excited to see how the research community has reacted to this. We have seen all kinds of different variations of this coming out. There's also challenging with hundreds of people participating, and I'm definitely very excited to see where this is going next. But for those of you who are not familiar with this, I'll just do a quick recap on this. What the occupancy network does for us is that it takes all 8 cameras image video stream in and produce a single unified volumetric occupancy in vector space directly. It has video context, and for each point in the 3D space, we predict whether it is occupied or not. And because of the video context, we are able to reason about occlusions and predict the things are behind visibility region. And the blue contour showed earlier here briefly was the way we use to model the volumetric visibility. And it also has a dynamic resolution. As you can see from the video here, certain voxels are bigger than the others. I will go to more details later. And for each of the voxels, we also predict semantics as color coded here, such as curbs, cars, static, road debris. Those semantics are usually defined for more driving relevant classes. And as you can see, for Optimus robot, we'll use kind of a different set of semantics. It also produces occupancy flow for motion. Since this network is very generalized, it does not make any assumptions on the object shape or motion. So it is able to capture arbitrary motion such as a swerving trainer here. And this network right now runs in all Teslas in the world with the FSD computer, and is incredibly efficient in memory and compute. Runs about every 10 milliseconds with our it also helps with latency, able to remove ISP in the loop, and it is we don't even do any tone mapping at all, and all the images generated here are actually done post-processed just for human eyes. We take these images and we rectify that with the camera calibration. And we then feed these rectified images into a set of RegNets and BFTNs to extract multi-level image features. Then we construct a set of 3D position queries along with the image space features as keys and values, and we feed them into an attention module. The output of the attention module is some high-dimensional spatial features. And we align the spatial features with vehicle odometry to create, to capture motion. And this is kind of like a simplified here, but it's a lot of work done happening here to just make sure the vehicle odometry is done correctly to recreate what's happening in the car and to align the features precisely. So, and after we do this, we're able to create a very rich spatial and temporal features, which we then pass through a set of deconvolutions to provide the final output for the volume, which include occupancy, flow, semantics, and so on and so forth. But the output of this volume is in a fixed sized voxel gray, which is not precise enough for control. As you know that, when things are close by, you have to really know these dimensions very precisely, and things are farther away, probably does not matter that much. And the way we solve this problem is that we also predict feature maps on a per voxel basis. And then we feed it into those per voxel feature maps into a set of MLPs with a set of 3D positional queries. So as the output of the network, we can query any 3D positions around the car to get the output. So after knowing the model better, let's look at one more video. Here we have an articulated bus parked on the side of the street, illustrated by the red L here. As we get closer, the bus starts to move. As you can see, the front of the bus turns blue first, indicating the model is predicting non-zero velocity. And as the bus keeps moving, you can see the whole thing turns blue, and you can see a very nice shape capture the motion and the position of the bus. So this is kind of like a awkward task for traditional object detection, because you have to figure out, okay, what's the formulation? Do I use 1 or 2 cuboid to represent this bus? But for occupancy network, it does not matter. All we care about is what is visible and what is the motion. So our car will be able to actually handle and yield to this bus correctly. Besides this voxel gray, we also predict surface output. And the surface has both 3D geometry as well as semantics. So by semantics, I mean we also capture the color of the surface and all the road markings on surface, whether it's a stop line, lane lines, or like any yield signs, stop signs that are on the ground. And we found this to be incredibly helpful for driving in unusual driving environment, such as San Francisco, which has a lot of hilly road and curvy road, where knowing what the surface looks like in 3D space removes the flat world assumption, and we found that incredibly improve our driving smoothness. So, and the surface or the volume are actually not output separately. In fact, the volume output is actually aligned with the surface implicitly, so that when you go through a different surface area, the voxels does not move up and down. It always just aligns with the drivable surface. And as we can see from this video here, the car is going through a hillcrest area. You can see this 3D shape of the surface very nicely, and it aligns with the voxel gray as well. So we can use this for a lot of different things. For example, the planner can use this information to decide how fast we should be driving here, and also it helps us to reason about occlusions, because sometimes the occlusion is not really due to any obstacle; it's just because the lack of surface as the surface is like going down. So we kind of built this network, and it runs in the car for about, I think, probably almost 2 years now. And then it works very well. So we start to think, what else can we build on top of this? So early this year, we had this very fun project where we start to predict a distance field around the car on top of the occupancy network. So this is literally just put a small head on top of the network and do a regression test to get a distance field. And we then show this distance field on UI for customers as a manual driving feature for parking or maneuver through very narrow area. And this is the video with one of our customers doing a parallel parking. And you can see from the right side that this contour is generated by this distance field. So compared to like traditionally, usually this is done with ultrasonics, right? So we just most of cars have ultrasonics on the front, on the back, and trying to just measure the distance directly. And the advantage here is that first we have 360-degree coverage. Let me just play this video one more time. And then it also is able to capture the obstacles at different height because we don't have this sensor limitation. So for example, the curb, and ultrasonics is usually pretty bad with S-curve detection. And third is that it covers arbitrary range, right? So we don't have like a range limit from the ultrasonic sensor anymore, and it's able to basically capture according to as large as what we want from the accuracy network, and we just show as a range that is comfortable for the driver to use. So this vision-based park assist is just a small application. But while working on this, we realized that this model actually has really rich features that's able to capture a lot of things going around us. And so we start to think, okay, how can we leverage this and build a really strong world model? So if you zoom out a little bit and look at this network, right? So the bulk of the network, all it does is really just create this world model in the vector space features. And this kind of ties to the previous talk where, we really want to just build like a really nice 4D world model to understand the world. And once we do that, all the downstream tasks are actually just tiny heads that is very easy. And we can just like plug in, do some fine tune on that. It usually just works very well. I couldn't find a very nice picture to capture this, so I just put a Tesla logo there to represent the vector space features. So, but what we're really looking for from this direction is really just like how do we build this 4D space world model feature, and then we can just use that to capture everything we want for driving, for humanoid robot, or for anything that related to embodied AI. And if we do this correctly, we'll be able to use this feature to capture everything that is relevant for driving, whether it is the aforementioned, a volume or surface, which has, all the information we need for understanding where to go, and for objects, for lanes, and for traffic control. And instead of trying to build different models to tackle each one separately, we really want to just like build one model that does everything together. And traditionally, we shared a lot of features from image space, which just extract the 2D information. That information is actually not quite enough for doing this kind of foundation model. And now, since then, we have changed our approach to actually combine everything in vector space, so that we just need to build one model that does everything very well, and then then connect them with different tasks for downstream applications. And in order to train such a big model, obviously you need tons of data. So we are very proud that we built this very mature data engine in the past few years. And this, in my opinion, is one of the biggest advantages we have here. So what do we do here, if you start from the bottom, is that whenever we have a model, we deploy it to the car. And then we mine the model with millions of Teslas on the road. And we mine mostly to two things. First is that we use heuristics to detect things that happen very rarely, so we can get the data back and then feed that into our network. The second is that we also run this compared to what a human does. So to understand that, okay, what is the inconsistency here? What did our model do wrong so that the human made a different decision? And once we have this event trigger, we put this data back, and then we automatically label this data to generate this beautiful ground truths in 3D space, and then we use to train this model. And we call this approach fleet learning, basically learn everything from our fleet. And most of the work happening at Tesla Autopilot is actually just crank this data engine and get the fleet learning going. And we have engineers looking at data all the time, and arguably spend more time on data than the model. And give some examples of data. We showed this video at AI Day last year, which shows how we leverage all the fleet from all the Tesla vehicles from the same intersection. We put them together to reconstruct the 3D surface and the lanes jointly, which will be able to actually create a ground truth neighbors that much better than if we were just to do that with a single trip. You can see all the lanes are very consistent across different videos, across different trips. And then we feed this data into our network to train our lane network. And the good thing about this is that our customer drives the Tesla in all kinds of different locations, and we get data mostly from the places where with a lot of Teslas. And guess what? That's also the area we care the most about. So we can immediately feed this data back to our training and train a network, deploy to the car, and the customer will just have a much better model because of their driving. And this year, we extended this same approach. Besides names, we start to model everything. So this is a 3D reconstruction from multiple trips of Teslas in the same area, and we put together. All this is generated from 8 cameras of video streams, and we put together through different trips. And you can see that it's able to capture all this very high quantity information, and we can use that to train all kinds of stuff to make sure the world is consistent. And all this data is very rich in terms of that. We don't have a separate data set just to provide one ground truth anymore. We just have a unified data set that captures everything we need to train such a foundation model. And besides the data quality and the quantity, the other thing that really matters is data diversity, right? So if you only have, boring data, this thing will rarely work. So this is also one of our biggest advantage where we can get all this data back from fleet. So this is just some examples of the random Tesla customer driving. So I will just pause for a second, let you guys to see what kind of crazy scenarios we can see here. A lot of the stuff is, when you will rarely run into in real life, but once you aggregate over 4 million cars, it actually weird stuff happens every single day. And what we do here is that we put this data back and put in the data engine directly, and run the auto-enabling pipeline, fit into the data set and the model training. Once you put all this stuff together, you'll be able to just build a very large, highly diversified, highly quality data set, and we use the train foundation model. And in our opinion, this is the path forward to build a foundation model for autonomous driving, and as well as eventually the whole embodied AI. This work presented here is done by dozens of very talented engineers at Tesla Autopilot. It's my privilege to present on their behalf. And if you guys are interested in this, please consider joining us. Thank you.
Any questions from the audience? Yeah.
I know that Elon Musk has claimed that we will have end-to-end system in the FSD12, right? And I would like to know how the occupancy network you have mentioned can be changed or even fit to this kind of end-to-end system.
Yeah, so that's a good question. Yeah, so basically we're building this network. So it's not really the occupancy network anymore, right? So we're basically building this foundation model to capture this world model, and we think that will be essential to use for end-to-end driving. And as for the end-to-end driving application itself, we're not ready to show what we have done so far yet. And I guess stay tuned.
Okay, so you just mentioned, so probably occupancy network is mainly used for building the foundation models, but not used in the end-to-end system.
Exactly. Yeah. Yeah.
Hey, thanks for the nice talk. How do you compare attention, self-attention or cross-attention based occupancy estimation with traditional multi-view stereo? So like
I would say that I'm a big fan of transformers. So, and we've definitely tried the different approaches, and the transformers just like works amazingly well. And it is also very resistant in terms of, I'm a big fan of like learn-based stuff where the information will extract more implicitly, where for different cars, when you do multi-view geometry, it is like usually a very deep like uphill battle in order to get every tiny bit of the geometry detail correct, so that you can build everything and correctly. And this kind of stuff just works much better, in my opinion, with the attention module, which goes to play well with our strengths of a huge amount of data. When you learn from most data, the model just learns it very nicely.
Cool. Thank you.
Hello, thanks. Thank you for your wonderful speaking, and I have two questions. The first is, what do you think the problem of occupancy network? For I have talked to many researchers. They think the occupancy network are too dense. The feature or something are too dense and too heavy to do, and every disadvantage of segment model, the occupancy model also shares the disadvantage. So what do you think the problem of these advantages of the network of the occupancy network, and when there is a question two, and what is the next after occupancy network? Yeah, I have to.
Yeah. So there are basically quite a lot of different representations for like this occupancy, right? So we use kind of dense voxel gray, and you can also do any other representation, implicitly, SDF, this kind of stuff. So the as I described in the slide, basically we have this dynamic resolution thing, which is a way to help us to make the network actually small enough to run in real time, right? So we don't just like naively say, okay, we need X centimeter resolution, so we have to segment the entire world in such thing, which is obviously not scalable. So I would say that the dynamic resolution thing we did here is one of the main reasons that we're able to actually achieve a high perception performance while running incredibly fast and efficient. And a lot of advantage we have is also with our own neural net accelerator. Basically, we build in-house so that we're able to actually accelerate this with what we need. And I kind of just said that in like one sentence, but it's an incredible amount of work actually happening in the background just to make this thing run fast enough in the car.
Okay, thank you. So what's the next? Is there any idea?
Yeah, so the next idea is that I would say that basically the occupancy thing is really just like building these features for the world model. We eventually it's not gonna like, I don't think we'll explicitly be driving on top of that. So these features give us this 4D understanding of the world. And I think the next steps, a lot of the next steps will be really just like on the application level. How do we derive different applications in a very lightweighted way to represent different scenarios?
Okay, thank you.
Yeah, hi, Fias. Thanks for the great talk. So like, people are now very confident in the foundation models, especially after ChatGPT comes and solve everything. So people are like more and more confident in these foundation models, especially how they will solve the autonomous driving task. So I'm curious about like, how can you quantify the data distribution for the foundation model in a driving task? Like as you mentioned, there are many factors in the driving, like dynamic mode, static object, and also the lane factors and the different classes. So as you mentioned, like when you get more data, you will determine whether the data is real in our current data, and we fit into our model. So I'm curious about how can you quantify whether the current data is real, or how whether the data is valuable for the retraining of our model. Yeah.
Yeah, that's a good question. Yeah, so I guess the data is basically used for whatever we need, right? So what we do is that we build a very good, there's two, I would say there are two sets of this for this. First is that we have a very complicated eval system to actually capture what is actually required for driving, right? So basically we're not building data for the sake of building data. We're building this data set to address problems. So we need to really measure our progress in terms of different scenarios so that we know which one is working well, which one is not working well. And sorry, I lost my channel, sorry. And on the flip side, it's also like there's like this scaling law basically has proven to be very well done with the language model community, right? So what we also look at is that we're applying scaling law to video module as well, right? So to vision models. So how do we basically build a model at what point the model is the data is big enough, right? And whether data is about like or model is about like, right? So obviously because this runs in an embedded system in real time, so you cannot just naively scale scale up the model. So usually what we do is that we basically figure out what the model, what is the best size of the model that is runs in a car, and then we scale that according to data, according to compute, and according to different parameters to figure out what is the best combination. And while doing that, usually it gives us a very good idea about how the data quantity and distribution.
Yes, thanks for the answer.
Thank you.
Hi, thanks for the great talk. So I have some questions regarding deploying transformers on vehicle. So actually transformers, we have like we basically find transformers are much more difficult to actually deploy. We are not just talking about academic here. We're actually talking about engineering, and to build a product, actually you need to make everything real time on the vehicle, and the hardware perf is. I think transformer operators create a lot of difficulties here. I'm pretty sure you. So I wonder if you could share some insight, and also I wonder like. Because right now, at least for camera-based perception, a lot of the state-of-the-art research were also like purely CNN based. So when you are building the product at Tesla, do you find that actually there are cases or there are insights where there are something that CNN simply cannot do the same good job as transformer, that you are willing to pay the cost for deploying the transformers? So maybe generalization at scale, or maybe like some others. That's my question. Yeah, thank you.
Yeah, so absolutely, deploying transformer is not very straightforward, I would say. So we actually goes to the previous question where we have an in-house neural net accelerator, which actually gives us a lot of advantage, because when we build this chip, we don't have to worry about somebody else has to use this chip, right? We only build this for our own application, which obviously transformer is a big part of that. So we have a very good deployment team actually work very hard on how to optimize this for deployment. And so far, I think initially it was quite challenging, but once we get working, it actually runs incredibly fast with our computer. And we also did a bunch of study for CNN versus transformer as well. And for us, it's that we're not we don't really worry too much about the philosophical debate of CNN versus transformer. We just use whatever runs fast and also does the job. And transformers obviously scale very well with the number of parameters, right? But we are because it's a real-time system, so we're also not going that route to just like go from that. And when the parameter counts are lower, sometimes certain CNN actually does better than transformer. I think highlighting complex, for example. And we definitely kind of try to take advantage of both and put together to build such a network.
Thank you.
Thanks for the talk. I'm just talking a little about some challenges for generating occupancy map right there.
Mm-hmm.
So I guess I saw there you consider some night vision or some low light vision considered right there. But I'm just wondering if you consider some adverse weather conditions and contaminations on the sensor or something like that, then that make it very challenging to generate occupancy map right there.
Absolutely, yes. So those are definitely the most challenging scenarios for us, right? So basically our customers drive everywhere, and a lot of places at different season with very challenging, scenarios. I think I probably have seen more adversarial weather events probably than anybody in the room here, just like all over the world, and we have to deal with all that. And on one side, that the fortunate thing we have is that we have tons of data from those, and we're able to actually targeting those problems specifically, solve them one by one. On the other side, definitely on the modeling side and the ground truth generative side, I would say most of the work is actually spent on dealing with such scenarios. And the normal sunny day driving scenario is actually quite straightforward to do. We usually don't have any engineer in the loop. You get a clip back, you run, it just works. And most of the time and the effort we're spending on is actually for all these adversarial scenarios.
Is that on Tesla, under studying about how to tackle, how to deal with that weather condition right there? Are you still studying about that part for FSD?
Yeah.
So now you are developing that to handle those kind of bad challenge condition right there.
Yeah. I mean, so what we do is that the ones we already, for example, you can drive FSD in snowing days, in foggy days, for example, it works just fine. And we also we gradually move to even, there's always long tail events we'll try to solve, right? So if you drive Tesla, you'll notice that sometimes it will tell you whether it's degraded, so certain functionality is not working as well as expected. So that is also very important to have a good understanding of what you are capable of doing and what you're not capable of doing, and to ensure the safety. And in the long run, obviously we'll have to solve all this problem. Thanks.
Hi, in your demo, it seems that you created the ground truth, and it seems that only the static objects are created. Do you create the ground truth of the moving objects?
Yes, absolutely. Well, moving objects is a big part of the driving. Yeah, we'll have that too.
It seems that creating the ground truth of moving objects is difficult. Could you explain how the difference of the creating process?
Yeah. So I guess it's a bit of a history here, where when we started, we only do moving objects, right? Because those are more relevant for driving. And so we actually, I think it's a fairly common approach among all community that how we model moving object. We started by just doing a cuboid, right? Just like fit every car into a box, and then but then gradually we realized the problems such as the articulate bus ones were shown here. So we had to actually model the exact shape of the objects. And a lot of them are done basically through what we call offline tracker. Basically, we take all the videos back from our cars, and then we process offline to figure out what is going on. So that usually involves three different things. First is that we have kind of like traditional robotics algorithm to use to help process the temporal information. Second is that because you have future information available offline, right, you're able to go forward and backward to actually create a ground truth that is much better than what you see in the car in real time. The third is that we also build large offline models to do this. So the models we use to run the offline ground truth generation is especially for moving object are much bigger than one we run in the car because it runs offline. We're actually able to do that. So usually, so that's the way how we get a really good ground truth for moving objects.
Thank you.
Okay, so due to the time, maybe let's thank Phil again. Okay, for you.
So hi everyone.
Okay, so our next session would be two state-of-the-art solution. This presentation on this 3D occupancy predictions. So two very exciting presentations. So the first one is from Chonghao Sima from Shanghai AI Lab. So this talk will be online. And the second is from Zhiding from NVIDIA. So this will be in person, right? So let's welcome Chonghao Sima first. It will be an online talk, 20-minute online talk. Yeah.
Okay, so thank you, Ziwei, for introducing me. So hi, everyone. My name is Chonghao Sima. I'm from the Open Driver Lab at Shanghai AI Lab. So today I would like to talk about, from bird eye view perception to scene-next occupancy, an overview of camera 3D perception done by Open Driver Lab in recent years. So let's give us some background knowledge about why we need 3D perception. So apparently we have 3D perception in terms of driving to sense the world around, and then in the robotics and in body AI, we also need the 3D perception to find the affordance in the surrounding environment to get what you can touch or to do the housework. And so why we focus on camera-based methods? So there are some basic 4 reasons for that. So it is low cost. It is easy to deploy. It can sense long range, and also it is rich in semantic appearance. And so what is the core issue in camera-only 3D perception? So we think that it is the accurate depth. So this is a bridge. So if we fill with the accurate depth, so we can bridge the gap between the camera-based and the LiDAR-based method. So here is a simple example to help you to understand this. So in the monocular 3D detection or tracking by detection, if we have a depth arrow, you can see here in the BV bird eye view. So you can see that depth arrow will cause the big gap between the ground truth and the prediction bounding box. But we fill with the correct depth or at the same time, so the ground truth and the prediction will align well. And then how do we solve these accurate depth issues? So there are many tracks to solve this. One is called the pseudo LiDAR. So we can predict. So if we don't have the accurate depth, we can predict the depths to form such a pseudo LiDAR things. And then is the center point track. Here we can detect the heat map in 2D to infer the pose in 3D based on the geometric mappings from the 3D space to the 2D perspective view. So the first way is to do the depth pre-training. So we can embed the 3D prior knowledge in the 2D pre-trained backbone, such as the work done by the TRI, the DD3D works. So it is a very successful 3D backbone used in many challenges and many 3D works. So the last thing is that we can do the bird eye view transformation. So we are transforming the perspective view feature to BV feature to facilitate the following task. So there's a trending in the bird eye view perception in recent years. So from 2021, we have HDMapNet, which is given the HD map in the bird eye view coordinate to propose the aggregation feature based on both camera and LiDAR. And then later years, we have the DTR3D and the BVDAT. We are able to fuse the object detection using the omnidirectional cameras in BV. And then in 2022, we have the BV transformer to explicitly construct the BV representation feature from the camera parameters. And then later we have some fusion works, so sensor fusion works such as the BV fusion at the FQ TR3D. In this time, we are fusing the multimodality features in the bird eye view representation, since it is a very convenient way to fuse the different modalities features. So the core problem here is that how to model the view transformation from the perspective view to bird eye view more effectively. This is the core issue when we do the bird eye view perception in camera-based methods. And then let's go into a deep dive into the view transformation. So there's basically two ways to do the transformation. One is from the 3D space go back into the 2D space. So this is basically camera projection figure to help you understand that if we have a 3D, if we have a point in 3D space, how to project it back to the camera plane. So by doing this, there's a problem that multiple 3D points will hit the same 2D pixels when even when the resolution is very low. And then we can also have another way to do that is that we are given the 2D image, we can predict the depths per pixels to reconstruct the 3D space. So so this is another problem is that the depth is unknown for each pixels. So it is obvious that both way has its pros and cons. So no matter what, the view transformation itself is a ill-posed problem. So to address these issues, there are basically two ways to address the view transformation. One is based on the 2D to 3D prior. So now that the depth is unknown, we can predict the depth itself. So this work is illustrated by the famous work like the leaf splash shoot and its variant like BV depth, BV depth, all this work. And another line of work is the pseudo LiDAR family. So the second way is that we based on the 3D to 2D prior is that we index local feature according to the projection from the 3D to 2D. So one promising work is shown by the DTR3D and its variant. And then the second work is done by some explicit BV feature construction, such as BVFormer, which I will introduce later. So the third way is an implicit 3D positional embedding, which we can embed the 3D position back into the 2D coordinate space. So now let me introduce our work in ECCV 2022, the BVFormer. So the setting is that we are given multi-camera and the temporal input. We can construct a BV feature based on this multi-camera and temporal feature by using the deformable attention, and then we use a BV query to look up for a current BV feature map. So here the BV query has two attention mechanism to do the fusing. So first is the spatial cross attention mechanism. This is to fuse the multiple camera feature into the same BV grid space. And the second is the temporal self-attention. So this is to aggregate the temporal feature from the history. So this figure illustrates the idea very well. So now we start from the BV query. We have an eagle car here, and now we want to know that what is in here at time step t. So we go two ways here. The first way is to do the temporal self-attention. We go back to the history BV feature and check that what was in that grid in the time step t-1. And then the second way is that we do the spatial cross perspective view on the image, and then we sample the feature back into the BV space. So this is the multi-camera images at time step t. So that by fusing these two features, we can construct we think is a very strong and very expressive the BV feature at time step t. And here is the BVFormer pipeline. So for more detail, you can check out our GitHub repo. Yeah. So here is also a visualization result of the BVFormer on the new set dataset. And then we have a second work called the Performer. This work is from a similar idea, but we are focusing on the 3D link line detection task. So we are instead of using the sampling task, we use the IPM-based cross attention for BV feature. The IPM here means the inverse perspective mapping. So we sample some 3D points based on the assumption that the ground is flat, and then we sample some point in the 3D space and back project them into the 2D space. So both the BVFormer and Performer shows that the BV perception is prevailing since the 2022 in academia. And then we want to ask a question in the next step, say, what is the problem of current 3D perception representation? Say bounding box is a very prevailing representation. So 3D bounding box itself, it ignores the detailed geometry of an irregular object. Say that you have a irregular car here, you have the arm out of the bounding box, but your bounding box cannot just depict the arms very well. So instead, if we use the 3D occupancy here, it can catches the geometry shapes well. And also the mobile eye and Tesla also adore such a representation, as Feldon just say that. Yeah. And so so back to here, I would like to go over how does the 3D perception evolve into the 3D occupancy. So back in 20,000, we have Professor Andrew Zisman to write a book about the multi-view geometry in 3D computer vision. He basically tells us how to do the 3D geometry mappings and projection between the 2D and 3D space. And then in 2012, we have a Kitty dataset release. So this sets the benchmark for the monocular, stereo, and LiDAR 3D object detection. So after that, 3D bounding box become the prevailing representation and all the task objectives for almost every 3D vision task. So we have many baseline methods at that time to be established, and then those methods you know well, so I won't read them one by one. So meanwhile, at the same time, we have the new sense dataset and the semantic kitty released. So this introduced two new works, two new tasks here in 3D visions. One is the multi-view 3D object detection and the map segmentation. And then also introduced the LiDAR segmentation and the semantic scene completion. And we noted that the semantic scene completion is very close to the idea of 3D occupancy, although it in the scene completion task, it emphasized the need of completing the scene based on the LiDAR input. So instead, we are starting a camera only methods to complete the 3D scenes. And then later, the people in academia and industrial start to address the monocular and LiDAR and fusion tasks. And at that time, many industrial preferred methods were proposed, like the center point, like the FCOT 3Ds. So at this time, the 3D vision tasks are getting advancing. And then at that, meanwhile, we have the panoptic new sense release. It is a LiDAR panoptic segmentation and tracking task, so that it provides the foundation of doing 3D occupancy in later years. And after the 2021, so the academics starts to shift attention to address the BV map and lane detection and segmentation. So these I would say these are the static objects on the road instead of the dynamic objects like cars, trunks, and the pedestrian. So meanwhile, at the dataset side, we have the Waymo open dataset and the open lane release, which is a larger scale LiDAR and camera 3D object detection for the academy. Yeah, so since 2022, so the BV perception is prevailing. So many multi-view and temporal clues or priors are addressed by these methods. And later in this year, we can come to a great attention on the occupancy tracks. So in occupancy, we would like to I would like to introduce our challenge this year, host with the Tsinghua Mars Lab and the Motion Node, and we have done a very great job in this. Yeah. So let me introduce the 3D occupancy prediction challenge. So in this task, the input is the multi-view images, and we output the occupancy state and the semantics labels in the 3D scenes. So yes, you can see the visualization here. This is based on the new sense dataset. So what is interesting here? So the first thing is that we have the camera only. It is a camera only general scene perception, and the second is that we are working with Motion Node to exclusive generate the test set labels. So based on the challenge participation, we have seen some trends in the 3D occupancy. The first is that the BV perception, the idea of BV perception is still prevailing. Many methods start to reconstruct the 3D occupancy based on the BV features or perception results. And the second is that we found that the depth supervision matters in many very good participants methods. And then we found that the data augmentation and 2D supervision also helps the 3D occupancy. And then we have some interesting finding that the occupancy is better in depicting the geometry of the scenes, while the 3D bounding box is better in object class prediction. And then we found that for the network itself, so the bigger backbone, the better performance. This law is still exists. So the benchmark, we introduce some dataset stats and the visualization results here. So if you're familiar with the new sense dataset, it is almost the same. So for the metrics, this is a tricky part since it is the first time we host the 3D occupancy challenge. We use a very simple matrix called the mean error view, which you are very familiar with the semantic segmentation task. And then I think that for the matrix part, it would be much more advancing or much more attracting that we can devise more metrics based on the need of the 3D occupancy. So here I post a QR code here for you to scan it if you want to learn more about these tracks. And there's some challenge stats here. So it shows that this is the most fierce contest challenge this year. So we have participants ranging from the academic to the industrial. So we have 145 teams participating, and the country regions are covering 10 countries and regions. And we have more than 400 valid submission. So the SOTA performance double from the baseline. So we have the baseline methods released at 23.7 at MIOU. So finally, the SOTA methods reached 54.19, yeah. And the matrix variance, the top three matrix variance is only 1.4. So it shows that the contest is very fiercely. So here is the challenge leaderboard. So the top 10 elegants here. So we have the immediate team as the outstanding champion. The 42 dot from the South Korean have the run out. So we also have an innovation award to the fifth place, the Harbin Institute of Technology. They are performing very insightful how to do the 3D occupancy from academics, so you can better check them papers. So all of these leaderboards and their papers can be accessed by our challenge website here. So I place a QR code here for you to visit. Okay, so it's about 20 minutes, so I think I should switch to the NVIDIA team for them to give their presentation of their methods. So yeah, thank you.
Research scientist at the Machine Learning Research Group, NVIDIA Research. So before joining NVIDIA in 2018, he obtained a PhD in ECE from Carnegie Mellon University. So he is the outstanding champion of the 3D Occupancy Prediction Challenge. So Zhiding's talk title is 3D Occupancy Prediction based on forward backward view transformation. So let's welcome Zhiding.
Yes.
Oh, okay. Okay. Hello, everyone. Thanks for attending the talk. Today I will present the FBOCC 3D occupancy prediction based on forward-backward view transformation. This is a winning solution for the 3D occupancy prediction challenge. This work is jointly done with Zhiqi, David, Mingsheng, Shiyi, Yang, and Jose. Yeah, so recently 3D occupancy prediction emerged as an important task for AV, and compared to object detection, 3D occupancy prediction incorporates more richer real world information, and therefore these information are very important towards the planning and prediction stack, and therefore towards end-to-end driving. So if you look at some of the in the academia, people have been thinking about like similar problems, for example, semantic scene completion, which is in some sense also this semantic occupancy prediction. And there have been solutions based on various modalities. So for example, we have these we have LiDAR-based solution. We have solutions based on RGBD camera where you have the additional depth modality. And then, of course, there are works that start to address camera-based occupancy prediction. And obviously, camera-based occupancy prediction is very challenging because you only get 2D input, but you have to output the 3D without any depth information. You actually have to infer from the camera. But the good thing of camera-based solutions, of course, cameras are very convenient to gather the data and also cheap to use. So this is the advantage. So and when we think about these 3D occupancy prediction, they are also highly correlated with the 3D traditional 3D object detection. In the sense we talk about perception in the BEV space. The difference is mostly we are encouraging denser and richer output from the network. So therefore, the network designs of 3D occupancy prediction are very naturally highly correlated with existing BEV perception solutions. So that's why I'm going to give some brief here, because there are many BEV solution state-of-the-art work. So I'm only picking two that are closely related to what the solution we built on. So the first one is BEV depth. Actually, this one is an example of constructing the BEV features using forward projection. The forward projection method they use is a lift splash shoot, which is also a method proposed by NVIDIA, by Sanya's team. So the way this works is that you could leave the you use an image encoder to encode the image features. And then what they do is that after lifting, so they use the LiDAR depth as a depth supervision to actually supervise a depth network built on top of the image features. And this depth supervision turns out to be very important for the accuracy of the BEV perception. And you can incorporate this depth information together with a context feature, and you build up the BEV feature. This BEV feature now has a good sense of the depth perception. And finally, you try to output the bounding box inside the BEV space. And note that this work is actually heavily based on science. But the next work that I think just now it was introduced is a BEV former. This is also the work done by Zhiqi. And other authors from Shanghai Air Lab. And also, so this one is actually a transformer-based solution for BEV. And this one actually features backward projection. When we are talking about backward projection, we are talking about we can build up learnable queries, transformer queries in the BEV space and back projecting to the 2D camera domain using deformable using deformable attention. So from this, we talk about these two works mostly because they are very representative works of forward projection and backward projection. These are two kinds of projections that are predominantly used nowadays in the state-of-the-art BEV solutions. And also there are some interesting works that are directly related to this occupancy prediction. And if you look at their architecture design, it's also highly related to this BEV solution. So for example, this monosync is one of the very early works that start to address camera-based semantic sync completion using neural network. And if you look at, and basically this module here is also a 2D to 3D view transformation module, very similar to orthogonal feature transform, but in a multi-scale manner. And then they have some UNet module that after you basically aggregate these features in the BEV space, you can use a UNet architecture to process it in the BEV space and finally output these predictions. The other work, which also we proposed this work at NVIDIA is Voxformer, and actually this work is accepted to CVPR this year. So we will also present this work at CVPR. And this one features a two-stage framework with backward projection. It's kind of similar to BEV former, and the way that it works is that it has two stages. In the first stage, you actually have a depth network that kind of propose a set of sparse queries in the space. The logic and the intuition behind this is these visible queries in the 2D domain. They are the most they contain the most abundant feature. They are the most reliable ones. So that is why you start to fill in the missing information, starting by prioritizing the featureization of these sparse queries are important because they are the most reliable one. Then you start to fill in and use an MAE styled approach in the second stage to fill up the missing pieces in the BEV space, and finally you have a dense output to predict to give you the occupancy prediction. Yeah, but one of the maybe small limitation is that this is a two-stage, and then it's not a single architecture. And also I will soon also talk about the limitations with forward and backward projection together. So here's the proposed model design. So if you think about this is a typical architecture of a camera-based BEV perception solution for autonomous vehicle. So you have multiple camera input. You have image encoder that encodes these camera input, and and then there is a module that is 2D to 3D view transformation module that leave these 2D image features into a BEV, into a Minecraft world space, centered at the ego vehicle. And then you have some encoder decoder in the BEV space, and finally you do the prediction. Now this view transformation, no matter forward projection or backward projection, it's very important. It's at the core of these BEV perception. Pros and cons with forward projection and back projection. So when we think about forward projection, the good thing is we start from camera pixels, and we build up we project the features into the BEV space. So a resulting problem is that because you are shooting rays to the BEV, that's why the rays gets more and more gets sparser and sparser as they go away from the from the ego vehicle. So that is a problem because ultimately your prediction are based on these BEV features. And if the rays get sparse, that means the sampling at those locations gets sparse, and that creates some problems for the prediction. This is one thing. But the good thing about these is, for example, method like lift splash shoot, they can encode the depth prior information very well. So using depth pre-training techniques works very well for this forward projection method. The other way around is a backward projection. And the backward projection, the representative work, of course, is a BEV former. But the problem is, as you start from a query and back project into the camera domain, you don't have a sense of these depths. So that is why actually you start to see these very like ray-like heat map, these emerging in the BEV features, and that causes a problem. So when you have an object and you tend to get false positives, multiple duplicate detections along this ray due to these undesired activation heat map along the ray. So is there a way that we can combine both? And this is our forward-backward design solution. So basically, what we have is that we can use LSS like lift splash shoot, like forward projection to create a feature, to lift the feature into the 3D space while using depths to supervise that. We can collapse those features into a BEV 2D flattened BEV feature and use them as to initialize the learnable queries in the BEV space and back project the queries back to the image feature. So this backward projection part is very similar to BEV former, is using deformable attention and then we can also find a way to combine these voxel representation from the forward projection and also these BEV feature from the backward projection, fuse them together, and then go through an occupancy head to predict the final occupancy. So you can think of this architecture at high level is organic composition of BEV depths and also the BEV former, and finally in the BEV in the BEV space, once you have these fused occupancy, one of the things we do is that we can reduce the resolution at multiple scales to increase the receptive field, and then expand back, and also then finally supervised by the occupancy ground truth. This is the head design. For more details, please refer to the report. So there are, of course, we are since we are participating in a challenge. So besides the model design, there are many things that are important for achieving state-of-the-art performance. So here I'm going to introduce this bag of tricks. Talking about scaling up, we use the intern image H, which contains 1B parameters as the encoder for the image encoder. Turns out this scaling up law applies very well also in the 3D occupancy prediction. But the problem is that once you have 1B parameters, when you apply the training on the new thing, it's very small. The data set contains very little samples. So it's basically an in-domain data. It's not very suitable for large-scale pre-training. So when you do the pre-training, you want to do it on maybe very generalized, like web data with a lot of diversities. So that is why we deploy this pipeline where we start from ImageNet 22K pre-training, and then we next go to 2D detection. We basically train the network using the 2D detection head on object 365. Then we do in-domain pre-training. These in-domain pre-training are depth and semantic segmentation prediction. So for this part, actually, it's interesting. We use the latest we use the latest work from Segment Anything. We use Segment Anything as an auto labeling tool to treat the bounding boxes and also the point cloud as prompts, and use that to auto label the nuisance images. So once you got the segmentation, you can actually use these segmentation as a very strong supervision signal to prevent the overfitting, and together with the depth map here to do the to supervise the backbone as this is shown on the right. And of course, post-processing, I think this part is a little bit less interesting, but since this again, this is a challenge, this is needed. So we have we used temporal test time augmentation. Basically, you have different kinds of perturbation flips, and you ensemble the method, and also temporal TTA, where we consider different frames and aggregate the information along the temporal, and this will refine your final result. The other is ensemble. When we ensemble, we have ensemble from different models. And when we are doing the ensemble, we consider the weight from different categories and different models. For the weights from different categories, they are determined by the IOU of the output from different from the different classes. This is not hand picked. This is actually is determined by the method. The model is validated. The weight of the model is actually searched on the validation set. Okay, so here are the experiment results. So we using these using the bag of tricks and also the model design, we were able to push from the very basic 23% IOU all the way to 42. All these are controlled experiment on the ResNet 50 backbone. And we can see from the curve that several things matters. Depth matters, and actually visible mask matters for a lot for training. So when you are doing the training, don't try to use garbage information, only use information from the visible part. And this is also quite a coincidence with the philosophy of Vox-Former, start from the visible part. And also temporal also seem to help a lot here. So these are the other findings. And we also did some experiment trying to scale up the models, and finally our largest model with more than 1B parameters pushed the performance to over 52% MIOU. And we also did some study like studying these BEV representation. We find that both the BEV and the voxel representation, they together benefit each other and give some performance improvement. And this is the final result. So after using model ensemble and also using all the bag of tricks, we are able to get 54.19% MIOU on the leaderboard, which ranks first among all the submissions. Here are some comparisons between FB OCC, our final solution, compared with the baseline starting from BEV DAT. You can see that on some irregular shaped objects, the prediction gets better. And also we notice some noise in the data set itself, hopefully can provide a useful case study. So the inconsistency between the camera mask and also this GT versus our final prediction, you could see that the prediction here does a pretty reasonable job, but the evaluated MIOU on this one is quite low. So I think there are some inherent noise in the data set as well. And here's a video showing these, I think this will be the last one. It's showing the prediction result. I think still, even though the numbers looks high, but I think there are still pretty much space. I would say this challenge, camera-based occupancy prediction, is a very challenging task, and it has a lot more room to improve. So that's my take from this. We will release also open source the code at the following repo. Thank you all for attending the talk.
Okay, so let's thank Zhibing and also congrats to Zhibing for winning. We have this champion certificate. Okay, so now we will have another 5-minute talk by Director of Huawei Vancouver Research Center, Canada. Yeah, so let's welcome.
Yeah, hello everyone. Dear speakers and fellow researchers. So my name is Mingxue Wang, and I'm the director of the Huawei Vancouver Research Center. So I'm honored to stand here before you today to represent Huawei Technologies. So our company is proud to be a co-organizer of this event alongside other esteemed partners. So together, we have created an exceptional platform for global participants to showcase their technical prowess and advancements in the fields of the autonomous driving. So Huawei is a leading global provider of the ICT infrastructure and smart devices. So we are committed to bringing digital to every person, home, and organization for a fully connected, intelligent world. So in the fields of the communication networks, IT, smart devices, cloud services, intelligent automotive solutions, and the digital power. So we provide customers with competitive, secure, and reliable products and solutions and services. So what people interact with experiences is our products. However, behind these leading products is a solid foundation of basic research and technological innovation. So our ongoing investment into exploration of mathematics, algorithms, chemistry, material science, physics, engineering, standards, and patents drive the competitiveness of our products. So heavy investment into R&D has and will continue to be one of the Huawei's key strategies. So Huawei reinvested at least 10% of the revenue into R&D each year, and over half of our workforce is dedicated to R&D. So by the end of 2022, we had 114,000 R&D employees, accounting for 55.4% of our workforce. So the company has now has more than 80 foundational technology labs and over 170 joint and innovation labs around the world that will establish the AI research center for our mission of the lab is to make significant contribution to both the company and the society by innovating in artificial intelligence, data mining, and related fields. So mainly driven by long-term and big impact projects. Research in the lab also tries to advance the state of the art in the fields of as well as to harness the products and services of the company at each stage of the innovation process. As a world-class research lab, we are pushing the frontier of research and development in all areas that we work in. So we dare to address both the challenges and opportunities in the area of AI and big data to revolutionize the ways in which people think, work, and live, and the ways in which companies to do business through intelligentization of all processes, with the slogan of from big data to deep knowledge. So research areas of the lab mainly include computer vision, natural language processing, search and recommendation, decision and reasoning, and AI theory. So founded in 2012, the lab has now grown to be a research organization with many significant achievements in both academia and industry. So by benchmarking industry thought on research and innovation, our AI academic impact has steadily increased year on year. So the amount of the papers accepted to the top conference is increasing. So the leading positions are achieved in more than 10 international competitions, including autonomous driving, visual and reinforcement learning. So autonomous driving is one of the major research and directions in our lab. So with challenge problems as the traction, so we explore the frontier and make the breakthroughs of crucial components in autonomous driving, such as the perception, cognition, planning and control, simulation, and data mining. So all these innovations will continually support the technical competence and the success of our car business unit. So in addition to our technological expertise, so we value collaboration and knowledge sharing. So we actively engage with research institutions, industry partners, and academic communities to foster ecosystems of innovations. So NASA Act Lab are located in 12 cities around the world. And it is connected to the world's leading innovation resources. By working together, we tackle the most challenging technical problems and propel the industry forward. So in conclusion, I would like to express our gratitude to the organizer of the partners for providing this remarkable platform. So we invite participants to join us in this exciting journey as we revolutionize transportation through autonomous driving technology. Together, let us create a safer, more efficient, and sustainable future for all. Thank you.
Okay, so thanks, Minxue. And finally is kind of sharing of the roundup solutions, right? So for this challenge track, so Zhiding has introduced one of these champion solutions, and now we will have another solution that's from our Fortitude Dog. In this presentation, we would like to introduce a solution for open state prediction training in CVPR 2023. Hello everyone, this is the Fortitude Dog, and my name is Tom. In this presentation, we would like to introduce a solution for open state prediction challenge in CVPR 2023 Autonomous Driving Workshop. The title of my presentation is Real Multitask Learning with Localization, Ambiguity, Suppression for Occupancy Prediction. The task is to predict occupancy state in specific level for it also increase price given multi-view images. A baseline model we first aggregate body will consist of three main components, an image important to extract image features, a view transformer to transform 2D features into 3D features,
and an occupancy encoder to produce occupancy predictions. We propose several improvements on the reservoir. We propose very in-depth multi-class learning for task synergy and strong path to supervision signal for a level component. We propose localization in UAT expression for occupancy prediction refinement. We extend a short spatial period pooling to 3D tasks for better occupancy prediction results. We address data imbalance problem. And finally, we employ other techniques for performance improvement. Perspective semantic supervision is applied into image encoder. In particular, we use a private applicant feature level and build it into two ResNet blocks, followed by a predictor. Since the image level semantic annotations are not available, we project 3D line of point clouds with label into the image to get semantic annotation on the image, which is used to train the semantic branch. Moreover, via perspective semantic supervision, we provide each network component a short path to supervision signal, which help training the network become easier. Occupancy prediction is dense prediction test which requires incorporation of large content. We extend a short spatial pivot pooling for 3D tasks to learn 3D feature with different sampling rate and field view. In addition, we propose localization and ambiguity suppression to define occupancy prediction. Unlike a system, the presence of object can be predicted by detected particles from 2D sensor. In camera system, we need to localize 2D objects from images. This leads to localization ambiguity in distant and small objects. We propose to suppress low confidence prediction using statistical framework. We also address the data imbalance problem. As shown in the figure, the portion of common classes is nearly 10,000 times higher than other rare classes. To address this problem, we employ weighted cross entropy and dice cost. We also employ other common techniques for performance improvements, such as high resolution input, long-term travel, test argumentation, pseudo labeling, and more. For our experiments, we use ResNet 15 as our baseline and training 24 ad hoc. We use 16 GPU I100 to train our model in about 3 days. Here are our experiment results. The baseline model achieved 33.5% MIOU. Here we show performance improvement. We added different components, including perspective semantic supervision, class balance loss, customized architecture, ASPP 3D, high resolution input, long-term temporal, pseudo labeling, test argumentation, localization ambiguity suppression, stronger backbone, and finally is model example. Our final model achieved 52.45% MIOU on test split, and we win 7th place in the occupancy prediction challenge. This is the end of my presentation. More information is available on the technical report. Thank you.
Okay, so let's thank these run-up solutions. And now we will have our next keynote speaker. So it's Patrick Liu from Xiaopeng. So Patrick is the director, principal engineer at Xiaopeng. So he leads several perception teams in San Diego and Silicon Valley in the US and Beijing and Guangzhou in China. Also, he designs, develops, and delivers perception features that kind of enable critical functionalities for X-Pilot, Xiaopeng's autonomous driving solutions. So talk title for Patrick is the practice of mass production, autonomous driving. Okay, so let's welcome Patrick.
Yeah. Sorry about the technical difficulties here. Oh, me. Okay. It's okay. Good to go now?
Yeah.
Okay. Awesome. Yeah. Well, thanks everyone for coming here. I'm Patrick from Expo Motors. And today I'm going to talk about the practice of mass production autonomous driving in China. For those who are not familiar with us, Expo Motors is a electrical vehicle manufacturer. We firmly believe the great potential that autonomous driving would bring to the human society. So since the very creation of the company, bringing cost-effective autonomous driving solution to the market has been at the core of our business strategy. And what is shown here is the lineup of our vehicles in production. And at the center of it is Xpeng G6, our latest release. It is a compact SUV. And we are a public traded company in both the New York and Hong Kong exchanges. Autonomous driving is a challenging task, and even more so in China. And China is perhaps one of the places that are most challenging even for a human driver, let alone autonomous vehicles. And we can take a look at this from three different perspectives. First of all, for dynamic objects, and the second is a static road topology. And the third, we have a bit of a difference. Sorry, just give me a second. Try to. And third, it's a little bit hybrid. We have a traffic signal because traffic signals, they're typically static in geometry, but dynamic in semantics. And I will quickly overview the dynamic and static challenges, and we will do a deep dive in the corner cases of the traffic signal. So for dynamic objects, and especially for VRUs or vulnerable road users, they can take on a variety of different shapes and poses, and they appear at places where we don't typically. For human to figure out what's really going on. Actually, it's a vehicle fully loaded with tree branches. For a static road topology, this is also my favorite image of a static road structure.
And this intersection really took the road design to extreme. It's almost look like a screenshot from a sci-fi movie, but actually it's a real place where we can observe from Google Earth. If we zoom in a little bit, we will see there is a piece of interesting road elements, and that is perhaps unique in China. It is a left turn waiting area. And they are initially designed to increase the left turn traffic throughput at intersection, allowing more cars to go through the intersection within one cycle of traffic lights. And you can even find academic papers about it, about its design and about its effectiveness. But it's also very obvious that this could cause confusion for even novice human drivers and let alone autonomous vehicles. And turning left at such an intersection involves a two-step process, and both involves some traffic light pattern shown here, and which requires some high-level understanding of the semantic meaning of traffic light or traffic lights. And I'm only showing the very typical traffic light pattern here, but they could be more complex, and sometimes even involving traffic lights that are specially designed for this left turn waiting area, which we will see later. Now let's take a deep dive into the traffic light. As we mentioned, the traffic lights, they are a bit different. They pose their own challenges because they are static in geometry, but dynamic in semantics. The recognition of traffic lights are challenging for two different reasons. And first of all, we have to recognize all the traffic lights in the sensor data. For example, here, if my human object detector is correct, we have 6 different traffic lights here. And second, out of all the traffic lights, we have to figure out which traffic light we should really pay attention to. This requires the correct matching between the traffic light to the traffic lanes. And also here we see a special type of traffic light. If you look at the left part of the image, it is a traffic light specially designed for buses. And we have to correctly recognize them for 2 different reasons. First of all, for the autonomous driving vehicle, because we are not a bus, we need to correctly identify it in order to ignore it correctly, because sometimes it may carry information that are conflicting to the traffic light that we should really pay attention to. And second, if there is really a bus nearby and we want to predict its maneuver, then we need to match the traffic light status to that bus correctly. And traffic light for buses, they may take on a variety of different forms. And here's some interesting examples. First of all, they can have different LED letters, the BRT, bus, SRT, or even simply a letter B. And of course, they can take on a variety of different Chinese characters. And they could also feature a little cute icon of a bus profile. And last but not least, we have traffic sign modifiers that are associated with these traffic lights. And for these ones, we have to identify both the traffic light and also the modifiers in order to correctly match them together to make the semantic mapping. And here is another complex example. It's a multi-bulb. Typically, for traffic lights you see on the road, you have a 1x3 or 3x1 traffic light, and only one light bulb would light up at one time. And for special cases like this, you will have multiple bulbs functioning at the same time. And for these, we have to correctly figure out the location and semantic meaning of each light bulb individually. And here is another example. But here, in addition to this little building in the middle of the intersection, that's interesting. We also see additional numbers here. They are countdown timers before the next color change. And typically in North America, we will see these countdown timers a lot for traffic signals that are designed for pedestrians on crossroads. But these are actually for vehicles. These timer information, if used correctly, they can really improve the smoothness of the ride. And these are some corner cases of different formats of countdown timers. They could be on standard display, such as the first one, and they could also be integrated with the rest of the traffic light. For the first one, we have to detect both and matching them together. The display format could be different, could be having a leading zero, such as 02 shown here, or simply a letter, simply a single digit 2. And they could have different fonts, some of them more artistic than the others. Last, we can also have countdown timers in the format of a progress bar. And typically this is the animation with the progress bar become shorter and shorter before they change to a full progress bar of a different color. And this could easily win the most innovative award for traffic light. But you can imagine this is a nightmare for perception engineers. And the last, we talked about the left turn waiting area earlier. And here are also some different formats of them. They could be in 2 different large categories. For the icon ones, these are typically also an animation where the lights gradually light up, guiding the vehicle to that waiting area. They could also be on text form. Some of them are in LED displays or in printed traffic signs. And there is no standard pattern of the text either. So in order to do this correctly, you have to do OCR and a bit of natural language processing to extract the exact semantic meaning. So despite these challenges, we still managed to deliver the best-in-class autonomous driving solution in China in mass production. And what is shown here in the SR display or surround reality display here is the perception results from our onboard platform. And we can see we can detect a variety of different 3D objects. And we can also detect some of them. We can also detect the other semantic features in detail, such as turn signal light, if you pay close attention to it on the left-hand side. And for static road elements, we see the road boundaries in red and also the driver space in gray. And note that this is not a demo video. This is actually a recording from a couple of days ago on one of our mass-produced vehicles without any aftermarket modification. I would like to highlight several milestones in the development of XPeng's autonomous driving solution. So over the past 2 to 3 years, we have released, we are the first in China to release a highway pilot system, the highway NGP or navigation guided pilot, and also the valet parking solution, VPA, and the urban driving solution, City NGP. And very recently, we started releasing City NGP to Beijing, so it's covering all 4 top-tier cities in China now. Note that these solutions basically sets the product experience standard for autonomous driving in mass production in China, and really cements the leading position of XPeng in this field. Note that all these 3 solutions I mentioned about are single stack solutions, meaning that depending on where you are on the highway, in the city, or in the parking lot, the underlying technical stack is different. Earlier this year in 2023, we started releasing the first version of our single stack solution, XNGP. It is built upon our next generation BEV or bird's eye view perception architecture. So both the BEV architecture and also the single stack solution it powers are some of the efforts we do at XPeng in order to achieve end-to-end autonomous driving solution. But before we dive into the details of XNGP, why do we need end-to-end in the first place? So here I'm drawing a little bit curve here, and in order for any practical engineering problem, in order to get to a solution fast, we typically have to do divide and conquer. That means we break a problem into smaller pieces until they are relatively well defined and easy to solve. The problem with this is that the more components you break the problem into, the more likely you'll get stuck with the local optimum. This is also echoed by the 80-20 rule, meaning that you can get to 80% of the performance with about 20% of the effort. So the benefit of divide and conquer is that you can get to a practical solution fast with about 20% of the efforts, but then you get stuck with the 80% performance ceiling. In order to get out of the local optimum and break the performance ceiling, we typically have to consider multiple components together and jointly optimize them. And we do this again and again, breaking performance barriers again and again before until we reach an optimal solution. So the final curve of technology evolution looks like a series of sigmoids that stack on top of each other until we reach the end-to-end and global optimum. There is another aspect of this, in order to get the 20%, the last 20% of the performance, we have to invest a lot more efforts. So bear in mind that all of us who gathered here in this end-to-end workshop are perfectionists who are not willing to give up the last bit of 20% performance, despite the fact that we might invest more efforts into this. So in a classical autonomous driving stack, 2D images are fed into perception module, and they would generate 2D results from multiple single cameras. And these results are passed down to a module called sensor fusion. And sensor fusion module reasons between all these 2D results and lifts them to 3D. And the 3D results are then passed down to downstream modules such as prediction and planning to generate the optimal control for the ego vehicle. Single cameras typically only contain partially the information of the objects and the environment we really care about. So binding them together requires a very careful adjustment of the fusion logic. And we have a lot of brilliant sensor fusion engineers working at this hard problem at XBone. Essentially, we are doing backpropagation through engineers' head. And this sets of logic very hard to create and maintain, and sometimes they even fail at very complex urban environment. So alternatively, we could also resort to this BEV perception paradigm, which combines the two components together and greatly simplifies the fusion logic. And at XPone, our BEV architecture, we name it XNet. And XNet is essentially our first attempt toward this end-to-end perception stack. Here on the demo video on the right, the little red car in the middle is our ego vehicle and is going through an intersection. And we can see we can detect the 3D environments and both the static and dynamic very accurately around the ego vehicle. We started experimenting with BEV architecture about 2 years ago, the same time that academia picked interest in this area. And after many iterations, we finally settled on the architecture on the left. So we extract image features from multiple cameras with conventional convolutional neural network, CNN backbones, to get multi-scale image features. And then these image features are then lifted to BEV space through a view transformer. In particular, it's actually a cross-attention module. And the multiple features from multiple timestamps of this BEV space are then fused together with the help of ego pose to both spatially and temporally to get to this final fused feature. These fused features are then decoded into dynamic objects and static environments. The XNet is not only our first attempt to the end-to-end perception, but also it gives great promises to reduce the hardware cost and promotes the mass production of autonomous driving. The great ability to detect to sense the static environment actually reduces the necessity to have a HD map. So both of these measures actually greatly reduces the cost and also ensure the high performance of the autonomous driving solution. in the training and deployment of such big model, there are multiple challenges. So first of all, in order to train such a big network, we need millions of multi-camera video clips, and they involve billions of objects to be annotated. And we did a quick calculation based on our human annotation efficiency. This will take about 2,000 human years. For our internal annotation team, which has about 1,000 people, this will take more than 2 years to finish, and which is obviously not acceptable. To train such a network, it would take about a year to do that on a single machine. And if we deploy this onto the NVIDIA Orin platform, which we have at hand, without any optimization, it would take about 122% of the GPU power. So we won't even be able to fit it onto one unit. To boost the annotation efficiency, we came up with our auto label system, which greatly increases the annotation efficiency. This reduces what used to take about 2,000 human years, right now only a little bit under 17 days. And on the left, we show some inner workings of the pipeline, and it's essentially an offline sensor fusion system. And on the right, you see this demo. And note that this pipeline is actually heavily based on LiDAR. And we also have a separate pipeline that are more vision-centric. And that vision-centric auto pipeline enables us to annotate video clips that are harvested from a customer fleet. This is super critical as it forms a data closed loop and ensure that we have a self-evolving perception system. And moving on to the model training. Initially, we said it'll take about 300 days to train this. So we optimized the large-scale model training from 2 different perspectives. First, we optimized the training scheme, and we did a lot of optimization work on a single node, on a single machine, such as the mixed precision training, and also some optimization of low-level operators that are hard to run or inefficient to run on the GPU. And second, we collaborated with Ali Cloud and built a GPU cluster with about 600 petaflops of computing power. And then we scale our training from one node to multiple nodes. With both of these efforts, we were able to boost the training efficiency about 600 times. Now we can cut down what used to require about a year down to only 11 hours. Note that as we add more data, we harvest more data from customer fleet, we add them to the training data set. So this number keeps increasing. So the optimization is actually an ongoing effort to make sure that we have we keep this under control. And finally, I think there was earlier there was an audience asking about the deployment of transformers. We were also faced with the same problem. If you look at the initial chart, profiling chart at the top, what is taking up the 122% of the Orin GPU power is actually the transformer module. In order to do this, in order to deploy this transformer more efficiently on the Orin platform, we completely rewrote the attention mechanism, and we were able to get about 3 times the speed up. Note that this co-design of hardware and software is super critical. But so far for us, we have to really optimize on the Orin, NVIDIA Orin platform. And then we ask ourselves, can we do better? So we did a pruning of the backbone, which achieved another about 2.6 times of speed up. And finally, by load balancing between GPU and the CPU, we were able to squeeze a little bit more out of the computing device. So what used to take about 122%, now we can finish that with only 9% of the computing power. And this gives enough headroom for us on the Orin platform to try out different architectures for different use cases. And now we have this XNet architecture in place. We're ready to boost the performance by data iteration by building this data engine. So corner cases are first identified on the vehicle then configurable triggers are deployed to our customer fleet to harvest relevant data. And in the cloud, we do image retrieval, either based on image patches or based on the text in natural languages. So here we are able to actually tap into the recent progress of large foundation models, large language models, to really boost the efficiency of data curation and also data annotation. So with both the XNet architecture and also the data engine, we are able to build a scalable and self-evolving perception system. And finally, before we conclude, finally, we are about to release Highway NGP 2.0. And this is a single stack solution for both the highway and in the city. This allows us to put whatever what we developed in the complex city scenario onto the highway and improve the user experience. And essentially, we're powering point-to-point user experience with end-to-end technology. And our vision is to build a single stack end-to-end solution that can power autonomous driving for all scenarios. And if this vision excites you, please consider joining us. We have multiple available positions in Silicon Valley and San Diego and back in China. Thank you very much for your attention.
Question from the audience?
So I have a few questions, but I'll just ask two. Could you talk about the ways in which you use bird's eye view modeling in your stack, the different tasks where it shows that you get improvements when you use bird's eye view. Some of them you can only do in the bird's eye view, of course. And the second question is you mentioned the transformers. So this is both the view transformer and the transformer. I'm reckoning the.
It is it's the pun not intended, but yeah, it actually acts as both.
Did you consider the ray casting based architectures that start and shoot those transformers, and why you went for one over the other?
Sure. Sorry, I didn't get your first question. What was the first question?
I mean, an overview of what the applications of the bird's eye view modeling is, like for lane tasks and 3D bounding box detection. It was there in your slides, but
right.
Perhaps more concrete.
Oh, okay. Sure. Yeah. Well,
thanks.
No worries. Thank you for your question. Yeah, we use BEV architecture for right now. We're only for doing dynamic objects and static environments, because currently we do have lidars on our cars. For general obstacle detection, we use the lidars. So I guess that answers your first question. Yeah. Okay. And the second is that for the transformers, yes, we use the cross attention module to lift the images from image feature from image space to BEV space. So we actually tried different varieties of transformers, and even before transformers, we also used to use MLP. I think one of the winning solution used that. With MLP, I think is relatively deployment friendly for hardware. And we also tried lift splash shoot. But at that, I know right now, I think there are some deployment ready solutions for lift splash shoot. But at that time, this is about 2 years ago. At that time, we did try both, and I guess we picked a transformer-based architecture for 2 different reasons. First, transformer-based architecture. At that time we thought, and through ablation study, it gave us better results. And the second, we have 2 different teams working on this deployment problem, and we finally cracked the problem of how to deploy transformers onto the device, and how to deploy lift splash shoot on on NVIDIA platform at that time was not very clear to us. That's right. That's right. I think there's called BV pool V2 or something. Yes, that you can use. I think the one of the lessons we learned is that the architecture perhaps is okay as long as does not have any information bottleneck in it. What's really driving the performance is a large scale training and large scale annotation, and also the data closed loop through the data engine.
Yeah, thanks for the talk. It's very impressive. And I have two questions.
Mm-hmm.
The first question is that you mentioned about the auto labeling system, right? It's very good, but from my understanding, you are kind of labeling the other objects or lanes, something like that, with a larger multimodal network, right? Is my understanding correct?
Actually, yeah, here I'm only showing the auto labeling for dynamic objects. For static objects, actually, we do reconstruction of the scene and then we label on top of it.
Okay, great. But if you have some minor issues with the larger program, how do you fix that? That's my first question.
With what? Sorry.
Like some missing objects or some misdetections.
Oh, misdetection. I see. Yeah. Well, because this is an offline system, you can first of all you can do tracking, right? Non-causal tracking. Because you can leverage the power of hindsight. You can see the future, and typically, what used to be an extrapolation or filtering problem now becomes an interpolation problem. Becomes much easier. And the second, you can leverage multiple different models, offline models. Essentially, you're doing an ensemble of different models, and that can also helps with the quality control. And finally, here we also have what's not shown here is we also have a auto QA process and always coupled with a human QA process. So the quality assurance is super important for this application.
Okay, thank you so much.
Yeah, thank you.
And the second question is kind of more high level. Is that how much do we like to push the end-to-end autonomous driving to? I see from your slides that the end-to-end you mentioned is mostly focused on the BEV part, right? But for the planning part, you hardly touch that. But I see that's a very important part of the XPerm autonomous driving. And I have actually tried that by myself. So how do you think of that?
Yeah, that's a very interesting question. I think for now, yes, we're pretty much limited the BEV or the end-to-end solution to both the perception and prediction. For planning, in my opinion, I think it's still pretty much an open research problem. We haven't converged the two. What's the practice, the interest, the researchers from academia and industry. I think they're trying different ways, and we internally are also trying actually. And in my opinion, I think this is a very promising field. This is the last piece in order to get to this end-to-end solution, right? So to make it end-to-end differentiable. Yes, I'll be able to, I'll be glad to talk to you after this.
Thank you so much.
Very much for your presentation. I have a question. Are you using HD maps?
We do.
Okay. And if so, are you doing some change detection of the maps? Are you updating the maps to keep them fresh?
That's right. That's right. Yes, that's a very sharp question. Yes, especially in China, construction is working, is undergoing every single day. This is, we have a dedicated team internally to work on that problem. And also, this is one limitation, I think one limitation or constraint of HD map, not only the cost for each car, you have to pay some fee, and for how to maintain the freshness of the map is also a very challenging problem. And in order to detect and also to maintain this map up to date, I think BEV perception we just mentioned here, it would be a very promising solution, and we are working on that. don't have a very good answer to that. We're also exploring the possibilities, from perception and to even to prediction and to planning. There are multiple ways I think the perception system can output the uncertainty. For example, temporal uncertainty is one thing, and that is typically handled by sensor fusion. When you do some tracking, you see the tracks when they get unstable. That's one great hint that the perception quality might be subpar. And also, of course, there are some deep learning based methods you can directly output uncertainty as well. Aleatoric and epistemic uncertainties, if you know about these papers. Yeah. I think these are the two approaches that you can propagate these uncertainties for downstream to handle.
Thank you so much.
Yeah, thank you.
Thank you so much for this informative and presentation.
Thank you.
And I actually have two quick questions. So the first one is, according to the architecture you're picture on the left side of X9, it shows like the input only cameras. Did you use any other types of modality inside the X9 itself? And my second question is that it would be great if you could give us some insights about, how to orchestrate different kinds of modalities like camera, lidars, and how to, leverage the pros between different types of modalities.
I see. Well, for the second, I'll perhaps answer the second question first. Think, camera and lidars and also radars, they have their distinct advantages, right? To me and internally, we really think that the correct usage of lidar, maybe I'm biased, is actually detection of general obstacles, right? For the objects that are not on the whitelist. For example, the car I showed with a lot of luggages on this, it's maybe really challenging for the 3D object detectors to pick them up. So that's really the use case, a really good use case of lidars. That's how we are using it internally. And the second, to answer your first question, is we actually only use cameras. It's a vision-centric system. The reason is that for all the other sensors, they are still rapidly evolving. For example, 4D radars, right? And also the radars, they keeps changing. The firmware also keeps updating. And also for the lidars in the industry is still rapidly evolving as well. The cost is coming down year on year. So we don't want to, if we fix them right now and into an early fusion stack, that solution will not be as scalable as of what we do now. We do a vision centric, or we do early fusion between multiple cameras, and then late fusion with the rest of the sensors.
Thank you so much.
Thank you.
Hi, thank you so much for the talk. I had a question on the data engine part. So you mentioned that you do text to image and image to image search. Can you describe, that process a little bit more? And do you retrain whatever model you use for this, for specifically the self-driving case?
I see. That's a good question. I think for now, the quick question is that right now we don't. We just use them as off-the-shelf tools to do that. And that's already enables us to do a lot of useful things. And I think fine-tuning them for our specific use case, especially our images may look a little bit different from the images on the web. I think that would be a very interesting direction to explore. Yeah, thank you for a suggestion.
Thank you.
Okay, so let's send Patrick.
Thank you.
Okay, so the final session for this morning session of the workshop will be the Open Land Topology Challenge. So it will be a challenge track, will be hosted by Lu Tian Tang. So welcome.
Okay. Hello, everyone. I'm Tu Tian from Shanghai AI Laboratory. I'm so glad to be here to present you the details regarding the open lane topology challenge. Apart from detection, understanding road topology is also crucial for autonomous vehicles. Apart from the ground line lane markings, the traffic elements such as road signs and traffic lights also affect lane possibility and road topology. Taken imports from surrounding multi-view images, the aim of this challenge is to predict the 3D centerline as the lane representation, detect traffic elements to enable vehicles to correctly recognize the possibility of lanes and establish relationships between lanes and traffic elements. Furthermore, we have focused on the topology among lanes and the relationship between lanes and traffic elements. The inspiration for this challenge comes from the road detection community. In the early years, people detected lane lines on 2D images and projected the detection results into 3D space based on the flat ground assumption through IPM. However, since the flat ground assumption does not always stand, lane detection errors usually increase with distance on unflat grounds. In 2022, we proposed OpenLane V1, the first large-scale 3D lane dataset in the world, with a large amount of high-quality lane line annotations, setting off a new trend for 3D lane line detection in the community. Meanwhile, other aspects were also emphasized, such as the HD map elements, the connectivity of center lines, and binding traffic lights to lanes. Among those active community works, we pondered for a comprehensive understanding of 3D road structure. We need a unified road topology representation in one dataset. Therefore, we proposed OpenLane V2. It is a perception and reasoning benchmark for road scene structure, first in the world. It boasts 2,000 scenes, 2.1 million instance level annotations, and 1.9 million positive topology relationships. In OpenLane V2, high-quality traffic elements annotations are accurately linked with lane centerlines. Both centerlines and traffic elements have temporal tracking information, and the topology information is updated in real time as the vehicle moving. To thoroughly evaluate road structure recognition performance under such complex circumstances, we have designed a brand new set of evaluation metrics. First, the detection score for lanes, usually the threshold distance to evaluate the detection of directed centerlines. Second, detection score for traffic elements, employing a multi-class IOU-based MAP. Third, and a topology score among lane centerlines and between the lane centerlines and the traffic elements. The final OpenLane score is a weighted sum of these four metrics. This score also serves as the main metric for this competition. OpenLane V2 as a newly introduced task has gained widespread attention. Participants ranging from academy and industry, representing 4 countries, form a diverse group of 34 teams with over 700 submissions. A large and solid improvement is made by the outstanding champion, 20% higher on OLS than TopoNet, which is a newly proposed strong baseline, specially designed for this task. We now come to one of the most awaited moments. We will have the award announcement and follow up by a presentation by each awarded team. The Innovation Award of OpenLane Topology Challenge goes to the team of Flatpers Whispers, and the authors are from Middle East Technical University, Turkey. Congratulations. And then we will have the Whispers team to present their method. They will be in the Zoom conference. Hello, let's welcome the team whispers.
Hello, we have decided that we can play the video recording that we have sent to us, but if you want to record present, then we can step in.
Sorry?
We can play the video, but if you want to present for us, you can present.
Oh, it's up to you. I can either play the video or you can just
Yeah,
the presentation.
it's okay. But if there is any question and answer, we can step in and answer if there is.
Okay. I will play the video then. Okay.
Thank you so much.
Okay, it's
Hello everyone, I am Scalpo and our team in the challenges related to Swifters, and our valuable members of the team are Ali Ibrahim, Professor Kılıç, and Professor Dr. Altıgin Temzel. And our study is TOPAMAS, which is instant math-based formulation for the road topology problem via transform-based architecture. So as a methodology, we have proposed instance math-based methodology with quasi-label direction representation, which is denoted as up, down, left, and right. And up means actually down to up, and down means actually up to down. So which is shown also in the figure 1. And as you can see, the semantic is shown in this figure, and with the following figures, the instances for every quasi-label direction is shown. So there is 2 main reasons for utilizing quasi-label direction representation. The first reason is that we have to convert every mask instance into the point citation. So in order to convert it, we have followed row and columnized expectation. What I mean is that for up and down directions in here, we have taken the row-wise expectation, and for the left and right direction representation, we have taken the column-wise expectation. So this is the first reason. And the second reason in utilizing the quasi-label direction representation is that even if we have obtained the point set, we don't have a flow information. It can be mixed, for example. So in order to obtain the flow information, we have utilized to enrich the point set with order information. So as you can see, the figure 2 shows the overview of the TOPAMAS architecture. The crucial point is that after obtaining the bare feature, it's treated as if like to the perspective feature and given directly to the mask transformer architecture, and this branches the traffic element queries and its relation to the object detection transform base. And queries are assumed to be embeddings of the traffic element as lane center lines. So for the metrics, for the detection of the center line, the mean average precision, but based upon the Frechet distance, is utilized actually. So the Frechet distance is basically placed in proportions to the flow information. This is the crucial part, and for the detection of traffic elements, basically the IO-based mean average precision is utilized. For the reasoning part, the important point is that we need to detect both the vertices and the edge between the vertices. This is the important point. And for the OLS score, the average distance, the only not the only, but the Shanghai distance does not place importance to the flow information. So just the the precision of the points is important, but the flow is not important. The pi is also similar, but it's not a mean average precision-based method. So when we are comparing it with the current state of our TOPAMAS architecture, even if the pressure-based mean average precision is the same, there is a significant increase in the Shanghai distance-based mean average image prediction performance. We have also seen that our advanced score is compared to the high with respect to the actual threshold distance-based mean average precision compared to the other teams. And F1 is similar to the Chamfer because it doesn't consider the flow information issue. So we have also compared with the Bayesian representation, our mask formulation, and it's superior over the Bayesian representation. And we have also developed some fusion strategy between them, and we have found a rule-based strategy that the OLS score might be better with this fusion compared to the mask. It's some conflicts actually. So we have also attempted to challenge with the fusion strategy actually. So that's it. Thank you for listening. If there are any questions, I will be glad to answer these.
Okay, thank you, the Whispers team. The honorable runner-up of the Open Lane Topology Challenge goes to the team of victory from Advanced Micro Devices. Congratulations. And then we'll have the team victory to present their method.
Hello. It's a great honor to have the opportunity to participate in the Autonomous Driving Challenge for CVPR 2023 workshop and share our MD solution. The name of our method is called separated lower top of one. In this video, we will introduce the details of our method. This is the overall framework of our method, which is an end-to-end neural network with separating architecture and serves 4 tasks simultaneously. The overall framework of our method is inspired by LoGNL, which is an end-to-end neural network. Unlike LoGNL, we apply a separated architecture. A BE and PV branch with modular backbones and a separated machine. We solve the 4 subtasks simultaneously. For lens center line detection, we use 3 small as backbone and apply BE formula to transform the HAB. A deformable TPR head with hierarchical query is utilized to predict 3D lanes. For traffic element detection, we use genome method to detect targets. For 2 topology prediction tasks, we follow STSU solution. In particular to LCRC topology prediction, we introduce a geometric clues to promote the prediction. 3D sample line detection. We design 2 kinds of queries, point query and instance query. They are first passed through a self-attention model to monitor interaction between queries. Then a point pooling model is proposed to get a global vision across point queries. We utilize summation operation to close the point queries. Finally, the LC query is obtained by adding each distant query to the broader point query. There are two kinds of center lines, normal center lines and connecting lines in the intersection. In case of normal center lines, connecting lines in the intersection are more related to the overall structure of the road and less related to the local textural features. Therefore, we distinguish these two categories in the classification head of the LC head. Instead of representing the 3D line and 5 Gazelle control points like STSU, we directly model the 3D line and 11 equally spaced key points in its skeleton. We find this simple representation is surprisingly better than the Gazelle curve. On this page, we summarize our major traits with this. First, we develop different models and chains through the main detector only. This strategy enables each model to perform unnoticed and avoids the impact between different tasks. Second, we utilize three small points instead of the less than 50. Third, we use 11 points representation instead of the zero curve. Fourth, we apply the identical query structure to promote feature learning. Finally, we utilize intersection sensitive head to distinguish two kinds of segments. The following table demonstrates the improved effect of the dial structures. For traffic element detection, we utilize 3 small as our backbone and Dino as detection head. Also, we use a covered chaining strategy and chain traffic element detector only. Unlike 3D centerline detection, we keep the original size of the function. The following table demonstrates how we improve the performance through the traffic element detection. For the topology prediction, we find the performance of the topology prediction is highly related to the performance of LC and T detectors. With better detectors, the topology predictors perform better without fine-tuning the whole. Especially for LCLC topology prediction, we introduce geometric components to assist you in predicting the topological relationship between n lines. First, we concatenate the LC query with its start and end point. Second, any two lines whose start and end points are less than 3 meters apart is considered to have a topological relationship. The two tables below demonstrate the performance of the two topology prediction tasks. Performance of OpenNV2 validation and test set are demonstrated in the following tables. On the validation set, we achieve around 53.57% OLPs. On the test set, we achieve 44.56% OLPs. With this result, we have to obtain the ongoing. Thank you for your attention.
Okay, let's thank the team victory from AMD. And the outstanding champion of the Open Line Topology Challenge goes to the team of MFV from Beijing Institute of Technology, MAGB Technology, University of Science and Technology of China, and the University of Hong Kong. Congratulations to the winners. And now the team MFV authors will present their work.
we developed a positive framework for high performance. I always use our ground systems, including personal selection, total environment, and requirement results. Open learning topology is to understand the structure of the traits by considering the relationship between the entities, such as traffic elements and lines. The detailed concept of 2000 allocated road sensors that describe traffic elements and their relationship to the lines. It has 4 subtasks, including the 3D interline detection, the 2D traffic element detection, the topology relationship between traffic elements and the 3D line, and the topology relationship between different 3D lines. The exploration of topology relationship is built upon central detection and traffic element detection. Therefore, the selection of these lines for central detection and the traffic elements detection becomes even more important. Different from previous 3D line detection tasks, 3D center line overlap geometrical features within images. The detection of 3D center line rely on surrounding 3D lines. Therefore, a larger receptive field is needed for center line detection. Therefore, we choose PTRV2 on our baseline from many excellent 3D line detection frameworks. As shown in this figure, the line pairs within PTRV2 which activates the image features through global attention. The sizing of global receptive field. The detection of traffic is also important. Taking account of previous computation dependencies, we use the latest Euro series model image as our baseline. Compared to other 2D detection methods, they have faster speed and more accurate performance. By integrating Euro V8 and PTRV2, we have constructed a multi-stage framework and extended it into the prediction of topology relationship. Initially, operation the Euro V8 model is used to generate the 2D detail object pairs. Then the 3D line pairs are fed into the PTRV2 height to produce 3D center lines. This design aims to maximize the performance of 2D detection while aligning traffic features with line features. Based on the features from both tasks, we compact the corresponding features and use 2 MRPs to predict their topology relationship. The positions with topology relationships are assigned a level of 1, while those results are assigned 0. Finally, factor loss is used for revision. In addition to the overall framework, we have made several modifications for each subtask as well. For the center line detection, we have transformed the on the data set. As shown in the figure, green boxes are from truth, while red boxes are predicting results. We found that in some rooms within the data set, some targets may not be labeled in the former frame, but labeled in the later frame. This phenomenon of missing annotations and impact the training process of the model. Additionally, The data set shows class imbalance issue. Therefore, in training neural weights, we employ the central modifications such as class balance thinking and using pseudo labels. Following relation studies and detailed environment results. Regarding land detection, increasing the scale of backlog leads to an improvement of model performance. Especially, VLT achieves a 10% improvement compared to S9 Moreover, extending the training direction had an additional 6% improvement. While using PDA augmentation contributes a 1% increase. Here is the population study for traffic detection. Lastly, we have shown the results of topology relationships under varying land and traffic detection performance. The performance of topology relationship will improve the performance of both tasks as the task increases. In the test leaderboard, we achieve the first performance. So testing the second place by 8 points. That's all my talk. Thanks for listening.
Okay, let's thank Team MFV for their presentation. And I'm very glad to tell you that it's the end of our morning session. So have a nice meal. And please come back by 1:30 p.m. if you are still interested. That's when our afternoon session will begin. Oh, thank you, guys.
Okay. 要停一下，或者我这个人做出来的，我进来了，然后我这个里边的。
So if I, yeah, no, should that like bounce up? Or you can actually check the participants. Hello. Okay, it is going through.
Yeah. Okay.
Okay. But I don't know if this audio is.
Let me have a try.
Okay, my colleague said it's okay. My colleague, even the video. Yes.
陈丽，你能听到那个视频的声音吗？就现在有一个背景视频在放。
Actually, I can. I can't. I can't hear the audio.
Oh, okay. So you can write yes.
I can't. I mean,
Okay.
I can't.
Oh, so far so good.
Wow, that was a lot simpler than I expected. Let me just test the other video. Oh my God, that's too soon. Okay, how do
I can only hear your voice. I mean.
Sorry, I think we may check again the audio.
Why?
Oh, it's the toolbar is cut off.
You're right.
So, oh my God, how do I even?
And I think we might yes at maximum.
Okay. This video is not quieter than the first My colleagues they can hear it, but it's not very clear. The voice is too low. Too loud. Too low. Does this change anything by the way?
Are you Ken?
Yes.
I'm Ihan.
Oh, nice to meet you.
Nice to meet you.
We're actually like going
Yeah,
through
yeah,
some. Yes.
Slides, yeah.
We can go through some of your slides now if you want, but we're just testing the audio now.
Okay, okay.
Hello. So this is still going through just fine. Like, I don't know if it's still, is it picking me up? Like when I speak from here?
Your voice is okay, but I think the audio in the video
Oh, okay.
cannot be heard.
But how did he hear the first video?
He can hear, but not very clear.
Oh, but now he cannot hear at all.
He can hear the voice of the microphone, but he can't. He can't hear the audio in the video. You can hear a little bit, but not very clear.
Let's try again. Oh, now there's no sound. Oh, that was bad. Yes, it's the audio. Oh, here, output should be.
With prediction for the input feature. We use vectorized map representation.
But I feel like this only affects this, like this going to Zoom. There's nothing we can maybe it's here. No, but this goes directly to Zoom.
For more detail, I recommend referring to the original reformat.
I don't know how it's.
To improve closed-loop performance, data augmentation is important. Generally, the newly generated trajectory include past and current states that demonstrate how the algorithm reached the deviated position, and future states that indicate how to go back to the expert trajectory.
Okay, I think it's
The past and current.
Oh, okay. So I think it's this one. This one we need to go a little bit.
So this.
For generating future trajectory, we try two methods. One is generating a smooth trajectory.
We just have to hear. No, so we can hear.
Recording in progress.
Oh, has there been a Whoops. That's not progress.
Let's check the good.
No, we can't hear. Let's try the audio. This is the audio of the video. And I got 10 minutes off from this.
Turn on my phone. Mute.
Oh, I think
Oh my God.
Wait.
Wait,
No.
Hello.
I know.
Yes. Okay, all right. Okay. And then after this. Can you hear it?
Oh, it's not very
However, does not follow the current trajectory.
My colleagues said it's okay. Just like this, we turn this all the way. We can only just relate it.
Is it possible that the audio from the PC does not the Zoom can directly pass the audio on the PC the directions usually without those headphone.
It doesn't, but it works. Yeah, for example, if I was doing a Zoom call, right? Just with is this working? Okay. But if I was just doing a Zoom call, then the audio doesn't go from the speaker back into the mic, right? It just goes directly.
Yeah, normally it should be. No? And normally if I'm doing a Zoom call, there's no setup.
Yeah,
at all.
So now we found
Yeah, so it works then.
So that's correct account. So let me just, I'll just take a picture.
So yes, there is an old saying goes that if something works, do not change it.
Yeah, I want to take this. All there's one more setting, but basically, does this make a difference? Oh, scary.
Hello, everyone. I'm Stuart.
Oh, that's clear.
Autonomous driving company.
The audio in this room is always clear, but it's not I think there's not much to confuse.
First, let me introduce our model, which is largely based on the CVPR waveform method with predictions. For the input function, we use vectorized mapping.
Okay, that's both of you. We need to share another slide. Oh, the quick. Oh, okay. Yeah, I can do the theory. 你来做。Yes. Again, this is the auto track, 1, 2, 3, 4, 5. And then share my screen. 1, 2, 3, 4, 5. Okay. OK。你没有 PPT 要放，你有 PPT 要放。那不重要，然后我们就第一位讲的这个。
All right, welcome back, everyone. So my name is Shen Long from UIOC. I'm the host for this afternoon session and also moderator for the panel discussions. So in the afternoon session, we're excited to have a few, very exciting, research talk, and starting from Dr. Jose Alvarez. Jose is a senior research manager from NVIDIA. He leads the autonomous vehicle perception research team. His groups focus on, scaling up deep learning for autonomous vehicles, spanning efficient and data-centric deep learning, 3D computer vision, and self-supervised learning. And Jose's talk's title is Camera-Based Perception for Autonomous Vehicle, from Data Collections to Network Robustness. Let's welcome Dr. Jose.
Thank you. And this. Well, thank you. Do you hear me well? Yeah, I guess so. And is it visible there? Yes. Okay, yeah, thanks for the nice introduction. So Jose here, and as was said, I lead a applied research team at NVIDIA, where we are focused mostly on resource efficient for AV. And in that setting, we have two branches, compute efficiency and data efficient deep learning. The team sits between fundamental research and the product itself. So it's quite exciting to be there to be able to transfer research results into product, which is the real challenge, right? Today, I'm going to talk about mostly two things, but I'm going to share some of the challenges that we are encountering. The title of the workshop is New Tasks and Challenges. So I thought it would be nicer to see more than what we have done, what we are working on, and what we think are the next key challenges that we should be working on. In that space, I will touch quickly on the camera-based 3D perception, and then I will focus more on the data side and something on the robustness of the neural networks. About the perception pipeline, I think for all of us, it's quite obvious that this is what we see these days in the car. We have multiple input images that go through one or multiple image encoders, and then we have this 2D to 3D transformation with some encoder-decoder functions, and then some representation of the world. One example of this representation is the outdated one that cuboids plus free space and any other thing that you can imagine. One key component there is the backbone, and that exists in all the applications that we can see. And obviously, the ultimate goal here is to obtain the best accuracy under the minimum latency, the minimum memory, and the minimum power consumption that we have. There's a trend to go into, There's a trend to go from one backbone per task to go into a unified backbones. As we can see here, unifying the backbones usually incurs in some losses of the accuracy compared to the single task or specialized backbones, but that's still work in progress. The other thing is how to actually generate those backbones. And I'm not going to go into detail, but
we are very good at generating very large models and models that perform extremely well, but those models cannot go into the car. So there's a lot of going on how to actually create these models. I will encourage you to attend. We will be giving a tutorial tomorrow, and also I will be giving a talk in the morning specialized on this, how to get the best of your hardware and how to go from extremely large models to the compact models that leverage the hardware that you have on the edge in the car. The key component on the perception, on the 3D perception, is this 2D to 3D transformation. And this can be basically the idea behind is you have points in the image and you want to find the correspondences in the 3D space. This can be done with a forward projection. Basically, as the pipeline flow goes, you have points in the image and you try to find where do they correspond in the 3D space. Usually with this forward projection, what we obtain is a very sparse volume. And the key component for this projection is understanding the depth. At the beginning, it was a non-parametric depth estimation that was not particularly efficient. With M2VEV, we improved that, simplifying the distribution of the depth. But we can do something more advanced, like some parametric distributions that actually will lead to not only a depth distribution, but we could also compute uncertainty that can be very useful in this era of end-to-end learning to subsequent modules to give like how certain my model is of what they are detecting. A different way to do that is a backward projection. So we start on the 3D volume, and we try for each point in the 3D volume, we try to see which points in the 2D image do we need to gather data from. The problem with that is that doesn't scale well. So Siding was talking this morning, and if you missed that, you can see that again tomorrow. What we can do actually is combine these two worlds and take the best of them, because at the end of the day, they are complementary. And that was the one of the key components that we used to win the 3D occupancy challenge that was presented this morning. So I encourage you to have more insights of this approach tomorrow as well. And with this, again, we won the challenge, and these are some video results of the winning solution. So this is when it comes to the pipeline with data, the 3D perception pipeline. And what I want to touch now more in detail is the data. As we all know, data is the fuel of the new AI models. And it's well assumed that the more data we have, the better the model is. But at the same time, data is extremely expensive, right? Collecting data is expensive, storing data is expensive, labeling data is extremely expensive. And indirectly, when you start scaling this and you have more and more data, the cost of training these models becomes invisible, right? So at the end of the day, maybe we need to start considering not how much, not giving more data, but how much data do we need? And what exact data do we need? And as you can see here, for instance, for ImageNet, if we select properly 80% of the data, we may get better results than just using more data. And we can see this can translate to other applications, and in the end, is very beneficial. So what we have been doing in the past is trying to estimate if we can make an estimation of how much data we actually need for a given problem. And it happens that we can use scaling laws for these AI models. Apparently, these AI models have three areas. One is a small data areas where the model is going to basically doesn't have enough data, so it's going to make a little bit of a random prediction. We have another section that is irreducible error region. Doesn't matter how much more data you put, there's some intrinsic errors in that data, and we're not going to be able to keep minimizing the error. But what is interesting is that in the middle, there's an area where we can actually estimate, given a certain accuracy target, how much data do we actually need. The interesting part here is that means that given a model that is performing in a small data regimes, like with a decent amount of data, but not gigantic amount of data, we can actually predict if we want to achieve certain level of accuracy, how much more data we're going to need. And this, interestingly, translates, is not only for classification, but translates to other downstream tasks. There are two potential very interesting applications here. One is the idea of what happens if, for instance, in traffic sign classification, we have a data set and now we want to add one more type of traffic sign. How much data do we need of that new traffic sign? And that's, if you think about the in real world data sets, and the target was 80% accuracy. And as you can see here, with the model actually trained on the data that we have, we can still predict how well we are going to do and how much data we are going to need of a traffic sign that we still don't have. So in this case, we are using a model that was not even trained on that particular traffic sign. A very interesting use case of this idea of predicting the amount of data is the idea of continuous error correction. So our models are getting more and more mature, right? So one thing that is going to be needed in the future is, given errors that happen at test time while the people is driving, how can we quickly correct? How can we quickly add more data and correct that? So the key thing there is, can we avoid just dealing into, like, going into a continuously long tail problem? If we don't, we're going to be able to use clip or any other image retrieval methods to expand our data set. But if we don't add enough data, we are just expanding our long tail. So it's very interesting to actually estimate how much data we need to correct an error. And in the case of autonomous driving, when we have fleets, we also expanded the framework to say what happens if, instead of going with one single time to collect data, we do that in cycles. So we can learn, and then in subsequent iterations, try to understand at each iteration how much data do we need to achieve a final goal at the end of the collection process. And what is very interesting as well is that we can expand the framework and use it to understand, if we have different sources of data with different prices, how can we minimize the cost to achieve the accuracy that we want? And in this case, we can think of labeled data, human labeled data, unlabeled data, or any other source like synthetic data. If we put this into this learn, optimize, and collect framework, basically we could make an estimation that will give us an idea of how much do we actually need. Now that we know how much data, the next stage, and I guess we are all aware that labeling data is very expensive. As today, most of the performance of our AI methods is based on supervision, human label supervision. So the next challenge is, how can we reduce the cost? As you can see here in the graph, the more data we have in general, the more performance, but can we achieve the same performance reducing the number of labeled images? And one interesting source for this is, can we leverage unlabeled data? There's a lot of things going on with pre-training models, but can we actually do that during training as well? So what we thought is, well, maybe we can use some sort of consistency-based learning. So at the same time we are training with our labeled data set, we can use consistency in the training process to leverage at the same time unlabeled data. Then what do we do with human labels? That's very costly, right? So ideally, we want to use human labels only to label those things that are particularly difficult. And we can do that with things like selecting the frames. We can do that with active learning that are based on the uncertainty of the models. How can we go mine the data and understand where the model is going to learn the most? One key thing here is that all these active learning methods, contrary to what we may think, need to be very efficient, right? What we need to do is traverse all the data that we have that is not labeled and make sure that we can select what data we're going to label next. Or in the ideal situation, we want to bring this into the car, and as we are driving, make sure that we can estimate uncertainty in real time and make decisions based on that. I'm not going to go into detail, but again, most of the uncertainty estimation methods are based on multiple models, and the problem with that is they don't really scale. So one of the challenges is how can we get calibrated uncertainty that can run in real time with a single model and a single forward pass. The challenge on selecting this is most of the work out there is based on a single task, but we are moving to multitask and more complex prediction settings. So how can we move? How can we understand and do a joint prediction of what data do we need for the backbone, for the heads, and differently? And what is more interesting, at the end of the day, the data sets are going to last longer than the models. So if we are collecting data with one model today, how can we warranty that that data is going to be useful tomorrow or in a year time? So what we found some time ago is that actually we collect data with a non so powerful model that's going to last longer than if we use the best performing model for collecting, for understanding which data do we need to label. And then if we only expand our data set with very difficult examples, what we're going to need is what's going to happen is that we're going to shift the distribution, the training distribution is not going to represent our test distribution anymore. So one way to solve that is we can do self-learning to maintain somehow the distribution. That will lead to different problems, like we will need to start thinking of how can we prune the data set, because at the end of the day, if we do self-labeling, the amount of data we can self-label is much higher than that we can manually label. So that's something that we put together. And at the end of the day, what we found out is that combining these three things, self-label, leveraging on label data, and human-based annotations, we can reduce significantly, at least for object detection, the costs in annotation. One quick thing here is we talk about annotation, and in the 3D world, we are mostly using LiDAR for annotation, right? So one of the challenges that we experienced recently is that our data sets, or the data sets that are publicly available, the range of annotations is very limited. But at the end of the day, if we are driving, and we are driving with a long distance prediction, we need to actually annotate those objects that are far away. So how can we get that? The problem with the current LiDARs is that they are very sparse. So annotating that becomes very, very tricky. One thing that we can think about is, well, if given a cuboid and given the depth of that cuboid, we can predict where in the image the 2D bounding box is, maybe we can do the opposite. Given the 2D bounding box, which is very easy to annotate, maybe we can infer where in the 3D world that is. And if we iterate with this, we finally should be able to get some good annotations without even having the LiDAR points there. One thing that is also very interesting about data, and we talked about this before, is like now, how do we deal with the long tail of the distribution? If we think about correcting errors all the time, what is going to happen is that the long tail is going to get longer and longer and longer, right? So one of the problems is that, or one typical way to solve this is to replicate the data. When we think about objects itself, let's say for object detection, the problem is that usually those rare classes are attached to frequent classes. So if you just replicate data as such, what happens, as you can see here, is that the frequent classes get more replicated than the rare classes. So one solution that we thought is, how can we actually is there any way that we can replicate only the objects? So we put this framework together that replicates objects itself and uses image sampling at the same time. And if we put the two things together, at the end of the day, what we get is a much richer training distribution that can overcome the long tail problem. Last but not least, again, data is growing increasingly, right? And training is complicated and it's very costly. So is there any way that we can just continuously leverage the data that we have without thinking of what data we had in the past? And if we can go one step beyond, the models also continuously change. So is there any way that with the model that I have today and the model I will have in the future, I can train my next model? So I will not go again in details, but on Wednesday, Danny will present this idea of continual learning, where we don't change tasks, it's the same task, and what we do is leverage previous models and new data just to keep moving forward and reduce costs. And at the end of the day, moving forward to a fixed training budget, so we don't have to continuously increase the amount of training cost that we have. The last thing I want to talk about is about network robustness, that I think has been not in the attention of many people, right? So when we talk about robustness, many people think about adversarial robustness and it's going to be chaotic, but there's another source of robustness, and is this idea of what happens if there's a small perturbation in the image. Are our networks robust enough? And those perturbations are going to happen all the time in real world settings, right? We can think about different acquisition conditions, noise in the devices, many of those things. What we observe is that our models tend to be very sensitive to these variations, right? On the top here, we see the performance of a 2D segmentation method, and the performance goes down when we change a little bit the image. But this gets drastically lower performance when we move to the 3D perception, right? So the fact that we have this 2D to 3D transformation makes these models extremely sensitive to changes in the training distribution. So we started working on this idea of this efficient transformer for semantic segmentation, where we had a efficient self-attention module and then a very efficient decoder. And with this, we realized that it's not only very efficient at train time and it performs very well, but the robustness of this method was extremely good, right? If we compare back in the days to a top performing deep lab with the results of Segformer, out of the shelf was like extremely good. So there were a few questions that we asked ourselves. So why, this is good, but why only 80%, right? So if we think about the retention ratio, we obtain an 82% retention ratio. That means that when we go out of distribution, we're still not good enough. So how can we, given the best Segformer model, how can we move this to much higher retention ratio? And we started analyzing why this is so robust. And we came with this fully attention networks that basically says that the attention mechanism is the key for the robustness. So if we work on that, and in this case, if we make all the modules with this self-attention, we're going to increase the robustness quite a lot. And we can see here some results that are available where how this is actually happening much better even compared to the previous Segformer. This self-attention mechanism also allows other augmentation techniques that have helped us to go even beyond these fully attention networks and create something that is more robust, even more robust than the previous methods, right? Now, the next question was, this is a large model, but we still want to go into the car, right? So what we observe is that big neural networks are robust, small neural networks are not so robust. Most of the methods, like let's say Segformer, we create a family of models and manually create a family of models, and then one of them may go into the car. So the next question was, why compact models are not so robust, and how can we make those compact models? How can we bring the robustness of these compact models, B0 in this case, up to the same as B5, the largest model? And in particular, the way we are approaching this is, instead of manually tuning the architecture, what we want is to transfer the large network into a compact network. So we can do that through pruning. And again, tomorrow there will be a bunch of us talking specifically about this. And what is interesting is that if we think of pruning and robustness, they are somehow complementary or like orthogonal goals, right? On the one hand, pruning is going to be specific to the data set. And what we found is that it's actually possible to do a joint optimization that is going to bring prune models, compact prune models, to increase their robustness. And that means that at inference time, when we deploy these models, they're going to be much more robust. There's one last thing about robustness and what happens when we change the sensors. What happens if we change the car where we are deploying our models? Again, with 2D, that was a problem, but now when we move into the 3D and we think about the robustness of changes in the sensor suite or the changes in deploying in one car or another, we observe that the accuracy drops significantly. This is extremely important because when we think about deploying self-driving at the scale, what is going to happen is that we're going to have to deal with all the possible models that we have in the market, right? So how can we do this? We can go out there and collect as much data as we can with every new car, but as you can imagine, then we need to relabel again, and that's brute force, but not very cost effective. So one thing that we are considering is, well, can we actually generate that data? And if we are able to generate that data very precisely, then we can expand our data sets and use that data for training. And the key thing here is that we already put our effort to select what data do we need for training, what is the right data that we need to annotate. So everything comes for free, right? Only the amount of the cost of generating the data. Yeah. So as a summary, I talk about three things. I talk about challenges on the 3D camera-based perception, where there's a lot of things to do still on maximizing the trade-off between accuracy and minimizing the latency of the models. We think that starting with extremely large models and optimizing these models to be specific to the hardware is the key to move forward. One of the challenges is how to continuously improve this 2D to 3D transformer module. And then I went into the data space, and one thing that we need to keep in mind is that we don't need more data, we need the right data. And we need to make sure that we can leverage all the data that we have, even if it's labeled, unlabeled, or even self-annotated. And last but not least, on the network robustness, we do believe that we need to start working, or we need to continue working on the robustness of the network. If we manage to improve the robustness of the network, that also means that we can optimize the amount of data that we need to collect, because we don't have to collect data on all possible scenarios. We only need to collect in one, make sure that the network is robust, or we are able to generate data. And with that, in that manner, we will be able to create safer autonomous driving methods. Obviously, I didn't do this myself. It was a bunch of people, NVIDIAns working on this. So all the credit actually goes for them. Thank you.
Thanks for talk, and now we have audience last question.
Yeah, please come.
I'm Chang from Cornell. Correct me if I'm wrong. So you have a method that predict how much data you have to collect for a certain accuracy. So like, is it conditional on certain active learning strategy, or
that one is not?
Just
that one only says assuming that all the data that we have is useful.
Mhm.
How are we?
So just randomly pick something.
So I
from
think the
something.
next step is now how do you inject there the useful data itself? Yeah.
I see. Okay, another question. So you were saying using pruning to actually sort of keep the robustness of the network. Is pruning a better strategy than distillation, or do you consider distillation as part of the pruning strategy?
For me, distillation, we will talk more tomorrow, right? For me, distillation is helpful as a combined with pruning. So the way I see pruning, especially moving forward, is we have this extremely large model that is easy to optimize. We can get extremely large accuracy. And now we need to compress like 80, 90% that model. It's going to be very difficult to maintain the accuracy. So with distillation, we're going to be able to lift that accuracy and minimize the accuracy drop.
So you're considering distillation as part of the pruning strategy?
For me, that's part of the model optimization that comes after. Yeah.
Okay. Yeah. Okay. That's all.
Yeah.
Thank you.
Hello. Thank you for the presentation. What are your thoughts on, instead of optimizing the model to a particular hardware, what do you think about optimizing the model maybe for a like hardware agnostic? I would think that maybe the chip in the car in the future could also change. So what are your thoughts on that?
So I didn't want to go into detail, but it's a very good question actually. So academia, I think, has done like sensor hardware agnostic optimization for a while. When you think from the industry point of view, what I want is something very efficient that given a new hardware, I can quickly adapt my model to the new hardware. That's what ultimately I want. So with model optimization, you have a generic large model and you have an efficient method to adapt quickly that model to the hardware. For me, that's the way to go. I understand that in the future, there's going to be new hardware, but at the end of the day, what I want is to get the best of my hardware today, right? So doing new architecture search or any other thing is extremely expensive. So what is a good method to, given any algorithm, any network, bring it to maximize your hardware today as fast as possible? And for me, pruning is the way to do that.
Thank you.
So I have lots of questions in this type of work, but so what was the range of the bird's eye view predictions? Because this whole thing, I'm assuming you're storing some kind of voxel grid to do the forward or backward projections depending on the method, and it's gonna very quickly overwhelm the compute device, right? How far can you go into the?
Well, that's one of the problems, right? So the voxel space is one that is the main problem when it comes to the efficiency of the method, because that volume is large. You need to voxelize that, and that's you need to find a trade-off.
Right.
So that's why when you do forward, that's very efficient because you only scan on the source. When you do backward, that's not efficient. So combining these two.
But there are some issues that the forward method also has. You've got to aggregate all the different cameras and over, because it's quite sparse, and you've got to pull them at. It's not.
I mean, I don't know the details. The range that we are aiming like very far away, and definitely the compute is a problem. I encourage you to go tomorrow. The sitting will can give you more specific details.
Because you've got the height discretization would play a big role in.
That's definitely that's a problem.
And also, have you considered doing augmentations in the BEV space itself? Is that something that
We have, data augmentation is always a way to go, right? So it's always improve, but there's other ways that we can do, hoping that augmentations then even boost further. Yeah.
Thank you.
For the sake of time, last question from
Thank you for your presentations. And I think you are right. You say the right model, the right data is good than more data. So how can we use the AI training the model? Because I think the camera right now is more efficiency.
Yeah.
So if we can use the camera plus the AI training will be better. So I think how to get the right data, not for the more data. That's the first question.
Yeah.
The second question is if you use this one, maybe we need a low consumption and fast computing chips. So how can we use lighter chips to fulfill your AI training model?
So I think, yeah, the camera is going to be one way to go. And the numbers that we were showing are based on self-training somehow. So it's just cameras. So there's a long way to go, I think, on leveraging cameras to train camera-based models, right? So, and then on the other hand, we can use LiDAR and other methods to do the combination. So I think that's possible. If you want to do that on the edge, definitely that's a challenge because, you need to dedicate some compute to those models. So the challenge is how to get something that is very, is efficient, and you may not need to be so accurate as in the cloud, because if you think about that, only saving, let's say 40% of the collection is a huge saving. So you can have something that is relaxed. The accuracy is relaxed in the car when it comes to what data do I need, and you do a second pass in the cloud. That could be already very efficient, and you could save a huge amount of storage, transmission, and some other costs. So I think that's for me, that's a way to go. Yeah.
Okay. Okay. Thank you.
Thank you.
Right. Okay, so we have a small team. Yeah.
Thank you.
Thank you.
Sure.
The next speaker is Professor. Many of you know he is one of the practice minds in the domain of reinforcement learning. He's currently an associate professor at the university. His work focuses on machine learning for decision making and control, with an emphasis on deep learning and reinforcement learning algorithms. His research includes the developing algorithms for end-to-end training of deep neural network policies and scalable algorithms for inverse reinforcement learning, deep reinforcement learning, and so on and so forth. Let's welcome Sergey.
Great, thank you everyone for the for the warm welcome. Thank you for the introduction. So I'm going to talk about some recent work that we've done in my group on building a kind of a general purpose. Oh, there's a 1 second. Sorry about that. Let me get this out of the way. There we go. And you don't need this. Okay, on building a general purpose robotic navigation model. So let me start off with a little bit of motivation. So it used to be that if we wanted to, let's say, build a computer vision system to, let's say, construct a segmentation or an image classifier or image captioning, we would train separate models for each of these things, and we would require, fairly large labeled data sets for each domain to get a corresponding model that would address that domain. The same thing for things like visual question answering, even tests outside of computer vision, NLP, sentiment analysis, summarization. Each of these was a separate task with a separate training set and a separate dedicated model, typically with its own dedicated architecture. Of course, most of you who are nodding in the audience already know where I'm going with this, that increasingly these days, the way that we approach all of these problems is by taking a very large typically weakly labeled or even fully unlabeled data set, and using it to train some kind of very large unsupervised or self-supervised model, what some people call a foundation model. And the idea is that by training a single model that can serve as a backbone for a variety of different tasks, we can use much larger sources of data, sources that are unlabeled or weakly labeled that wouldn't be able to be used for something like visual question answering by themselves. And then, of course, we would take a small or moderate amount of data for the desired task and either fine-tune our pre-trained backbone, or maybe with the most modern architectures, even prompt them in few shot to perform the task of interest. And of course, we've seen a lot of consolidation around this kind of principle in computer vision with things like self-supervised representation learning methods, in NLP with things like large language models, BERT, GPT, and so forth. But also the other trend that we're seeing increasingly more of, especially in the past year, is the consolidation even across modalities, where we could imagine having multimodal models that can ingest multiple kinds of inputs and serve as backbones for perhaps all of the potential prediction tasks we want to solve. So this is an example for the Paul Me paper from Google that I was involved in, where the robotic navigation model look like. So if we want to apply a notion of consolidation, being able to leverage more sources of data for a general purpose pre-trained backbone, how can we go about doing that? And you can call this whatever you want. You can call it a navigation foundation model, a navigation backbone, a pre-trained navigation model, whatever it is. The point is to do for navigation what BERT or GPT did for language, or what CLIP did for computer vision. That's a very ambitious goal. I don't think what I'm going to show you accomplishes that goal, but perhaps it gives us a hint about how we could take a step in that direction. So roughly speaking, you can think of it like this. We're going to take a very large and heterogeneous data set of navigational data. So not just autonomous driving data, not just data from sidewalk robots, but data from a variety of different robotic platforms that are all performing different kinds of navigation behaviors. And then we're going to try to build some kind of general navigation model trained on top of this data that can then be adapted to a variety of downstream tasks. And this model needs to capture some basic understanding of the kinds of concepts that go into navigation, understanding obstacles, understanding navigational affordances, generalizing across platforms. This model does not have to be able to perform every possible navigation task straight out of the box, but just in the same way that, for example, BERT serves as a pre-trained backbone, this should serve as a pre-trained backbone to then enable adaptation to individual tasks, like autonomous driving, sidewalk delivery. I'll show some demos of RL for off-road driving and things like that. Okay, so what are the challenges that we have to deal with to make this happen? Well, we have to figure out appropriate algorithms, and these algorithms need to be suitable for leveraging very diverse kinds of navigational data. So they need to make very weak assumptions about how that data is actually labeled. In the same way that, for example, you could train a language model on any text data you can pull off the internet, our aim with algorithms here will be to develop the kinds of methods that can leverage any kind of navigational data so that we can use as much of it as possible. We'll, of course, need to be able to collect large robot data sets, and then we'll need to design flexible and general models that could be pre-trained on all this data that are scalable enough, and that can also be adapted to the downstream tasks that we might want to solve. So let me start with a brief discussion of algorithms. So what do we want to actually learn from this navigational data? So what objective can we use to learn general navigational common sense from diverse data sources? So we're going to have all this heterogeneous data. We're going to pull it from all sorts of different robots doing all sorts of different things. That's going to go into some big bucket. We're going to run some algorithm on that. And whatever comes out from running that algorithm needs to be suitable to be adapted to autonomous driving, off-road ATVs, sidewalk delivery, controlling Spot to run around and inspect buildings or whatever. So something that is flexible enough for all this stuff. Well, if we want to try building an algorithm like that, we could start by taking some inspiration from other domains that have been successful at this. So what do unsupervised or self-supervised learning methods in vision, NLP, and so on actually learn? Like, what do they look like? Well, here are a few examples. So BERT predicts missing tokens. So you take some sentence, you mask out some tokens, and you predict them. Language models, they predict the next token, very similar principle. Self-supervised learning methods in vision, like SimClear, well, they're going to transform the image in some way and predict representations of the cropped or transformed image. So in all these cases, we're predicting some kind of missing piece of the data. So all these methods essentially fill in the blanks. They're training on completion of incomplete data, and by figuring out the right bit to hold out and complete, they can acquire a fairly general understanding of what's going on in that data. So this is great because it doesn't require very strong supervision. It doesn't require, for example, ground truth class labels or even a notion of classes. And therefore, it can be run on all available data. So if you can take your data set and you can hold out some piece very carefully and force the algorithm to complete it, that can be a foundation of a really good self-supervised method. So that's what we're going to do for navigation. The objective that we're going to formulate is going to complete parts of navigational trajectories. Now, we could complete them by actually filling in raw sensory observations. That's pretty hard because it's a very high dimensional completion problem. And also a lot of the stuff that you end up figuring out when you're completing observations is not actually all that useful. Like, for example, the shape of the clouds in the sky. So we're not going to complete that. We're going to actually complete actions and temporal distances. So let me explain what I mean by that. So you have to be careful in selecting which bit to fill in. And the prediction problem is going to be set up as follows. Given current observations, so a little history of what you've seen before, so that basically allows the model to figure out where it is and what's going on in the world, and given a goal observation, which during training will just be some future time step in that same trajectory, maybe a few minutes into the future, predict the current action to take, and predict the time steps to that goal, basically the temporal distance. So this is very useful for the following reasons. First, you figure out which actions will get you to different places in the future. So that allows you to understand the relationship between observation and control. And by filling in these temporal distances, now you figure out how far apart things are. So that gets you an understanding of the connectivity of the world. And these are very basic things that you need to understand to do navigation. So for example, if the goal is very far away, you'll figure out that it's far away, even though it might be, visually it might be somewhere nearby. Maybe there's an obstacle in the way, and you figure out that there's something real about obstacles by understanding that things are far away if there's an obstacle in between you and them. So there's a lot that's captured in this. And I won't go into it in this talk, but actually this notion that I presented very intuitively can be quite a bit more precise, because these temporal distances in the parlance of reinforcement learning are actually equivalent to value functions. And we know that if you can figure out value functions, then you've actually figured out good representations for decision-making problems. So that's a separate discussion, but for now, hopefully that intuitive explanation will be somewhat satisfying. So it's a very general objective. You can do this with any navigational data as long as you have sequential observations and corresponding actions. You can do this. If you don't have actions, run structure for motion and figure out your actions. So that's actually pretty straightforward. It captures collision avoidance and basic navigational common sense, because you'll never see a future time step that cannot be reached, right? If you saw it in trajectory, that means it is reachable, at least for that robot. And it's directly useful for zero-shot navigation. So conceivably, you could actually straight up feed goals into this model and ask it to take images, and it would actually drive a robot or a vehicle. But it could also be used in other ways. Okay, so that's basically the algorithm we're going to use. Very simple. And by the way, this kind of thing can be trained with standard supervised learning. You can also use offline reinforcement learning if you want to get shortest paths rather than just the paths in the data set. And in the experiments that I'll show, we'll actually use a little bit of both. Supervised learning is simpler. Reinforcement learning can be really helpful if you want to initialize for online RL later down the line. And I'll talk about that a little bit too. Okay, so let me describe some work that we've done that actually uses this method. First, just for straight up doing goal reaching, but then we'll extend it as a general pre-trained backbone. So this is a project that we did at this point about 3 years ago, where we just wanted to explore this way of training models. So the user specifies an image as a goal. In this case, they take a photograph of their front door, and the robot is supposed to deliver something. It delivers, in this case, some mail or a pizza to their front door. Okay, very straightforward problem setup. Find and navigate to a given goal landmark using only camera observations. So there's what the robot sees, there's the goal, and the robot is supposed to figure out the actions in between that'll get it to the goal. And I'll show a lot of these kind of aerial views in these slides. Unless stated otherwise, the robot actually only gets the first person view, and then the aerial view is just extracted from GPS just for your visualization so you can see what it's doing. So the model is pretty much a straightforward instantiation of the idea from before. There's a convnet that takes in the current observation, a convnet that takes in a goal observation, and it predicts the number of time steps between them and the action to take at the current step. And that's just supervised directly with the data set. Now, by itself, this kind of model can reach nearby goals. Think like, on the order of like 50 meters in front of you or to the sides. If you want to reach very far away goals, then you have to combine this with some kind of planning approach. And it turns out that a really, really simple planning approach works great here. So we use a topological map that's constructed from other observations the robot saw in the environment. So this is not running SLAM. This is not trying to actually map out the environment. This is just taking other images the robot saw. All you need for this is the images, connecting them with a graph where the edges of the graph are the distances predicted by this model. So for the endpoints of each edge, you feed in the images of the model, ask it to predict the distance, and label the edge with that distance. And now you can use that graph to plan paths to distant goals. Of course, you need to have driven around the environment before to collect those images, but we'll get rid of that assumption shortly. For now, assume that you've driven around there before, then you can reach distant goals. One of the cool things about this project when we first did it is that we actually, taking a step towards leveraging large data sets, we actually didn't collect any new data for this. We actually just used all the data that we had collected in our previous navigation research. So we had done a bunch of navigation research before that for other projects, and we just took everything, trained up this model, and it was able to navigate around some outdoor environments up in Richmond Field Station north of UC Berkeley. So that was pretty neat. But then, of course, we wanted to relax this assumption that we require having seen images in our environment before and actually turn this into a viable navigational system that can solve some real navigational problems. And the way we did it is by basically giving the robot a map, not a reconstructed SLAM map, but like literally a map, like the kind you get from Google Maps. And that turned out to work great. In fact, you can just give it a satellite image. So the idea is that we had our goal condition model, and just like before, we predict the distance to the goal and the action. And we would also predict now an additional GPS offset. So not the GPS coordinate, but just the offset from its current location. And that you could then use to index into a satellite image. And then we would give the robot a satellite image and train a separate model to act as a kind of heuristic, think like A-star search heuristic. And this heuristic would basically guess the answer to the following question, given the current state and the final destination, which might be very far away, and some predicted waypoint that's on the way there, is the waypoint on the path to the final goal. So we would learn, like, for example, if the waypoint is an intersection and the intersection looks like, like the one in the picture there, that it's on the way to the goal, that's like maybe a good waypoint to go to. But if it's in the opposite direction, then that's a bad waypoint to go to. And the point was that this was supposed to serve as a heuristic to just bias the robot in the right direction. And now we could actually use this to drive around environments that had not been mapped out in advance, in the sense that we don't have those first-person images, we just have the satellite image. So the heuristic was trained with contrastive learning kind of in a fairly obvious way. So you would just take positive pairs and negative pairs. And then we would combine this with the navigation model into what you can think of as almost like a physical A-star search. So the robot would be building this graph as it goes. So it would start off in a new environment where it hasn't seen any images before. As it traverses that environment, it adds additional images to the graph with edges computed by the model. And when it comes time to select a new node to navigate to, it would use this heuristic to pick which way to go. Or if any of the existing nodes have a higher heuristic value, just like an A-star search, it would backtrack and go to one of the existing nodes. And that would be very convenient if it got stuck in a dead end. So here's a video of this in action that hopefully makes it a little bit more concrete. So over here, you'll see the satellite image. In the lower left, you'll see the first person image. This is about 1 kilometer. The course here is about 1 kilometer in length. The goal is in the lower right-hand corner. That's the green circle on the map. You can see the robot does a pretty good job puttering around this environment. The environment had not been seen before, except for the satellite image. Mostly it does very sensible things. It kind of gets biased towards the goal. It cuts across this grassy field, so it's not trying to obey any rules of the road by any means. At one point, it does actually go into a parking lot where it gets stuck, so it just backtracks and goes back onto the road and finds a better path. And then eventually it reaches the destination. So this is basically the first time it's seen this environment. The only thing that it's provided is the satellite image and the coordinate of the goal. This thing can traverse paths that are about 1 kilometer in length. If you give it some intermediate checkpoints, we took it on a hiking path that was 2.7 kilometers long. So that was pretty neat, although we did have to tell it the key milestones along that path. Otherwise, it would try to go off-road through the forest, which would not be fun. Certainly not fun for the student having to follow it around. Because the satellite image is used only as a heuristic, this thing can actually handle situations where the satellite image is not correct. So here in the example in the top right, someone parked a semi-truck across this path. The satellite image has a clear path there, but when the robot approaches the semi-truck, the first-person view tells it that this path is not traversable. So then the navigation model says, okay, I can't actually go through there, and finds a route around the parked semi-truck. This can work with heuristics computed from other data. So of course, the satellite images are the best. That's the one shown in blue. If you just give it GPS coordinates, but no satellite image, that's the pink path, then it's still biased in the direction of the goal. Of course, it doesn't know where the obstacles are, so it has to backtrack quite a bit more. If you give it neither GPS coordinates nor the satellite image, it'll essentially do kind of a random frontier search, which is not terrible, but in this case, it's a little too hard for it. But it can still reach nearby goals in that case. Okay, but this is not yet providing us that pre-trained backbone for other tasks. This is just validating the notion that training a model to reach goals in this way does something. It does some kind of reasonable navigation. We can start using it for other stuff though, and we'll build a much bigger model later that can be even more flexible, but just to give a preview of the kinds of things it can be used for to convince you this is a fairly flexible recipe, let me tell you about a project that we did about adding language instructions. And here we were able to add language instructions to this kind of pre-trained model without actually changing the model at all. So the way that we add language instructions is we just use a language model to interpret the instruction. The instruction might be like, after passing the white building, take the right next to whatever. Interpret the instruction using a language model to turn it into a sequence of landmarks, essentially a sequence of waypoints, and then take the observations that were seen in the environment, run a vision language model to figure out which semantic objects are present, and then when planning through the graph, essentially generate a plan that accords with the instruction, meaning that the plan has a very high probability of visiting the landmarks that the instruction is actually describing. And notice here that the vision part, the actual navigation model, is not changed at all. It's literally the same exact model. So all that's being done is just a vision language model is being welded onto it to interpret the semantic content of the images, and then that's incorporated into planning. So the vision, the visual navigation model gives us the temporal distances between the nodes. That's what VNM means. The language model transcribes an instruction into a sequence of landmarks, and then a vision language model, in this case, CLIP, basically associates language with the individual images that we've seen. And then you do a big joint decoding, which can be formalized as a kind of graph search to figure out a sequence of nodes that both has short distances between them and visits the landmarks that were described. And then you can do stuff like this, where you can tell it, go straight towards the white building and right to the stop sign, look for a glass building car, and then the robot will decode that into a path through the environment, drive around until it visits each thing. So here it goes to the stop sign, takes a look at the stop sign, then it's going to go to the white car. That's the second one. Notice it says after passing the white car. So it'll go to the white car, and then we'll go to the glass building. So the point I wanted to make with this project is just that once you train one of these goal condition models, it's not just for doing goal images, right? Like then you can weld a front end to it. In this case, with language, you could weld onto it a front end with other things and actually use it to perform a variety of tasks. Okay, now this was still at a somewhat more modest scale. This is still controlling a single robot. Let's talk about scaling this up a little bit. So first, can we get one policy that can control many different robots? It turns out that that's somewhat to our surprise, this was actually not that hard to do. So we're going to use basically the same model with one small modification that I'll describe shortly. And really the key to making this happen was just to collect the right data set. So we essentially called up all our friends. We said, hey, if you got some robot navigation data, can you send us your robot navigation data? And we collected a bunch of robot navigation data. By the way, if you're in the audience and you sent us something, thank you. We got data from everything ranging from a full-size ATV down to a small-size RC car. There's some data from a spot robot that someone had put on the internet. So there's a whole bunch of different stuff in here, ranging in size. And the model that's trained on this data set is actually almost exactly the same. The only modification is that now instead of getting the current observation from a robot, it's given a little temporal context, basically a little history of frames. And that's really useful for essentially figuring out what kind of robot you're driving, because if in that temporal context you see it making really sharp turns, well, perhaps this is a robot that can make sharp turns. We thought we would need to work harder at getting the model to really understand something about the robot it's controlling, like maybe give it some parameters of the robot. It turned out that that wasn't really necessary. Maybe it will be necessary if the robots differ more drastically, but in this case, just that little temporal context proved to be sufficient. The other thing that kind of surprised us here is that we could then take this model and actually have it generalize in zero shot to entirely new robots. That's actually, at least to me, this was pretty shocking. So, for example, this drone here, I'll talk about that more later. It was never trained on drones before, this is the first time it's flying a drone. So let's talk a little bit about how this thing generalizes. Well, first, it generalizes to a lot of things. So this is just a collage of all the different kinds of experiments that the students ran, all using exactly the same model. And you can see here everything from outdoor robots to indoor robots, turtle bots, local bots, drones, etc. And it could control all of them. In fact, it could control pretty much any ground robot we had in the lab. If you have other robots you want us to try, you can send them to us. We also found, surprisingly, that this model was much more robust to physical changes to the robot. So here we stuck a stick into the wheel of the robot, which changes its dynamics to kind of simulate mechanical damage. And just to prove that this mechanical damage is non-trivial, if you command the robot to drive in a straight line, before the damage, it goes in a straight line. After the damage, it veers off to the side and crashes into the bushes. So this is really changing the dynamics of the robot in a meaningful way. The GNM actually does a pretty good job of controlling the robot, even with the damage, I guess, because once the robot is modified in this way, it just looks like a different robot. And if you can generalize across robots, then you can generalize to a damaged robot. So that's great. This is the drone. Now, I will give a caveat here. The drone is pretending to be a car. So the drone is flying at a fixed altitude. The model is not controlling altitude because it doesn't understand altitude. It only understands ground vehicles. But other than that, there was no modification made to the model to do this. And straight out of the box, it could fly the drone around hallways. So that's pretty cool. That means that it really is figuring out some general notion of obstacle avoidance. The other thing we could do with this model is we could modify it a little bit to pre-train it with offline RL and then do online RL fine-tuning for high-speed driving. Now, of course, you'll notice the video in the lower right is anything but high-speed driving because this is what it does more or less out of the box. So out of the box, it comes equipped with some rudimentary ability to drive this rally car. It's actually worse than the GNM out of the box because we reset the last layer because we're going to run a different online RL algorithm, but it's kind of decent. And then that's 5 minutes in. So 5 minutes in, it's kind of, roughly making its way down the hallway, although periodically bumping into things. And then we're going to keep training it with online RL. We use a very efficient algorithm called RLPD, and it's learning from raw pixels here. So this is 5 minutes in. Here it is 15 minutes in. Now, 15 minutes in, it still collides occasionally, but it's starting to do a much better job of making its way around this building. The racing course here is just to race around the 5th floor of Soda Hall, which is a building on the UC Berkeley campus. So it's certainly not racing at this point. It's driving kind of at a moderate speed, but it is getting much, much better at following the hallways. And then 25 minutes in, it actually starts going pretty fast. It actually kind of doesn't look so fast from the third-person view, but this is like pretty much near the top speed that we could do without risking the vehicle damaging itself. It's also pretty close to the fastest route that the human driver, the expert driver, I guess, who is the grad student, could do from the first-person view. If you let the grad student drive it from the third-person view, they can actually do a little bit faster. But from the first-person view, this is about the max you could manage. So that's pretty cool. And that's 25 minutes, right? So for those of you that are familiar with reinforcement learning from raw pixels, learning in the real world in 25 minutes is actually not very easy. You can do the same thing outdoors. Part of the reason why it's so efficient is, of course, because it has that really powerful pre-trained backbone to start from. So this is the beginning of training. It's supposed to race around a building. Now, of course, just like indoors, at the beginning of training, it's not doing that great of a job, but it's doing something. It's kind of roughly making its way around, bumping into things periodically. And here it is at the end of training. Now, there's a few cool things you can notice. Outdoors, of course, the terrain is much more interesting. So one of the nice things it can do is it can maximize how much time it spends on those paved paths. It's not perfect at this, but it's pretty decent. Part of why it has to go on the grass here is that the waypoint, the checkpoint that it has to go through is actually on the grass. But after it goes through that checkpoint, it beelines towards the paved path and tries to keep some time on there to go a little faster. So it actually does a pretty good job of racing around this building. And again, we found that this was about as fast as the grad student who was doing the project could do himself from the first-person view. So this is the first-person view. I think it actually looks a lot faster from first-person because the vehicle is small. So when you see third-person, it looks kind of slow. First-person, you realize that given its size, it's actually going pretty quick. Okay. So that's online RL fine-tuning, and that's pretty nice. I was pretty happy with this result because generally, I've worked on online RL a lot, and learning a policy from pixels in 25 minutes that's quite a bit faster than anything I've seen before. But let's try to scale this up even further. Let's see if we can get towards something that looks much more like a real foundation model that can be adapted to a wide variety of downstream behaviors. So what we're going to do next is we're going to take the same basic recipe, the same kind of prediction problem, but we'll scale it up to have a much larger transformer-based model that it's going to take a tokenized version of the observation history and a tokenization of the goal. It's going to have quite a few more parameters. This is small by transformer standards, but it's huge by robotic policy standards. So it's about 30 million parameters. And we're going to solve the same problem, temporal distance and normalized actions. But then what we're going to do with this model is we're going to see how far we can push in terms of generalization and how we can adapt it, how we can fine tune it to downstream problems. So we're going to build this model, which we call VINT, the Visual Navigation Transformer. And then we're going to use it for zero-shot navigation, for exploring new environments, and for adaptation to new tasks. So first, let's talk about the zero-shot stuff. Let's talk about how we can use it to explore a new environment. So the problem is, of course, we need to feed it goals to explore a new environment. And if we visited other places in that environment before, we can just give it the images that we've seen before. But if we haven't been in that environment before, we have to produce the goal images somehow. That might seem like a pretty difficult problem. In fact, when people think about these goal image condition policies, that's one of the biggest stumbling blocks. But fortunately, we've gotten as a community pretty good at generating pictures. So we're just going to use the best models for generating pictures, in this case, a diffusion model, to basically propose goals. So the diffusion model is literally going to take what the robot sees now and produce pixels for a potential goal to explore. And then VINT is going to navigate to that goal. And here you can see the navigation in action. Now, something kind of funny that many of you might have noticed is that the goals shown on the right, these are generated pictures. Not all of them look very good. Some of them seem like they're in a completely different environment. But there's just enough good goals there, just enough goals that are feasible for the robot to visit, that Vint still does the right thing. Because remember, the Vint model itself is pretty robust. It actually understands how to avoid obstacles and things like that. So if the diffusion model, let's say half the time produces garbage goals, but the other half produces sensible proposals, then Vint will actually do something sensible with it and actually explore the environment properly. And that's pretty neat. That suggests that the robustness of the model is actually making it easier for us to use it for downstream behaviors. We can use it to control, in this case, a goal one, a quadruped in zero shot. So since we already tried the drone before, the drone still works, but we wanted to do something new. So we had it control a quadruped. This is on the UC Berkeley campus. It actually wasn't trained on campus itself. We trained in these outdoor environments in Richmond Field Station and indoor environments. But since there's enough of them, then the campus also worked. But we can also adapt this to tasks that are not expressible with image goals. And here we take an approach that's very heavily inspired by prompt tuning. So the idea is this, that Vint takes in the current history of observations from the robot and a representation of the goal. But what we can do is we can replace the goal with some other modality, like, for example, a turn-by-turn instruction, turn left, turn right, go straight. And the way that we're going to do this is we're going to basically cut off the encoder for the goal and train a new encoder that encodes whatever new goal modality we have, like these turn-by-turn instructions, into the same token representation. So the rest of the model is left frozen, and only the goal encoder is retrained to interpret the new modality. Now, this is getting a lot closer, in my opinion, to what you would expect from a solid pre-trained backbone. Just like you can fine-tune BERT, for example, to do new text classification tasks, you can fine-tune a new encoder on this thing to get it to solve new types of goal modalities. So we experimented with a few different things. We experimented with navigating GPS coordinates, and we also experimented with taking turn-by-turn instructions, like think the kind of instructions you get from Google Maps, like turn left at the next intersection. The basic navigational common sense from Vint is retained, but then this ability to interpret new commands is acquired. So this is a small experiment in Carla, where every time the robot approaches an intersection, there is some top-down high-level planner that basically tells it left, right, or straight. It's just a three-way discrete command. And it can successfully drive around in Carla doing basic things like lane keeping. This is not by any means a sophisticated autonomous driving system. It's just a proof of concept that the same Vint backbone could be fine-tuned to a very different scenario. The other thing is, of course, that this was pre-trained entirely on real data. Carla is not real data, but that's fine. So you do need a little bit of data to actually do the fine-tuning, but of course, much, much less than what you would need to learn this from scratch. Okay, so a few takeaways and perspectives. The goal with all of this was to really do for navigation, or at least start to do for navigation, what BERT and GPT do for language and what CLIP does for vision. I don't think it's by any means done yet, but hopefully this illustrates that something like this could be possible. There's still a lot of questions that remain. Of course, different navigational contexts have very different rules and conventions. For example, if you're driving a sidewalk robot versus you're doing autonomous driving with a full-size car, they have different and very contradictory rules, right? In fact, for the sidewalk robot, it's the exact opposite. How do you handle this? Well, so far, we're just handling it through raw fine-tuning, but it would be very nice to have a model that's more flexible to receive some description of how it's supposed to drive in its current context. The current model doesn't do that, but you could imagine things like language conditioning could enable that in the future. So perhaps we could incorporate more complex prompting, perhaps something like in-context learning by prompting with demonstrations or language descriptions or other sorts of modalities that could conceivably be built as an extension on the current goal prompting technique. Perhaps we could generalize to platforms of very different capabilities. So far we assume that all these robots can be commanded with waypoints in 2D. That's why the drone flies at a fixed altitude, but conceivably it could be extended to have different action spaces with tokenized actions that's not too difficult to set up in terms of the model. So there's a lot of interesting questions, and I think it would be really exciting to study those in the future. How much time do I have? Okay, I have a bit of philosophy, but I'll save the philosophy for the panel discussion, and then I'll stop here and take questions.
I mean, you didn't finish by philosophy, but I'll ask you a philosophical question. Great work, and we are following your work. We're cheering for you on side. Looking forward to borrowing your ideas and applying our work. I'm from Motional, by the way. So the question is, you're comparing the ideas between LLM and navigation. In LLM, the input is aligned, fairly well aligned.
Yeah.
The output is less aligned, and we fine tune for that. This is a bit opposite, right? You have sort of misalignment in the input and a bit better alignment in the output.
Yeah.
what's your experience there? Like, how does it affect the complexity of the problem? Maybe the problem is not as complex, so we don't need to capture that much of insight. So I would like to hear a little bit more, maybe before the panel, or maybe feel free to say some to the panel as well.
No, this is a really good question. I am afraid I don't have like a very intelligent thing to say about it. I think that but from my own experience, I guess, okay, so the first GNM paper that I described, that was really our first foray into multi-robot learning, where there was this really big issue in terms of things not being quite aligned. For that one, I was actually surprised by how not bad it was. Like, I kind of expected it to be a complete disaster. My hope was that, like, well, maybe it'll successfully control all of the robots it's trained on, but it actually turns out to be able to control all sorts of other robots. Now, I do think that something about navigation is special there, in the sense that all the navigation tasks are structurally similar. And we did have to do a little bit of work to actually align the action spaces, just insofar as putting them on the same scale. So basically the ATV is like, 10 times the size of the RC car. So its action space is like divided by 10. But that was actually all we did. Now, I have worked quite a bit on multi-embodiment policies for robotic manipulation, where this kind of stuff is a lot harder. So for manipulation, it really is the case that you're lucky if you generalize to all the robots you train on. But it seems like navigation has so much structural similarity that you can actually get these sorts of effects. I do think this stuff will get much harder and more interesting when we start dealing with the context more properly. So I'm kind of shamelessly giving this talk in an autonomous driving workshop, and I'm sort of hoping that people aren't going to challenge me too much on the fact that, that indoor navigation problem is completely different from autonomous driving, because stuff like that, which we're not really having. Maybe that's kind of really the next frontier, to basically tell the robot not just where you want it to go, but how you want it to get there in a way that generalizes in this way. So that's the thing for future work.
Thank you.
Actually, a follow-up to that, how do you evaluate these for quality, right? Because you gave a lot of like subjective videos to say, broadly, this seems like it's working, but as you start scaling this up, as you start adding new features, how do you measure how much better you're doing?
Yeah, so the quantitative results are all in the papers. I decided not to bore you guys with the numbers, but for all the things that I showed you, typically what we measure is distance traveled without collision, kind of very similar to autonomous driving metrics, distance traveled without collision, number of routes in the test set that it completed successfully without colliding. Time for the RL stuff, it was actually the speed of the lap. So kind of more or less what you expect. And yes, it's decent. Like, the multi-robot training actually does pretty significantly improve those metrics.
Thank you.
For the awesome talk. A follow-up question, actually. So when we try to deploy this kind of general navigation model, how do we ensure the safety in the real time? And let's see, if we encounter out of distribution, what do we do there?
Yeah, that's a really good question. So here, there's nothing that's handling that. The hope is that if you have sufficiently diverse data, then you will get more robustness. So this is something that we've actually seen a lot in computer vision. Like, people have observed multiple times, for example, that the CLIP model appears to be more robust than features trained on ImageNet. Why? Well, because CLIP has more training data. So at least part of the hope is by incorporating more sources of data, you will get more robustness. But if you want to use this in an actual safety critical setting, of course, that's not going to be good enough. So sort of the presumption here is that this model gives basic navigational capability. If you want to enforce constraints and things like that on top of that, then you would use whatever is the best method for handling that. So this is kind of not really addressing that.
Got it. Thank you so much.
Yeah, also from my side, thanks a lot for the talk. You talked about decomposing the problem of learning something general into the next waypoint, and then the time to reach the goal. And like the latter one also largely depends on what type of robot you're facing, like how fast can it be? Is that also just solved by the scale thing you just answered in the first question, or?
As well as by the fact that it gets a little context, right? So the model actually receives some previous frames from that robot, and that's basically giving it the context necessary to figure out what kind of robot it's driving. Now, I think it's very reasonable to surmise that in general, that shouldn't be enough. Like, just because you saw the robot driving at like 10 meters per second doesn't mean it can't drive at 50 meters per second. Yeah. So I do think that in the long run, maybe there's a better way to provide that context. We found this to actually work decently well, so that's why we're just using it. But yeah, probably there's a better design that could be feasible.
Oh, cool. Makes sense. Thank you.
Right. So in traditional AV stacks, like there's would be under the planner, right? So but presumably it's doing some sort of perception as well. Do you have a sense for what the model is learning in terms of occupancy or static versus dynamic obstacles or?
Yeah, that's a really good question. So like one of the ways that we can examine this model is we could, for example, give it random garbage goals, like you can actually just feed in random numbers and see what it will do. And what it will basically do is it'll more or less drive straight while avoiding obstacles. So it kind of seems like a lot of what it's learning is avoid things that are coming right at it. In fact, one of the things that we found, this is very anecdotal, we haven't done this systematically, so I'll say it, but just keep in mind with the usual, take this with a grain of salt. We actually found that the larger model, the transformer-based model, actually had much better ability to handle dynamic obstacles being like grad students walking in front of it than the smaller model we had before. And that's based on this like random goals test where we feed it in random goals, have someone walk in front of it. Anecdotally, it seems like the transformer actually gets better at that than the smaller model. So that's how we're testing it. We haven't done this very rigorously yet though, so that study is still ongoing.
Thank you.
Yeah, so actually very similar to the previous question. I noticed that like with all of these models, you're using 2D images as input, and then your goal navigations are kind of just like, well, drive forward until like maybe you hit something. Do you think that the lack of depth perception or 3D understanding is limiting this model or this like paradigm in some way?
That's a good question. I think there's kind of nothing stopping us from giving it depth maps or any other modality. We really wanted to optimize for being able to use as much data as possible.
Sure.
So we basically reduced everything down to the lowest common denominator.
Right.
I think if you really wanted to get the maximum capability, what you would probably want to do is train a model that takes in variable modalities and get it to use depth when it's available and not use it when it's not available. As far as how important depth is, I mean, my honest answer is I don't know. I think there's probably people in this room who would have much better sense for this than I do. I mean, I'm kind of a learning guy, so I always somewhat foolishly approach this as like, well, just tell me what sensors you have and I'll do my best with them. Whereas I think people that actually build the whole thing end to end will think about what's the ideal sensor. And I think if you guys want to think about the ideal sensor, then maybe my job would be to make sure my model can accommodate whatever sensor you've got.
Makes sense.
Hi. My question is, have you tried building a general robotic model for other tasks such as manipulation, for example? And if yes, which one's easier? What are the challenges that are similar? What are the challenges?
Yeah, thank you for asking that question. I have slides on that. I just didn't want to go into them because I'm conscious of the fact that I'm talking in an autonomous driving workshop. But we are doing more or less the same kind of stuff for robotic manipulation. We have a lot of work, especially out of Google research, that studies training large transformer models for manipulation. In fact, the design of this architecture is virtually identical to the RT1 model that some of you might have heard of, the robotic transformer, which basically does this for manipulation. Now, I will say from my experience, cross-robot transfer is much easier for navigation than it is for manipulation. I could guess as to why, but the truth is I don't really know. Perhaps there's more structural similarity in navigation problems. Perhaps the navigation data is much more diverse. I think that's actually a really big one. So we're doing the same kind of multi-embodiment stuff for manipulation, and it's coming along, but it's definitely not, it's not something that wants to work seemingly quite as much as the navigation model.
Yeah, I'm the last one. Okay, regarding for your models, I just thinking about like, because for the sidewalk, maybe it's a real problem because there is some pedestrian on the road, and also the sidewalk is up and down. So not only directly go to the house. So how can we to solve this kind of question for the practical use? And do you use some 3D map, or who will be your ecosystem to provide this kind of data set so we can go to the house directly without thinking about the safety issues?
Yeah, that's a great question. So this is actually something that we're working on right now as an extension to this work. We actually already have a data set of sidewalk driving that we collected in the city of Berkeley. Right now, the approach we're exploring is basically similar to the prompt tuning that I showed for Carla driving, where we're trying to essentially take a data set that has just sidewalk driving. So kind of you can use basically a learning for demonstration approach to figure out what sidewalk driving means by fine tuning it on top of this model, and then do these kind of turn-by-turn instructions. Now, we haven't gotten that working yet, but we're kind of hopeful that since the Carla stuff worked, then maybe we can adapt to the sidewalk data as well. So that's underway right now, and hopefully in a few months, I'll have an answer for you.
Thank you for all the time. Our public break will be 10 minutes and we'll restart at 15:10. Yeah. Driving, it's changing. The poster is still there, so maybe tomorrow it's top down. I want to stay here for the challenge. I'm going to grab a coffee now.
Hey, how's it going? I do. One of those. You can't come to a conference without being prepared with an adapter, right?
I don't have that.
Here we go. Hey man, how you doing?
Hey Alex, great to see you. Yeah, looking for really great results. Shared, JD shared some great results with the stuff.
It's pretty exciting. Yeah, we've only had that model a couple of weeks, and every day we're discovering new capabilities. Got some to show in this talk, actually. Great. Awesome. Do I need to go on any Zoom or anything like this?
Yes, you are prepared to share the screen and at the same time.
Okay. How do I do that? Is the Zoom link in the calendar invite? I think.
Do you have Zoom first?
Yeah, here we go. This one here. No, I've got it here.
Right.
Cool.
Just wait a minute and you are okay, right?
Recording in progress.
Shoot. And so I just need to share screen.
No. Yes.
Does that work? Hang on, this is broke. This is not up in here anymore. Sorry, it's there we go. Great.
Okay, good.
Cool. Does that work all right? Oh, it's
it might be this line is
cool. Great. Seems to work. All right. All right. Sweet.
Patrick from Expo.
Hey, how's it going?
Hey, yes. I'm really looking forward to your talk. Yeah.
Awesome.
Yeah, also seeing that you have made a great progress recently a field blog with official site.
Yeah, it's been an exciting couple of months actually.
You think we're almost there?
We're getting closer. We're getting closer.
Alex, may I try out my setup as well?
Oh, yeah, sure. Feel free to unplug that.
Right. Let me ask around if they have an adapter.
Do you want me to borrow this or you got
But I
USB-C?
mean, you probably, yeah, but you probably need to stay here, right? But I mean, over the.
You can borrow it for your talk if you want.
I can return it to you at the panel. If you
Yeah.
like.
Yeah, you joining? Yeah, that's
Yes.
fine. Go,
That would be
you're welcome to
great.
borrow it.
So I don't need to. Yeah, I'll just quickly check it out and
Go for
give
it.
it back to you. All right, thanks. Oh. Okay. I should, sorry, I should not activate the speaker, right? Wait. Host has joined, we've let you.
And you have to wear this Harry Potter. Okay, I'm there after.
It's working, right?
So about
Hello, everyone. Now let's take a seat and we'll restart our afternoon session. All right, so next it's exciting for us to have Alex Kendall, who is a co-founder and CEO of Wave, the London-based company pioneering AI to scale autonomous vehicles to complex, never-seen environment. Alex is a world expert in deep learning and computer vision. Before founding Wave, Alex was a research fellow and PhD at Cambridge. Many of you might know Alex from his uncertainty quantification for perception work. He's really one of the pioneer work in our domain. And Alex's leadership and vision has led Wave to become one of the most exciting startups in the autonomous vehicle market. Let's welcome Alex. Yeah.
Thank you for the really kind introduction. And I think it's gonna be an exciting talk today because we've been working on this can play okay. So we've been working on end-to-end deep learning for autonomous driving for almost 6 years now at Wave. And if anything, I feel like this year has provided some of the, I'm going to go as far as saying big breakthroughs that are really making this method viable and feasible. I'm looking forward to sharing some of if this can come on, I'm looking forward to sharing some of these with you today. And in particular, one result that we haven't talked about publicly yet, which I'm really curious to get everyone's feedback on. Do you know how to get, is this on the adapter side or should I try this one? All right. Bear with me while we set this back up again. How's that? Great. All right. Where was I? So today I want to talk to you all about the frontiers of embodied AI. And to start off with, I wanted to give a motivating example for why it is such a challenging problem to address autonomous driving. It is to be able to create an autonomous driving agent, you need to have to be able to deal with such diverse sets of scenarios. I'm just showing a bunch of different driving videos, and you can see the diversity in appearance and behavior and agents in the scene. And it really is a true open set problem. So what we've found is that you need to go beyond a specific task-driven AI to create a really robust and intelligent system that can deal with that long tail to be able to succeed in this space. And fundamentally, I think that the holy grail of the autonomous driving space is going to be solved by building an AI solution to the problem. And this has really driven the approach that we've taken at Wave. So what is that? So to quickly introduce what we've been working on, we're taking an end-to-end deep learning approach to the autonomous driving problem. So that means that our stack that is today running on our fleet in the UK has an end-to-end deep learning model, billion parameter model that has raw sensor input and a motion plan output. And our belief is that by building that kind of learning system with the right set of data infrastructure and feedback is what's going to allow autonomous driving to scale. We think of this as a next generation approach to autonomy in AV 2.0, and I've listed some of the key features of this approach. The first one is that generalization is going to be absolutely key to getting autonomy to scale. And for us, AV 2.0 is characterized by a system that is easy to generalize and adapt to new places without needing significant engineering in each new environment. So for example, without a requirement of high definition maps. The second one is that it's vehicle friendly and can operate with a low bill of materials cost. So moving away from the expensive 30 camera, 6 radar, 6 LiDAR setups, but moving to a setup that makes it economically viable and feasible to integrate into fleets at scale. And then the third one is creating this fleet learning framework that allows us to align behavior with human expectations to really create a system that has trust and safety. Today, we operate these vehicles here, a Jaguar I-Pace, as well as electric vans. And if you look at the results of what we've been able to see with the end-to-end deep learning system is that it's able to operate with really substantial robustness, even when it rains and snows in London. This is a system that can drive and deal with the kind of complexity of environment that we need to be able to operate in. I mentioned generalization. Well, what we've been able to see so far is that we can generalize between those two different types of vehicles that I showed, the passenger vehicle and the van. What that means is that we've got a single neural network that can learn to drive both of those vehicles with the same parameters. So it's agnostic to sensor pose, to vehicle geometry. But not only that, we've been able to generalize to different geographies. So we predominantly learn to drive in London, but we've been in over 10 UK cities now, and we see that the system can drive in those cities despite having no training experience from them. So I guess what we're trying to show with these results is that we are moving towards building a general purpose learning system for driving. And don't take my word for it. We had the chance to host Bill Gates for a ride a couple of months ago, actually. And this is myself, our safety operator, Deepa, and Bill in the car driving through central London. We picked him up at his hotel and went for a drive through the busy streets of Soho and King's Cross, and even stopped along the way for some fish and chips. Have a look at the video on YouTube if you want. It was quite a fun one. Today, we are starting commercial trials and really looking at how we can start to realize commercial impact with this technology. And so we were excited to launch a couple of months ago a last mile grocery trial in London. Now, the neat thing about that is that our autonomy is dropped straight into the operations of our partners, Ocado and Asda, and is able to access, in that trial, just from one site in Northwest London, access over 170,000 customers because it can drive on new routes every day, routes it's never been on before, at all times of day and all weathers. And these trials are demonstrating the power of this AV 2.0 approach. So hopefully that gives you a little bit of context of where we're at as a company and where our technology is at today. What I wanted to spend this talk talking to you about was where the frontier is of embodied intelligence. But before we do so, I just want to spend some time reflecting on where the frontier of AI is this year. And I'm sure many of you will have been inspired by some of the breakthroughs we've seen, things like AlphaGo, ChatGPT, or DALI, or you could go on and list many of these breakthroughs that have really transformed what we can do with AI technology. The interesting thing to me is that there's a bunch of foundations that underpin all of these results, and they're surprisingly common and shared across all of these major breakthroughs. Let me just run through some of the major ones for me. The first one is data sets and benchmarks. Often underappreciated. The interesting thing to me is that typically data sets and benchmarks are what catalyze the breakthrough itself. Take image recognition, for example. Convolutional nets were first proposed in 1989, yet it was the ImageNet data set in the 2010s that made that a solved problem. Games and simulation. The key thing here for me is being able to move with fast feedback. And I think games and simulation provide an ability to iterate at the speed of software. Self-supervised learning. Of course, self-supervised learning is really, we heard a lot about it in the last talk, but it's really the key thing to be able to remove the need of labeled data and learn on data at extraordinary scale. Foundation models, to be able to learn general purpose models with emergent behavior. Of course, scalable compute and architecture, it's a remarkable result that we can see fairly predictable growth and performance as you scale up data and compute and training across many different AI tasks. Multimodality, I'm keen to talk a bit more about this in this presentation and why it can be so powerful, in particular for embodied AI. And finally, alignment with human goals, being able to train these systems to get the trust and safety that we need. All of these foundations have really underpinned those breakthroughs. And the point I want to make today is that I think these same foundations are going to be what changes the game for embodied AI. So I'd like to share 3 examples in particular with how with how they apply into the embodied AI space. I think embodied AI is going to be, my prediction is I think over the next couple of years, we're going to see much more, a great amount of impact realized from some of these large language models and internet scale generative AI. But I think embodied AI gives us the opportunity to go beyond all of the internet text and video that I think we've almost exhaustively used to power some of these systems. Embodied AI gives us another data source to fuel even more advanced development of AI systems. Of course, we live in a physical world, and I think in 10 years' time, when we think of AI, it won't be a LLM, it'll be an embodied physical system. And so for me, that's why this is such a fundamentally important mission to work on. So what are we going to cover today? Well, the three really exciting pieces of work that I feel fortunate to present on behalf of all of my colleagues that have made this possible. This is what we're going to be talking about. First one is reinforcement learning for driving. Second one is bringing language into the driving domain. And finally, some new results from world models. So let me dive into each of these 3, starting with reinforcement learning for driving. This one touches on these 2 foundational building blocks on games and simulation and alignment with human goals. But I wanted to start off by, going back a few years to the very beginning of our work at Wave. This was some early work from 2018, where we actually put, for the first time, a reinforcement learning agent on a real-life physical autonomous vehicle with vision input. And this is it's a model-free RL agent trained with the task, with the reward of trying to drive as far as it can without safety driver intervention. This is actually me as a safety operator. And the interesting thing here is that it started off optimized from scratch, initialized randomly. And you can see after a few episodes it can't drive and drives off the road. But after a little bit more training, you can see that it's learned a policy that is somewhat stable and can keep it in the middle of the road. Yet it oscillates, and it's still not very good. But after 10 episodes of learning, so you can see a few more pieces of feedback, it's able to learn to do basic lane following. And that was really cool because we saw for the first time, learning in front of our eyes, we could actually get the vehicle to essentially learn to drive. But of course, it's a very, very simple environment, and here's what we've done. We've done a multi-agent reinforcement learning paradigm where we can train diverse and large-scale driving agents in simulation. Our simulator, the Infinity simulator, gives us a procedurally generated world of exceptional diversity, and we can run this with hundreds of agents at 700 times faster than real time. We train these agents from low dimensional tokenized input from the simulator itself. And the thing that's really exciting behind this is that we don't just train one agent, we treat all of these agents independently, and we can learn both good and expert driving, as well as diverse and adversarial driving to ensure we have a robust world. Now, the rewards we set in this world are very simple. They're don't hit anything and obey a few basic traffic rules, but it's a really light touch reward paradigm. And given this environment, we see some remarkable emergent behavior emerge. So let me show you. Here's one example. So you can see our vehicle here pauses and waits for the gap before coming through. This kind of emergent, let's say, cooperation comes out of training. Or this one here with some quite complex give way scenarios. Again, this all comes out of that training paradigm. And so this is neat. We can see that with increasing training and scale, we can essentially solve the driving problem of complex urban driving in simulation. And you can see some of the results that we can now populate our world with agents that far outperform any hand-coded agent we can create. And they learn all kinds of behaviors from conservative driving through to adversarial driving. And populating this world gives us an environment to really accelerate the development of our autonomy. And of course, I mentioned that these agents were trained from low-dimensional privileged information from the simulator. Of course, we can distill this into a non-privileged driving policy that takes image inputs and can drive with similar capabilities. But now we might ask the question, okay, this is in sim. How do we get it in the real world? Well, to that end, we can address the sim to real. How do we address the sim to real domain gap? One of the interesting things to see is we can actually go the other way. We can train a policy just on real world data and then deploy it in our simulator. And here you can see that this is a driving agent that's trained just on real world data, now driving in our simulated world. And so we see that even though you can see from that result, even though there is a domain gap that you can observe, we still get fairly robust transfer. We can push that even further by using neural rendering techniques, NERF, other methods. And you can see here an example of us testing a policy in one of our NERF worlds. And so this gives us fairly photorealistic environments. We can adapt camera pose and all that kind of thing as we move between different vehicles and test largely in static worlds, although we're working on adding dynamic agents into our NERF environments as well. So to summarize, in this section, we've been able to show that we can train really effective reinforcement learning agents in a multi-agent setting in simulation, and our simulator is becoming effective enough that we can see transfer into the real world. And so, where are the opportunities from here? How can we develop rewards that can function effectively in the real world? And of course, continue to improve the sim to real gap even further. Let's move on to the next section, which is about language meets driving. I think this is really exciting to me because it builds on a lot of the transformational results we've seen from large language models. And it's work that we haven't talked about publicly yet until today, in fact, at some of the talks at CVPR today. So really curious to get everyone's feedback, but this really touches on the multimodality foundation. And in particular, let me start off with some motivation of why we want to consider language when we're thinking about driving. This is something that would have seemed absurd to me a couple of years ago, but I've become deeply convicted that language is a massive accelerant to driving. So the thing we know is that language, LLMs already know a huge amount about driving. Now, if you take, for example, ChatGPT and ask it some basic questions like, if you're driving and a bull rolls out onto the road, what should you do next? It tells you you should stop. If you're doing it next to a school, it reasons correctly that it's more likely a child might run after the bull. And if you say if it's at midnight, then it reasons correctly that it's unlikely children are going to be playing on the road at midnight. So there's a bunch of really interesting inherent knowledge that's present in these LLMs. You can ask other questions like, what should I do if I'm approaching an intersection and I see a motorcycle with no one on the top of it driving? And it actually reasons that, oh, that's a really weird thing to see on the road. And so you can see it starts to know what is expected or unexpected on our roads. People often say a picture is worth 1,000 words, but I'm going to make the opposite argument that a paragraph is worth 1,000 pictures. And here's why. If you think about this scene here, what do you need to learn from it? Well, you need to learn that there's pedestrians on the pedestrian crossing, so you need to slow down for them. It's a T intersection. You need to make a decision whether you're going left or right. You need to give way. And actually, there's a 20-mile-an-hour speed sign as well, so you need to change your speed. That's probably the description that you need to learn from this. But if you were to learn that from simply, a self-supervised way, watching videos, that would take you gigabytes, if not petabytes of video to learn those concepts. What I just told you is less than a kilobyte of text. And the point I'm trying to make is that although there's more information content in images and videos, the signal to noise in text, the accuracy and specificity of that data is orders of magnitude higher. There's a reason why we've developed language to communicate between our human brains, between each other, and it's because it's the most effective way to communicate information. And I think we're going to see the same with embodied AI and robotics. So we've done exactly that. We've built a system that we've trained a system that is able to ground a large language model in driving. And this is really exciting. Have a look at some of the results. We have our driving AI can not only drive, but we can query it and start to ask it questions. For example, if you look at this question that we're asking about this driving scene, should we start and proceed through this intersection? And we actually start to ask our model why. Have a look at the answer it gives. It's quite remarkable. This AI tells us that no, we shouldn't proceed because the traffic light is red. It's important to obey the traffic signals and wait for a green light. And it warns us around all of the agents in the scene. Let me show you another one. This is quite a fun one. Should you honk at the pedestrians crossing the road? The AI explains to us, no, you shouldn't honk at the pedestrians crossing the road because they've got right of way and they're crossing on a green signal. And so, we can start to query our driving AI. And I think, why is this powerful? Well, I think it opens up a number of opportunities, whether this is for interpretability or explainability, or actually understanding why the system is behaving in a certain way, by improving the performance, by bringing in the knowledge from language, or perhaps even a future solution to remote assistance. If you want to help your driving AI in a situation it can't understand, you might want to give it a text prompt. Here's what it looks like in a video. So this is our system driving through London and explaining what it's doing. And you can see it's actually giving a commentary. We've prompted it, asking it to explain its driving. And you can see it's turning left, it's following the route, it's maintaining speed, and then, oh, actually we're stopping down. And it even explains it's stopping because there's pedestrians on the crossing. Well, let me show you another one. I think this is fascinating. It's correctly describing that it's slowing down because there's a cyclist ahead. We overtake the cyclist, and then it's slowing down because there's pedestrians at the zebra crossing. And this, this language model, this driving AI can now start to actually commentate and explain its driving. And I can show more. This is another interesting example where, again, remember, we don't drive with an HD map. This is driving based on what it sees, and we're being told to go straight and actually explaining that it needs to change lanes to follow its intended route, to go through the lane that allows it to pass straight ahead. So you can see that just with some very initial training, it's able to learn concepts like pedestrians, cyclists, traffic signals, lane changing. I think this is really exciting and opens up a new forefront for embodied AI. Right now, we're capable of explaining our driving in text, but I think we're really close to being able to do the other way, to be able to prompt our driving with text. And so I guess there's many opportunities from here, but one I'm really excited about is not just grounding vision and language, but also action. It's also worth commenting that large language models, we know that they're frequent in the way that they hallucinate, and that will be a challenge here as well. But I think the important thing to think about here is how do we bring how do we allow these systems to reason about their uncertainty and actually know what they don't know. For example, we saw an example where it said it thought that a motorcyclist without anyone on top was weird. It should know that and be able to reason about when it might not know something and not be forced to hallucinate, but be aware of that. But ultimately, I think this does provide extraordinary opportunities to improve the confidence and the understanding in our driving AI through language. Would love to know what you think. Let me move on to the final section, world modeling, where I'm really excited to talk about a new result that we've developed at Wave, Gaia, that we released for the first time a couple of days ago. But world modeling, it really touches on all of these foundations. I think it's the holy grail of intelligence. If you have a world model which can predict and understand the world, I mean, that's the closest definition that I can think of an AGI, of a true AI. Now, of course, we're building a narrow world model for driving scenes, but being able to predict and understand the world is that for me is true intelligence, and it touches on all of these different aspects. All of these things are required to make this work. Why do we need to develop world models? Well, to drive well, it's really important that you understand how a scene is going to evolve. If I ask you how you should drive given this image, it's really hard to tell whether this white car is going to pull out in front of us or not. And of course, when you see the video, we're able to actually understand intuitively and predict what's happening. So that's why world modeling is important. But what is a world model? Well, a world model is a generative model that is able to predict the next state conditioned on an action. So it's a model that can allow us to predict how the world is going to unfold given a decision that we make. And of course, this is incredibly useful across the board for autonomy. It lets us actually look at counterfactuals, to resimulate, to learn from this environment, from this world model. And in fact, it's really how we learn in our human brains. There's a lot of evidence that our hippocampus, the world models in our brain, are able to replay experiences in many different permutations from what we've experienced in order to improve our motor behavior. And my expectation is we'll see the same from embodied AI. It opens up model-based reinforcement learning and imitation learning opportunities, or allows you to do search-based planning. If you want to go down the tree search method that solved AlphaGo, for example. Some of the work that's been talking about this for the last few years that really inspired me was a paper from David Haar and Schmidhuber on world models, or a paper that scaled up these approaches, Dreamer v2. More recently, Jan LeCun wrote an opinion paper arguing that world modeling was one of the biggest missing building blocks to creating embodied intelligence. I agree with him. We've actually also been working on it at Wave for many years. Another flashback to 2018, we trained a world model back on that same quiet country road that I showed you that reinforcement learning demo from. And here's the example. I think this was I can't remember, it was something like a 10,000 parameter MLP that's encoded into a 16-dimensional latent representation. It was really tiny back then. But what we found is, and you can read the blog post from many years ago, but what we found is that training that world model on some recorded data from this road, we could learn to drive on that road despite never having, with no on-policy interaction. And so even with that very rudimentary world model, we were able to learn how to drive on a road through just imagination and experience by unrolling that world model. Since that work, we've been able to scale it up, but first we, again, if you want to look through the history of our work here, Fiery was a paper where we worked on using semantic labels and a bird's eye representation to better structure the world model to scale it up to busy and dynamic scenes. We showed multimodality, we showed diversity, and then Mile connected this with imitation learning and integrated it, but only in simulation. If you want to read more about the Mile architecture, just quickly, it was a recurrent model that encoded into that bird's eye view space, could recursively go forward and decode into not just perception outputs, but also action. There's been, outside Wave, there's also been a ton of work that's worth mentioning. Things like NVIDIA DriveGAN or other diffusion modeling around videos at various levels of accuracy. But this has been a really hot topic for the rightly reason that Jan LeCun points out, that it's of a video generative model on action. I wouldn't argue it's a world model. It's simply generating a plausible video. It's conditioned on style and things like this, but it's not generated on action. And again, with various levels of performance and robustness. But what I want to show you today is the results of Gaia 1. This is a model we've only had access to for a couple of weeks, but it's truly extraordinary. I think it represents a step change in capabilities of world modeling for embodied AI. So Gaia 1, generative AI for autonomy. Let me show you some of the results. This is something we released yesterday. And the thing that I'm excited to share, if you remember that very first slide I showed you of the array of videos, these were not real driving videos. All of these videos were generated from Gaia 1. All of these videos here are samples from our world model and represents the diversity that we can generate. So let me talk through the properties and dive into some of the features of this model in more detail. So Gaia-1 is a self-supervised autoregressive world model, and it's capable of being conditioned not just from video, but also text and action prompts. So crucially, it is an interactive world model. It's got an incredibly temporally coherent and accurate representation. It can look at multimodality. And crucially, we see safe and emergent driving behavior within this world model. This is a sequence generated from the world model. It's entirely synthetically generated from a short video prompt. And you can see that we learn to drive down this quiet road. We imagine feasible and realistic scenarios that come up, and it's temporally stable over, I think this video has been sped up 4 times, but I think it's something like a 2-minute sequence. The results were mind-blowing to me when I first saw them. So the architecture itself is, as you could imagine, it's an autoregressive architecture. It takes video, text, and action inputs and encodes them into tokens and feeds them into this autoregressive world model that we can decode into the video you just saw. Here's some more results. You can see that it's able to model pedestrians, traffic behavior, signals like traffic lights, roadworks, many other things that we find in our training data. We're able to see different weathers, different lighting conditions. We can look at different futures, so we can sample it multiple times. You can see the same video prompt we fed in the same few frames, and it's able to model diverse futures from that prompt. So here you can see, one, we look at what happens if we turn left at this intersection. One even imagines a different intersection. All of this stuff is occluded from the original prompt, and so it's uncertain what might be there. And so the world model is able to look at the distribution of things that might happen in the future. It's truly remarkable. And one in that bottom right, we saw a pedestrian come across the road. Here's another example where we turn right, and we don't know what we might expect down that right turn, right? Because it's occluded as well. And so here we can start to, we can again sample and look at those different futures. I guess what these results show is that we can genuinely look at diverse and multimodal futures from this initial prompt. And these are all from video prompts. We can also condition on action. So here you're going to see the model play forward, and then we're going to condition it with different action commands. And you can see when the model starts turning, it's when we trigger that action command from a slight left or a slight right to a hard turn. And you can see that the world model correctly synthesizes the world evolving based on that action. And this is what makes this, I think, a real step advancement from the video generative models, as it's a true world model that we can drive in. Look at this. When now we're conditioning it on a random walk of a sinusoid as input into the model, and you can see we drive around, and it's got remarkable consistency even when we drive off the road. It's never had any training data driving on the footpath. We don't drive our cars there, but you can see the model is still able to synthesize remarkably robustly, and even our action, and understand and model how that will affect others' actions and vice versa. But this one's truly exciting to me. It's a similar thing. We put in the same sinusoid, and you can see us drive around, particularly as we get significantly out of distribution. And look at this. We are out of distribution to the point where we're driving on grass, and then we drive into a bush. This is entirely synthesized, and it is truly out of distribution. And so the fact that the world model can show coherent data when we're going this far out of the lane, for me was mind-blowing. And this is all action conditioned from that initial video prompt, and then driving with this, it's just a random sinusoid we put in. But let me just pause it. The thing that I've been staring at these for the last few days, they're amazing. But look at this. If you can see that really thin structure there, it's maybe a pixel or less wide. As we drive forward, see how it holds its space and time. I'm going to play that again. I think it's a really, really interesting thing to look at. You can see that thin structure stays there in a way that's consistent in the 3D scene. For me, that was really exciting to see. I think two or three more final results here. You can see where we condition it now on text. So I've shown you how we condition it on video, on action, And now text, we're saying turn left or turn right. And you can see that it made a left or right turn depending on the text we condition it on. And it's that same language grounding that I was showing you before. Similarly, this is not prompted on any starting video or any starting action. We only give it a text prompt. We say going around a stop bus. And this video is entirely synthetically generated from that text prompt. So there's no input video. And you can see there, it's been able to produce a scene that quite accurately matches the text prompt. We can look at counterfactuals. So here, the same video prompt, but different text prompts. And you can see we can play it forward and look at different counterfactuals, whether the light turned green, which way we turn, or if it stays red. All of these scenes are imagined forward from the world model. This one's quite cool because we prompt it halfway through this video to go from this rainy day to a nighttime, and you can see it gradually transfers it to nighttime. So we can change the weather, change the time of day, and all of this is controllable through prompting. So look, we every sorry, I'm getting some feedback. So what's next here? So this is a model that, as I said, we've had it for a few weeks, and every day we're discovering new capabilities. It's a relatively small model, right? It's less than 1 billion parameters. And what we're going to be doing over the next weeks and months is scaling it up to billions of parameters of scale, more data, and the results we're seeing so far is a really meteoric growth curve. But of course, the key benefits come when we integrate this world model into our driving AI. And I think that's what I'm truly excited to see the improvements in trust and safety that we can see as a result. So let me conclude. I think the points that I hope that you can take away from today is that autonomous driving, it is an AI problem. Gone are the days where you can solve it with a perception planning mapping stack, where you can divide up to the problem into different components, where you can rely on safety assuring each component in isolation. The way that this is going to be solved is going to be the same as Go, same as AlphaGo, same as ChatGPT. It's going to be through end-to-end deep learning. And in fact, the foundations that have made some of those breakthroughs are already starting to accelerate driving. We believe that world models and language, as some of the examples I've shown you today, are going to be results that provide meaningful step change capabilities to the intelligence of our system, and ultimately be what brings us autonomy at scale. You've seen some of the results we're building at Wave, and we're just getting started. I couldn't present this work without all the incredible colleagues that I get to work with, many of whom are at the conference, so please do come say hi to us. If this is work that interests you, whether it's academic or research collaborations, or if you're interested in joining our team, we're absolutely looking to grow this, and I would love to have a conversation. My contact details are at the bottom. Please do come chat or get in touch. If not, I'll be glad to take questions. Thank you so much.
Questions. For the sake of time, we will take 4 questions.
Awesome talk. So I'm trying to figure out what are the guiding principles you see, these approaches, right? And just use think about large language model, right? There are 2 guiding principles, right? One is, the scaling law, right? So essentially, as you scale data compute, right, and model capacity, and then you get better, right? And then there is a thinking called compression is intelligence. So essentially, language model just compressing your data, and then as you scale, you keep compressing, and then really sort of reasoning and all these things come because you needed to compress the data better. So what are the guiding principles you think for autonomous driving? Do you have this scaling law or the
Sure.
Compression is intelligence? Yeah, thanks.
So the results I've been excited about are the scaling laws you see in large language models with data and compute, and we're seeing the same thing for the control problems. Ultimately, of course, the interesting thing for us is we're limited by the onboard inference compute we have. But there, I think I wouldn't bet against the rate that we're seeing algorithms get more efficient and the improvements we're seeing in onboard compute. But we will regardless push that to the limit. Sorry, what's the specific question? I guess.
Compression is intelligence.
Hmm.
Essentially, it's driving your, your system much better, a large function to do much more capable, to be more capable,
You want to see these systems compress to produce behavioral concepts, right? You don't want to have them memorize or just, copycat from the training data. You want to have them compressed so that they're truly understand these concepts and they're grounding them between the different modalities of training data. That's what we're really looking to push here.
Okay, it's the same principle you're saying. You're essentially also compressing the data. Okay, thanks.
Thank you for the presentation. What are your thoughts on when you're generating with Gaia, like a video, for instance? I saw you were generating for UK-based location, right? Because you were driving on the left. If you wanted to generate that for a city when you drive on the right, would that be a problem?
No, it's just a matter of additional training data. There is fundamentally no difference with driving data from the US to the UK, for example, or Canada, where you drive on the right. I think there is going to be different behavior, like, for example, four-way stop signs. We don't see those in the UK, but you see them in North America, things like this. But ultimately, if you have the training data that has those experiences, then Gaia will be able to reproduce it.
Thank you.
Hey, Alex, fascinating talk. I can see this so many times and I'm going to be equally fascinated, and had the privilege to seeing it slightly earlier. So it stayed with my mind, the part where you had the LLM describe the behavior of the algorithm. And I think you guys cracked the code of explainable AI, right? That's the true explanation. So my question to you is slightly kind of technical. And I mean, maybe you're going to say, I'm not allowed to say, but I'm really curious to understand, how do you guys, so you prompt it with text and you also, I suppose, get a text back out of it, but do you do joint models? Do you train another model on top of it? And the reason I'm asking is to understand, how are you thinking about the fidelity of the explanation? How do we know it's aligned with the behavior?
It's a single foundation model. So we feed in video, text, or action prompts. We can drop them out during training. At inference time, you can see that we can pick and choose which ones we prompt in. But the key thing is it's a single multimodal model. That's really important. If you train all these models separately, you won't get that joint and complementary training by bringing them together. The second part of your question around performance, I think we've seen three results that really push down the hallucinations and push up the performance. One is scale. Scaling data and compute and model size, you just see improvement in accuracy. The second one is by introducing ability for the model to be aware of its own uncertainty and not forcing it to make predictions where it's not capable of. And then the third one is having, algorithmic advances and improved grounding, whether these are auxiliary tasks or other structuring, a way that you can help influence the causality of the model. These are the kind of techniques that I think we've found promising to overcome hallucinations or challenges in the model.
Awesome. Absolutely fascinating.
Thank you.
Hi, Alex. Thanks for sharing the progress and your vision on the emerging technologies. I have a question about the multi-agent RL simulator and also the world modeling. So this opens up like opportunities for generating diverse behavior. However, there's a generative data.
Sure. There's been a few approaches to thinking about that problem that I've seen. One of them is that if you can ensure that your simulator or your virtual distribution is a superset of the real world, so for example, domain randomization, where you look to randomize beyond the bounds of the real world, then you can be more certain that the real world will exist in that subset somewhere. It's perhaps inefficient, but it gives you sufficiency around that. The other one is that you measure the correlation, and one of the key metrics for us is the correlation of various parts of our simulator and the whole simulator as a package. And so we directly measure the correlation and performance on the real road compared to our simulator, and look to drive up that correlation.
Got it. Thank you.
Thank you for the great talk. It may be a similar question, but how the Gaia 1 work in the real car? And what's the difficulty in integrating the Gaia 1 into the real vehicle?
So that's work we're starting to do now. This model Gaia 1 is something we've just trained. It's the results I'm showing you from offline inference right now. And we just obtained them recently. We're absolutely thrilled and excited about it. What's going to be coming next is we're going to be working on actually integrating it into our training, policy training, and online online driving algorithms. There's an array of approaches we're trialing, from synthetic data generation to model-based imitation and reinforcement learning. There's a ton of different ideas there. There's so much to do. So give us a few months and hopefully we can share more on that front.
Thank you.
Great, let's thank us. Bye-bye.
Thank you.
Thank you. Thank you. Next, we have Pat to discuss about the very exciting new plan challenge, the results, the fundings, and the award ceremony. All right, welcome back, Pat.
Close enough. See if we get this configured correctly. Yeah, also need okay.
Yeah. We remember the conference number. Yeah. Okay. You should just wait a minute. Okay.
Recording in progress.
Yes. This should be. Okay. Yeah, that's right. No, just share the screen. And you need to unmute yourself. Yes. Here we go. Share my screen. Is it working? I think it is. All right, can I start? Yeah. Perfect. All right. Thank you everyone for being here. My name is Pat Kanchanachari. I'm senior engineer at Motional, where I lead the new plan team. One of the many things that we do as the new plan team is running and hosting the new plan motion planning challenge that I'll be going through today. So a quick run through. Well, first I'll give you an introduction of Motional, what we do, how we went and collected the data set and curated it for us to release to the public, how we built and designed the dev kit to accompany the data set, followed by how this all builds up to the challenge that we hosted, and we'll end with the finalist presentations at the end. So at Motional, we're building a level 4 autonomous driverless system. We developed this with collaboration with Hyundai on the all-electric Ioniq 5 robotaxi platform. The platform is equipped with over 30 sensors to enable fully safe autonomous driving operations.
Over the past decade, we've hit a number of milestones. We've launched the world's first pilot robotaxi system service in 2016 in Singapore. We launched a public robotaxi service also on the Lyft network in Las Vegas in 2018. It is now the world's longest standing public robotaxi fleet. We became one of the world's first companies to go fully autonomous on public roads in 2020. And we also launched AVs for deliveries on the Uber Eats network. So over the past 5 years, when we've launched the service in Vegas, we've given over 130,000 rides where we achieved the vast majority of rides have been rated 5 out of 5 stars. So the mission here at Motional is to make safe, reliable, and accessible robotaxis a reality. So now on to new plan, the data set, the dev kit, and finally the challenge. So new plan is an evolution of new scenes. You've seen in previous presentations before where new scenes been referenced, we've released 2 iterations of it. First, new scenes in 2019, our second iteration in 2020, and last year in 2022, we released the new plan data set. The data set contains 1,282 hours of human driving data. It's collected from over 4 cities, Las Vegas, Pittsburgh, Boston, and Singapore. A portion of this data set is also released with sensor data. Lastly, we tag interesting events and scenario in the data set. Some of these scenarios includes unprotected cross turns, dense vehicle interactions, jaywalking, lane change, pickup drop-off area, and vehicle following, just to name a few. The reason that we tag this is to enable quick and efficient evaluation of planners. So we want to be able to identify what scenarios and events our planners are good at, and more importantly, where we can improve. So how do we collect the data? As I mentioned before, we collected through human driving data. We sent the cars out to 4 cities and collected them all raw sensor data. We then processed it on our offline perception system. This is to remove real-time and memory constraints that would otherwise be present on the AV platform online. We use many LiDAR sweeps, and we look into the past and to the future to achieve a consistent tracking solution for detection of agents and obstacles in the scene. On top of this, we have traffic light information that is inferred from the agent's motion in the scene. And lastly, we have route information as well. The route information is inferred from the driven route by the human driver. And this is depicted as a sequence of roadblocks along the route. Next, we have the dev kit. The dev kit is a way for us to quickly access the data set that we provide. We developed a modular and scalable framework for evaluation and training. So I'll be mostly focused on the evaluation part here, but there's also the whole training side that you can read more on our website and directly at GitHub. So the evaluation framework, it's split into 3 main parts: the simulation, the metrics, and the dashboard. So the simulation itself has 4 components, the observations. The observation first is how we represent the world or the data detections to the planner, raw sensors or 3D boxes. Next, we got the planner. Under the context of the competition, this is what the contestants are providing us for the competition. This is also how we implemented our baselines for the competition as well. So it doesn't matter, it can be ML, it could be rule-based, it could be some hybrid platform that you design, it could be any planner. Next, we've got the agents. So how do we propagate the agents along the scenarios? The most simple way to do it is to do log replay. So simply taking the actions of the agents in the scene and just replaying it is the most common way of doing it. You can also propagate it through according some predefined path. We call this on rails, and that will just allow you to be more particular with how the agents are moving, although it then deviates away from the log. Lastly, we've seen in many presentations beforehand, that you can do ML policies as well. There's many companies trying to do it to achieve realistic and diverse traffic simulations. Lastly, we've got the controller. The controller here can be the perfect tracking controller, which is simply taking the plan trajectory from the planner and interpolating along the planned path. This is somewhat unrealistic because if the planner decides to do something that's kinematically infeasible, then the car will simply teleport to that point. So we also provide a kinematic bicycle model along with a LQR tracking controller to simulate low-level control and the dynamics of car that would be present on real AV on real road. This also confines the movement of the AV to be kinematically feasible, leading to more realistic simulations. Like I said, it's modular, so we can configure this to be open loop and closed loop by selecting the modules that I've listed out here. Once we've run the simulation, then we pass it on to the metrics engine. The metrics engine here will calculate the metrics based on whether the scenario is ran in open loop or in closed loop. I'll go into a little bit more detail of what those metrics are in a later slide. And lastly, we've got the dashboard. And this is just how we visualize the metrics, time series data, and also the scenario itself. And you'll see some of the visualizations later as well. So to the challenge itself, it's a planning challenge, as the title suggests, but however, you can think of it as a prediction planning challenge as well, because the input to the planner are agent boxes, the map, the goal, and the route. So we don't provide the planners with any prediction. So any good planner will need to account for possible trajectories that the agents might take in simulation to plan accordingly. These are very important, especially like cross turns, Pluto areas where interaction with other agents is crucial. The planner module is responsible with outputting an ego trajectory, which is then fed back to the simulation suite, trying to track the given trajectory, pass through the kinematic bicycle model, and then this loop keeps going until the end of the scenario. Like I said before, the simulation or the evaluation framework is modular. So we've split this down into 3 main challenges. In challenge 1, it's the open loop challenge, where both the ego and the agent simulation is in open loop. It's very self-explanatory. Everything's according to the log, even though the agent will plan, the ego will plan differently from the expert trajectory, will not deviate. And this is more similar to a motion forecasting challenge. In challenge 2, we make the ego propagation closed loop. And similar to challenge 1, in challenge 2, the agent simulation is still in open loop, so it follows the log. And in challenge 3, we have reactive agents. So now both the ego and the agent simulation are in closed loop. For agents policy, we follow the IDM policy, stands for Intelligent Driver Model. It's not an ML policy, it's a simple policy that describes how an agent should drive according to a lead agent, maintaining some sort of distance and targeting a velocity. So let's see how this looks in action. On the left, we've got open loop. The thing I want to point out is, as I mentioned before, the plan trajectory might deviate from what the expert route is in orange, but the ego will simply follow what was in the log. Here we compared the plan trajectory with the expert trajectory. In the closed loop non-reactive agents challenge, now the ego is in closed loop. What we have here is a situation where the planner drives considerably slower than it was in the log, leading to a false collision, as you can see here, where a lagging agent essentially collides and goes through the ego, leading to an unrealistic scenario. So to remedy this, we have reactive agents where now all the agents are aware of each other, and more importantly, the ego. So again, with the same planner that's driving a bit slower, the reactive agents are now respecting this change in behavior and accelerates a bit slower, not then avoiding the collision that you saw in the second graphic. So now we have all this. So how do we quantify the performance of AV? So we've got metrics here. The scenarios are given a score from 0 to 1, where a higher score indicates a better performance. For the better performance here is different for open loop and closed loop. Again, with open loop, we're taking inspiration from motion forecasting challenges. So we're taking metrics such as average displacement error, final displacement error over the position and the heading. As for closed loop, we have to be more sophisticated with the metrics, because in closed loop, the scenarios generally diverge from the log, and therefore you cannot really hold down only to the expert trajectory as the ground truth or the correct thing to do. It's not very easy to quantify what the correct thing to do is, but it's quite easy to identify things that you shouldn't do. So things that you shouldn't do, you shouldn't collide, shouldn't go out of drivable area, shouldn't go in the wrong direction, follows the speed limit. And the likeness to the expert here is we simply take a look at if the ego is making progress along the same route as the expert. And that's how we see if the behavior is somewhat similar to expert, but we don't really constrain the metrics to the expert directly. And lastly, we've got comfort metrics as well, just to guard for jerky planners. Now that we have the score for each scenario, we then aggregate them by just taking the average over the whole challenge. And then to get the final score of the entire challenge, we take the average of challenge 1, 2, and 3. So before we go to the results of the challenge and see what the finalists did, I want to show you the baseline that we set up for the challenge. We have 3 baselines in total, 2 rule-based, 1 ML-based challenge baseline. Sorry. First up, simple planner. As the name suggests, it's very simple. Plans in a straight line, constant speed. The only logic that it has is it will decelerate if the speed is faster than the max velocity that's set for the planner. Quickly here, you'll notice that the scenario here is tagged as starting right turn. And the planner is supposed to turn right into the pickup drop-off area. But because it's simple planner, it completely ignores that and goes straight through the intersection, thus failing this scenario. So adding a bit more sophistication to our rule-based planner, we've got the IDM planner. Again, IDM stands for Intelligent Driver Model. So we're using modified policy for the reactive agents for this and repurpose it for this planner as well. So there's 2 parts. First part is the breadth first search path planning, which simply plans the path along the route towards the mission goal. The second part is the longitudinal velocity control. Here, the planner takes a look at if there's a leading agent. If there is, then it tries to maintain some distance, a safe distance. If not, then it tracks a velocity. Usually we pick the speed limit for this. As you can see, the starting right turn, this planner has no problem and simply takes a right towards the pickup and drop off area. However, it's not all powerful. There are still scenarios where it does fail. And here is an unprotected turn, a relatively complex situation, and has reason to wait for oncoming traffic before turning. As you can see here, that it simply collides onto the oncoming vehicle at the front there. So next up, we've got our ML-based planner, which is based on L5 Kit's implementation of Urban Driver. We implemented our own version in new plan, and we trained it in open loop. It takes a vectorized input of agents and map. It passes through a global attention mechanism that predicts the ego trajectory. During training, to account for the distribution shift in closed loop simulation, we apply some data augmentation to the agents and to the expert trajectory so that can drive in closed loop. What you'll see here is like actually the reverse of the IDM agent. First, we saw that the IDM agent can turn right just simply fine, but now we find ourselves with the ML model struggling to making a simple right turn. However, in the unprotected turn, it actually reasons correctly to wait for oncoming agent before turning onto the intersection, crossing it onto the pickup and drop off area. So here are the challenge results. These are the distribution of the overall scores of all the submissions. We had 52 in total, or from 11 countries, from 21 institutions in total. Here are the scores of our baselines, where Simple Planner, unsurprisingly, came in very low, IDM at middle of the pack, followed on by Urban Driver at 0.75. So let's break it down challenge by challenge. First, we've got the open loop challenge. What you'll see here is IDM and Simple Planner performing very poorly, and then Urban Driver actually doing really well. The reason for this is the open loop challenge favors imitation learning based method, especially if your planner is trained on the new plan data. It learns the action that the driver usually takes for each snapshot and tries to imitate it, thus scoring fairly well in the open loop challenge. So rule-based planner here ignores this entirely and plans according to its algorithm, and therefore performs really poorly on this challenge. For the closed loop non-reactive challenge, we see that now the IDM planner is now performing much better. The Urban Driver performing less good, but comparable to IDM planner. But what we see is both learning and rule-based planner perform well, but the best strategy so far, based on what we've seen from our own experimentations and what we saw from the submissions, which did better than both the IDM and Urban Driver, are hybrid methods. Methods which combines both ML and some processing, whether it's pre-processing or post-processing of the trajectory to smooth it out through an optimization, some collision checking to perform well in both open loop and closed loop. Lastly, we've got the closed loop reactive challenge. Here, the score tends to improve. And the reason for this is the reactive agents tends to yield for the ego vehicle, avoiding collisions, and thus improving the score. Lastly, before we move on to the presentation of our finalists, let's just compare the top three side by side. This is not listed in no particular order. If you haven't seen the leaderboard, then you won't know who the winner is, but if you've seen them, then it's pretty clear. But what I really want to point out here is it's a fundamental behavior of just coming to a stop in a dense traffic scenario. The middle one from CS2TU actually nudges to the left. It's left to avoid the lane changing vehicle. The auto horizon planner comes to a stop perfectly fine. But then we have Pegasus, which drives a bit slower, and we saw the exact same scenario as we saw before, which leads to an unrealistic scenario. Next, we have the unprotected turn that we saw before. As you know, it's a challenge scenario, but all three planners here manages to traverse this scenario just fine, all with different flavors. The main difference here is that I see is CSTU actually inches much closer to the oncoming traffic compared to the other two. The Auto Horizon Pegasus planner actually managed to go through just fine, reaching the pickup drop-off area, while the CSTU one lags behind a little bit, but at least avoids all collisions. So that brings me to the end of the new plan intro overview part. So let's move on to the finalist presentations. So the Innovation Award first, and this one goes to Team AID with the Gameformer Planner. Unfortunately, the team couldn't be here today, so I have a video from them describing their approach. There's no sound.
Output should be the handbook.
Professor Cherry. If you would like to learn more about our research, please.
All right, let's start again.
Hello, everyone. My name is Zhi Yuguang, and I am delighted to present our solution for the new plan challenge. First of all, allow me to introduce our team, AID, which stands for Automatic Intelligent Decision Making. Our team consists of myself, Hao Chen, Xiaoyu, and our advisor, Professor Chen Li. If you would like to learn more about our research, please visit our lab's homepage. And if you are interested in our solution, it will be open source in GitHub. So now let's dive into our proposed planning framework. The framework is built upon Gameformer model, which we designed for interactive patient planning. It has also demonstrated stellar performance on the remote texture vision benchmark. The planning framework has the 4 key steps: feature processing, task planning, model query, and traffic refinement. Firstly, we retrieve information from the observation buffer and map API from the U-Plan simulator. We process this data to obtain agent history and a vectorized set map problem. We then get necessary information such as roadblocks, obstacles, and traffic light states to perform path planning, ultimately generating a reference path for Eagle View. Next, we feed the processed features into the GAN-form model. This model generates multimodal jump trajectories for the surrounding agents and an initial trajectory for the Eagle View. We project initial Eagle trajectory onto the reference path, as well as most likely prediction results of other agents onto reference paths in free net space. This process yields a spatial temporal path occupants for a subsequent trajectory refinement process. Finally, we utilize a nonlinear optimizer as the planner to refine the Eagle's motion plan. This step can help avoid distributional shift or causal confusion, which are often encountered by measurement-based planners. The optimization space considers a wide range of factors, including speed limit, acceleration, jerk, final displacement error relative to the initial plan, and most importantly, collision avoidance. The final optimized trajectory is then transformed back to the Cartesian space and executed within the simulator. At the core of our planning framework lies the GAN-form model, which utilizes the concept of level K GAN theory to model the mutual influence among agents' behavior in the future for joint prediction and planning. It is a transformer-based encoder-decoder network. The encoder part uses transformers to extract the relationships between agents and map elements. The core idea of GAN-former is that we use a series of transformer decoder layers to iteratively decode the trajectories of all agents and iteratively refine the interaction prediction process using the previously obtained information from the last level. Specifically, at level 0, all agents act rather independently without the future information of the agents. And then at each decoder level K, the decoder receives the predicted information from the previous layer, as well as the counter background information from the encoder part. For additional details, please refer to our preprint archive. For the results, our planner has achieved competitive performance on the U-Plan challenge leaderboard in terms of the overall score. It also shows top performance on some key metrics in both open loop and closed loop planning tests. We also visualize the closed loop testing results on several challenging urban driving scenarios, which demonstrate our planner's effectiveness in handling complex and interactive driving situations. So that's all about our solution. Thank you very much.
So the innovation prize winner, Team AAD, came in at a score of 0.829, which coincidentally also was the 4th place of the competition. Next, we have 3rd place, honorable runner-up, Team Pegasus with a multi-path planner. Unfortunately, they are also not here today, so I have a video from them describing their approach.
Hello everyone, I'm CVPR. I'm coming from Pegasus. Pegasus is an autonomous driving company. We have an office in Shanghai and San Jose. Our method is based on reinforcement learning, utilizing data augmentation and post-processing to achieve better performance. First, let me introduce our model, which is largely based on the state-of-the-art waveform reproduction. For the input feature, we use vectorized map representation. For the diffusion encoder and neutrality, we build different types of input feature. They require attention used to reduce computational cost. To represent multimodal output, also mixer model with predefined visual query is used. For more detail, I recommend referring to the original waveform view. To improve closed-loop performance, data augmentation is important. Generally, the newly generated trajectory include path and curve states. Let's demonstrate how the equal wave reach the derealization and future states. Let's indicate how to drive back to the expert trajectory. For past and current equal states, we found that past equal states are not important in our program. The model with or without past equal states can achieve similar results as demonstrated in the right table. Therefore, in our model, the ego input only includes the current state, and random noise is introduced for data augmentation. For generating future trajectory, we try two methods. One is generating a smooth trajectory, which converges to the ground truth. This can be done by truth optimization. The other is directly using the ground truth. Both methods achieve similar results. Therefore, for simplicity, directly using the expert trajectory is a good choice. Despite using the train model with data augmentation, the planner still not work well in closed-loop scenario. As shown in this video, the ego vehicle exhibits large understeer. With closer examination, we can see that the plan trajectory is reasonable in every field, as shown in the figures, even if it deviates from the expert trajectory. However, the ego vehicle does not follow the plan trajectory exactly, and the deviation accumulates gradually. Moreover, this needs to occur with both two-stage controller and perfect tracking controller, indicating that it is not caused by the controller either, and rather comes from the neural network itself. Here, we propose a workaround that can somewhat alleviate this problem, and we hope other teams will have better solutions. This trajectory in every frame is generally okay, and the error accumulates gradually. Using a lower planning rate may slow down error accumulation. In the default setting, the planning rate is 0.1 seconds. We reduce the planning rate to 2 seconds. The video in the right demonstrates the effect. However, planner with lower planning rate reacts more slowly to environmental change and potentially leads to more collision. Therefore, we add a post-collision check. If a future collision is detected, we immediately replan. Finally, as shown in the table, with post-processing and the data augmentation, our planner performed well in closed-loop program for validation dataset. Thank you for your attention. If you have any questions, please feel free to email me.
So that was Team Pegasus, came in at 0.848 at third place. Next, we have second place honorable runner-up, Team Outer Horizon with the Hub Plan Planner. We've got Ihan here to present his approach.
Good afternoon, everyone. I'm Ihan Hu, and today I will be sharing our second place solution, imitation with spatial temporal heat map. It is a joint work with my teammates, Kun Li, Pingyuan Liang, and we are from Horizon Robotics. For overall structure, our approach consists of a neural network predictor and a set of post-processing algorithms. In form of multitask learning, the neural network predictor takes raster image and input and output the heat map, occupancy, and the initial plan trajectory. All this information is then fed into the post-processing module for optimization to generate a safe and smooth plan. Specifically, we use ResX50 as our encoder and use UNet as NAC. As shown in the image on right, we adopt an input raster with 6 channels, which capture the ego states, surrounding dynamic agents, static environments, navigation, and roadmap information. This type of encoding is simple, intuitive, and comprehensive. As shown in the image below, we represent the plan trajectory using spatial temporal heat map, where each pixel represents the probability density of ego vehicle, and each channel represents the probability of different time steps. This representation is effectively captured the uncertainty and multimodality in complex driving scenarios. Similarly, to effectively model the motion of surrounding dynamic objects, we predict the occupancy probability of dynamic objects at each time step. As shown in the video on the right, the occupancy prediction plays a key role in collision avoidance in complex and dynamic driving scenarios. For training, we adopt a multitask learning strategy and takes a weighted sum of these losses. Simultaneously, we inspired by ShuffleNet, we employed perturbation as data augmentation under the dynamic constraints. To better serve the downstream pole servers, we fused the future ego poles, future dynamic agents, static objects into a collision avoidance map, as shown in the right. Specifically, we constructed an ego kernel based on the ego car poles, and then performed convolution on the long-drivable areas to obtain the collision avoidance map. The entire operation can be implemented with convolutions, and it's run extremely fast with GPU. Then we utilize a pole server to consolidate the above information and refine the final plan trajectory. Inspired by UniAD, we use Casati IPOpt solver to find the optimal trajectory considering the initial trajectory, collision avoidance map, heat map prediction, comfort, and ego vehicle's dynamic constraints. This type of pole solver steers the trajectory away from unsafe areas and ensure the final safety and comfort. Here is our application study. We can see that the perturbation, heat map representation, and pole solver all contribute significantly to the improvement of the results. Particularly, the pole solver with occupancy is the most effective for the closed loop results. Our methods rank second on the leaderboard and achieve the best comfort and ego progress score. The methods demonstrate that our methods is good at balancing the ego progress, comfort, and safety. Since the first place is rule-based, so we could say that we are the highest learned methods in the leaderboard. Thanks for your attention. Since time is limited, if you guys are interested, please refer to our technical report for more details. Thank you.
Thanks, Yan. So the team Outer Horizon came in at 0.875, only 0.02 shy from the first place. So for our first place outstanding champion is team CSTU with the PDM planner. So we've got Marcel here to present his approach. Go on. Yeah, hi everyone. I'm Marcel Hallgarten. I'm going to present the predictive driver model on behalf of my team. And this was joint work with Daniel Dauner, Kashyap Chitta, and Andreas Geiger. So the starting point for our method was this simple benchmark that we conducted right at the beginning with some baselines that we had available, where we found that these ego forecasting learned planners perform quite well in open loop, but in contrast, they are outperformed by the very simple and quite old intelligent driver model in the closed loop evaluation. Also, we found that not even the log replay planner that has access to the ground truth future trajectory was able to achieve perfect score in the closed loop evaluation, indicating that the controller is unable to accurately track the trajectory that's output by the model. So that's why we decided to pursue a hybrid approach, relying on two separate planners. The first is our PDM closed planner that is responsible for planning the short-term trajectory based on a rule-based planning approach. And the second is a ego forecasting learned planning approach, which we call PDM open. And we came up with two strategies to combine the outputs of both planners. So the first is what we call an adaptive interpolation, where we basically infer both planners and then take the output from the PDM closed planner up to a certain horizon, and then append the output of the PDM open planner. And this cutting horizon can be either fixed or adaptive to how the deviation between the current state and the past predicted trajectory is, so it can account for the drift of the controller. The second way is to not predict a trajectory with the PDM open model, but instead feed the PDM closed trajectory also to the feed the PDM closed trajectory to our PDM open model and regress offsets rather than exact waypoints. So this is what our rule-based PDM closed model looks like. In the first step, we identify a sequence of central lines leading to the navigation goal by a graph search. Then we forecast surrounding agents with a simple constant velocity forecast and generate different IDM proposals. In total, we evaluate 15 IDM proposals obtained by 5 longitudinal IDM proposals, each combined with 3 lateral offsets from the center line. We then simulate these proposals to obtain the expected outcome of the controller and score them with a cost function that closely resembles the new plan metrics. And finally, we select the highest scoring trajectory as the output of the model. For the learned long-term ego forecasting part, we use this very simple and lightweight MLP-based model, which takes just the center line points as an input and the ego history. And we observed that these inputs are enough to accurately forecast the ego trajectory. So adding information on surrounding agent even made performance worse. And we use a very simple model for this ego forecasting. So it's a simple 2-layer MLP model with 512 hidden neurons in each of these layers. So it's very simple and lightweight. Still, we found that this lightweight PDM open model was able to outperform the baselines in the open loop evaluation, while the PDM closed model also significantly improved upon the IDM model in the closed loop evaluation. Also, the PDM open model considerably improved in runtime compared to the other models. Our PDM hybrid model then is able to effectively combine the strengths of both models, leading to state-of-the-art performance on the new plan benchmark. If you found this interesting, then make sure to check our code and also our paper. And if you have any questions, then feel free to approach me later. Thank you. Thank you, Marcel. Congrats on first place. They came in at 0.895, topping our leaderboard. Here's a quick overview of our finalists and the Innovation Award today. So some closing remarks. For future works, we'd like to improve on controllers. As we saw there, our tracker is definitely not perfect. So we'd like to see an MPC controller, something like this that can improve our tracking performance. We like to diversify our metrics. So our metrics are definitely not comprehensive at the moment, and improving it to really distinguish and discriminate between good from great planners. As you can see also from the finalists today that the scores are already saturating the top end of our scale. So being able to stretch that out and really depict good from bad planners would be very valuable. Next is to improve on our reactivations by employing some ML policy to increase realism and also simulate more diverse and simulate the long tail problem as well. We've been asked about RL training a lot. Yes, we can look to implement some gym-like simulation, and more importantly, apply some offline learning, offline RL using our data set. Lastly, now that since we have the sensor data released, we can also look to do some end-to-end planning challenges as well in the future. If you're interested to keep track with us, keep up to date, please visit newplan.org to download our dataset and check out our dev kit at github.com/motional/newplan dev kit. Quick thanks to Shanghai Artificial Intelligence Lab and Mars Lab for organizing this workshop. Quick special mentions to Dimitris and Holger for helping set up and run the challenge, Hongyang Li and Hang Zhao for inviting us to be part of this workshop. The workshop organizers themselves, of course, for setting all this up, the challenge participants for making the New Plan Challenge happen, And finally, the team at Motional, New Plan team. This will not be possible without you. This project has been 2 years in the making, all the way from data collection in 2021 up until building up the dev kit and now concluding the competition here today at CVPR. Lastly, we're hiring. We've got sites in US, Singapore, South Korea. We've got on-site, hybrid, and remote positions. So if you're interested in what we're doing here at Motional, whether it's New Plan related or otherwise, please visit us at motional.com/careers. Thank you so much for listening. Have a wonderful rest of your afternoon.
Great challenge organization, and next we'll have Yuning to give a presentation. Yuning is the head of AI research at Boost. Prior to that, he was a staff research lead and manager for the center prediction team at Waymo, dealing with statistics.
Yeah, actually, there in the title there wasn't a question mark. The question mark was a mistake in the communication. So we are doing it. So it's not a question. All right. So this is Chai from Cruise. Very excited to be here. And before I start, I'd like to thank the wonderful organizers of this workshop for this opportunity to speak here today. For this talk, I thought we'll discuss a few things. Namely, I'll talk about a few projects that we've been doing at Cruise Research, and I'll also highlight a few directions that I like to have the academic community and the industry community moving forward as far as self-driving is concerned. All right, so just for our international audience, just a few words about our company. We are a company based in San Francisco. We specialize in building self-driving cars for ride-hailing and delivery services. And has been, the company is about 10 years old. And we are, so here's a short video. I'll just play it here while keep talking. So we actually deployed a self-driving fleet and operation in San Francisco and beyond. And as you can see, we can handle very complicated situations in San Francisco. I think for one of you who have been in San Francisco, especially during nighttime, is a complicated, it's a lot of interesting things happening in San Francisco. And the fact that we have an operating fleet in the city speaks for itself. And so I also wanted to talk a little bit, just a few words on how we are thinking about scaling the self-driving car operation. So again, right, we started in 2021 with just 2 cars covering about 30% of San Francisco, and we were mostly operating during nighttime. And then around CVPR time last year, we scaled to 10 self cars covering 70% of San Francisco, we were still constrained at nighttime, but then already at New York's time, we scaled to over 100 cars covering most of San Francisco during nighttime and somewhat during day as well. And back then I said, okay, hopefully we'll be covering the full San Francisco soon. And this is indeed the case. If I were to, can I move this thing, this block here to somewhere else? Yes, perfect. So that's indeed the case. If we look at, where we are now. So we are in 2023, June, we have, hundreds of cars driving in San Francisco. If you were to visit San Francisco, maybe after this workshop and conference, you'll see our cars driving in San Francisco. You'll find many of them. And we've also scaled to other parts of the US. It's Phoenix and Austin. And we also always had the belief, if we were to be able to tackle San Francisco, the other cities in the US are a lot easier to handle. And that turned out to be indeed the case. In Phoenix and Austin, a lot of roads, they are much wider, fewer pedestrians, fewer bicyclists, and just a lot easier. So we were able to scale really well. And yeah, I think I just want to remove this, and we are okay. Now it's on the left side, so I really can't. Oh, much better. All right. So and we are doing it at 24/7 as well. Okay, so last slide here, we are now looking at new expansions in Dallas and Houston, and those are some of the largest cities in the US. And we are also looking forward to deploying in international markets such as Dubai and Japan, and deploying our customly built hardware that's just for the self-driving car application. All right, enough about the company. I'm pretty sure you folks are here to listen about technical details rather than business. The next few slides, I just want to outline a few kind of research opportunities I see for the research community here and also our industrial partners. So to understand that, we need to look at how the self-driving car industry moves forward. And I think this slide not only applies to us, but it also applies to a lot of other self-driving car companies, right? Beyond even the ones working on L2 and beyond. So essentially what happens, you have some kind of self-driving car stack, you put it on road and you gather problems. And that's where you see, all those safety drivers in the cars, they gather problem, they make nodes. And those nodes, they go into kind of a database. People then, engineers will then work on problems, and then they create solutions, retrain models, and redeploy models. So this is, a typical iteration of the self-driving car stack. So then the question is, these days, what are some of the hottest areas in machine learning? I think today we've already visited many of them. I think it starts with foundation models, also generative AI and so on. So I think obviously there's a lot of opportunities to use foundation models to optimize this pipeline, and it starts with reusing some of the existing foundation models, like public available ones, like CLIP, like SAM, where you have a model that has seen basically the entire internet. And there are many ways to leverage those. And in particular, I want to point out in terms of auto labeling, right? When it's kind of expensive procedure that you can use, some of these existing foundational models to do auto labels. But at the same time, you can also try to build your own foundation models. And I think today we've seen a few examples. We've seen, I think, Wave has pointed out in this Gaia work, and I think, Sergey talked about their foundation models as well. So then here's also the aspect of generative AI. I think these are very correlated, right? Here we talk about diffusion models, we talk about autoregressive models, that's like GPT style models. And we also talk about even more traditional ones like GANs, like VAEs, they still have a lot of value here. So you can use those for, for example, training data generation, especially if around long tail problems. And you can also use them for testing. I think, as we heard from the previous talk with the new plan challenge, the evaluation of planning modules is still extremely difficult. It's still, if you want to get the diversity, you need to find counter factual outcomes for your planning stack. So all these generative models will be very helpful here. So finally, we are at the end-to-end workshop. So I also wanted to just give a shout out for kind of end-to-end solutions. I think it's not a secret that a lot of that end-to-end solution. There are a lot of companies, a lot of more mature companies that use like a more modular stack. But I do believe end-to-end solutions, they do have a place in the self-driving car stack, especially if we want to target particular maneuvers and functionalities that are maybe difficult to build and difficult to scale if you were to do it modular. But having mentioned all those opportunities, I understand that we've already listened a lot, listened to many talks addressing these three topics before, over the course of today. So I wanted to give another perspective. I want to talk about like two areas that are a little bit orthogonal to the three areas I mentioned before. So, and those have not been targeted. So on this graph, that have not been targeted by the other ones, other topics before. So one is around testing. So we talk about this workflow of finding problems and then tackling them one by one. But this is, when you think about it, if you really want to scale, this is not really a scalable approach. So you're essentially driving around and you're waiting for problems to happen, and then organically, and with the hope that if you fix all of them, you'll have a very safe solution. But the challenge here is, we are all working on long tail problems, and this is essentially, it's endless. And moreover, the world is an ever-changing place as well. So you'll always have new challenges coming up. Maybe it's because, like a new trend on TikTok that suddenly happened, and suddenly, everybody will dress up differently. So the question here is, can you find problems or issues like in a more proactive way, rather than waiting for them to happen? And note, this is orthogonal to everything we talked before, because here, this is about recognizing and proactively recognizing problems that will happen. All of those topics we talked before, be foundation model, generative AI, they still apply once you recognize what problems you are facing. And the second topic I want to mention is, machine learning models don't have infinite capacity. You can do, and we don't have infinite data in our storage. We do collect a lot of, all these self-driving car companies. We have a lot of data, but you can't store all of them. So what do? The answer here is continual learning, and I'll talk a little bit about that too. All right, let's dive right into them. Let's start with motivation. So this is, again, a video. I'll just play it in the background. It showcases all the challenges of, at least a subset of challenges we've seen in San Francisco that are somewhat long tail situations. And these are things that we have to deal with in San Francisco. Essentially, the question here is, it's great if we know that these exist and then we can tackle them. But the true question is, how do we get aware of these? How can we tackle them before they happen, before they cause us problem in the first place? Right. Perception side as well. So that I generate scenarios that will challenge our perception system. So we can start with a kind of baseline object that we can mine on the road and where our object detector has no problem with. but then we have to modify it in a way to another object that will cause problems to the object detector, and while keeping the object human interpretable as well. So, just very related work, right? I mean, this really reminds us of the adversarial sample generation literature that has been around for at least 10 years, where the idea is you have an input, in this case was ImageNet, you have an ImageNet image, and you have a differentiable system, and you have a loss at the top, and you can compute the gradient from the loss with respect to the input image instead of the weights, and that gives you this noisy image that you can append or you can add on top of your input image, and suddenly the network will say, okay, it's a cat. So this is great, but it's difficult to use it one-to-one in a self-driving application. So this is equivalent to saying, okay, here we just modify, we have this point cloud scenario, we just modify a few points here and there, and suddenly the entire perception system fails. But this is not particularly useful. Think about it. You give it to like a perception engineer. What are they supposed to do with this? They just look at this, okay, this is very overfit sample of their system failing. So it's not particularly helpful for them to understand the weakness, the true systematic weaknesses in their system. So what we came up with is essentially to say, okay, we need to regularize a lot in this pipeline. So if we were to do, the traditional adversarial generation, it would be just like this part. So the right part, right? You have a detector that's differentiable, you have an input scenario, and just propagate the gradient back. But you have to do more than that in order to make the system useful for the perception engineers. And well, the answer is just to regularize the model in several ways. So one way we found out was to just make this scenario compositional. You can compose this scenario. So you still have a concept of, here, what is a background? What are the active agents? And where is the self-driving car? So that certainly helps with regularization because it projects the entire scene into a lower dimensional space. And the other regularization is in this shape, right? So we still need to have shape, like an asset to render in the scenario. And if you just take the assets as like a bunch of point clouds or meshes, it will still overfit. You'll just have small changes in the assets, and that will fool the model, the detector here. So basically, we need to rely on a much lower dimensional latent encoding in order to regularize the model. All right. So and then the challenge is once you have this structure, the next challenge is, okay, this entire thing needs to be differentiable. And how do we do this? We rely on some existing works. So here is a prior work called deep SDF, so sign distance function. And what it does is it trains a function to represent the asset. So when you have like 3D assets, you can represent as a mesh, and represent as voxels, or you can represent a function. So we found that with mesh and voxel, it's difficult to make a differentiable. But if you have a function to represent the assets, it's kind of naturally differentiable. So the beauty here, right? You basically need to train these assets, like given a bunch of point clouds, you can now train this function that represents this rabbit here. It's differentiable, watertight, and it's very easy to render this object as well in a differentiable way. So yeah, exactly what we do, right? You have a car, you train the SDF function on top of this car, and the SDF essentially says, okay, given a latent code and given a point in space, 0 would mean that like a point that's on the surface of this asset will have the value 0. And I think if it's positive, it's inside the object. If it's negative, it's outside of the object. So then what you can do is you can encode. So then the next thing you need to do is to render this car from the view of the self-driving car. And the rendering parameter, you can just play with the calibration. It's essentially rotation translation, right? Or essentially linear transformation that you can apply to the rendering parameter theta. And we can do some simple ray tracing here. So for example, a point, that's outside of the car, you can just reuse it from the existing log. And if a point is somewhat occluded, because you get this from the function that we learned before, you can then replace the occluded points with the points that's on the vehicle. So now what we can do is to insert objects into a logged scene. So this is a scene that that we have in the data set. And now you can easily render this object in a differentiable way anywhere in the scenario. So it's important it's differentiable for the adversarial generation procedure that we'll do later. Okay, cool. So now we have the entire pipeline figured out. What now to do is to optimize compute gradients of the loss with respect to the shape encoding Z and the pose encoding theta, and then you can find adversarial samples that are helpful for the perception system. Yeah, exactly. So you can generate shapes that will drop your accurate detector accuracy to 0. You can also find poses that will. So by poses, we don't just send a car like to the outside of the range of the sensor. That would be too easy. So even for pose changes, we just keep the object where it is and just make small changes in rotation and translation. So yeah, here is, for example, an original asset that we can then that's easily that can be easily detected. And then we can use this method to generate something that looks like a convertible. And obviously there are still challenges in, there are still questions, okay, how realistic are these? There's no windshield, there seems to be a hole here. But overall, it gives engineers a direction what to look for. For example, here, in San Francisco, there aren't many convertible cars. So, this basically points the engineer to a direction. Okay, we might have some trouble if we go to a place where people are super rich and everybody drives a convertible car. All right. So, and now the beauty here is also that you can apply the gradient at different levels. So you can, gradually, because the gradient is essentially a direction that you walk on in this latent feature space. So you can apply it at different degrees. For example, you can, so essentially that can help you to generate a gradient of different assets, and they, one after each other, they will just achieve lower and lower scores for the object detector. So I wanted to reemphasize the results shown here are not based on our production model and the production object detector. So this is reproduced on a benchmark data set, on set of benchmark data sets, and using a publicly available detector. That's certainly, hopefully that's good than our own. So here are some examples of, you can take an SUV, you can apply this method on a particular scene. And for example, it will give you kind of human interpretable weaknesses in this procedure. So we see like objects with smaller windshield, the detector has some trouble with it, or anything that's more sporty, but still looks legit. The detector also has problems with them. So the same with the shape, you can do this for poses as well. And here we just simply rotate the object, and already the system has started to have some trouble detecting object. So here again, right, same thing as with shape. So you take an asset, you place it somewhere in the scene, and where you get a very high detection score. But now just by playing with the simple like rotation translation parameters for the asset, you can find weaknesses on your detector. I think usually there's no question that, the detector is supposed to detect these objects, even if they're just rotated slightly and translated slightly. All right, so here are some quantitative results. So this basic attack, this describes attack success rate. So essentially what, so in each of the graph here, I know it's a little bit small to see, I'll just quickly describe it. The upper curves show the accuracy of the detector on the baseline objects, and the lower ones show the accuracy of the detector on objects that we've adversarially tuned. So then there's also the question of fidelity. And here, the experiments we conducted was to just add the generated objects as additional training data, right? If they belong in the same distribution, you expect an increase in accuracy once you do that. And this is what we observe as well. So we have baseline. So the blue line here is a baseline curve for on kind of the baseline objects. And once you fine tune the detector with the generated data, you get the green line, which is a somewhat improvement. And then the orange line is the accuracy on the generated data. And if you obviously fine tune, you see a much larger improvement. All right, so much to generation and adversarial finding problems proactively rather than waiting for them to happen. The next topic I want to touch on is continual learning. So here, the question that we all face quite frequently for the self-driving car industry is that you have to keep changing your model for new tasks or new ODD. So those are just when you go to another location, you have to include the data from the new location. You have to retrain your model. So this is, and you need to not forget the old data either. So we go to another place, you need to be good at the new place, but you can't forget what you learned at the older place either. So there are a few ways to do this in the literature. So one way is called multitask learning. So what you do is to simply add new data to your old data and you train your model in a multitask way. The problem here is that this is, it is very difficult to tune this system because you have to have a really great balance between the old and new data. And typically the new data is so small, tiny, that essentially you don't end up with any change. And that's not great. You have to, one way to do it is just to reweight the new data, but then you're in this regime of really careful hyperparameter tuning. So the other way, the more sophisticated way is called model anchoring. And here what you do is to take your, so you compute some statistics from your new data on the old model, and your objective becomes, okay, fine tune this model while not moving too much away from the old statistics. The problem here is that it doesn't scale well if you need to do this fine tune multiple times, and it has a high, it requires extra engineering as well, because you need to compute all these statistics and then set it up in your training pipeline. Now, basically, these are all complicated. So what people end up doing is just the simplest thing, which is to fine tune with your new data with a lower learning rate, and then cross your fingers that nothing is going to blow up in our faces. Now, so the traditional fine tuning is fine, but here I'll outline a problem that essentially the forgetting problem. So you start with a pre-trained checkpoint on your old data. You take your fine-tune steps here, 1 to T, and now you are at this new checkpoint. And the next step you want to do is, for example, going into this N+1 step. So you'll notice this is the source of essentially the forgetting problem, right? So you're kind of moving. There's no guarantee that you will stay. So this pre-trained checkpoint, let's assume it's pretty good on the old data. It's already fit on the old data, somewhere in a local minimum there. And essentially this leads to forgetting because there is nothing that prevents you from just moving away from your old, a checkpoint that work pretty well on your old data, right? So this looks like a past learning problem again, right? Where you have two objectives, two gradients you want to pursue, and what you can do is you can, so there's a kind of simple trick here that's well known, where you project the gradient from one to another, and that's the direction that you go. Now you might ask,
okay, we are going back to multitask learning. So how is it different from what, this thing here that we said we don't want to do? So the main difference here is really that you don't need your old data. And that's very critical for self-driving. You don't want to store all your old data forever. So in case you want to fine-tune your model, you have to kind of use the old data again. So essentially what we did here was to trade a few steps. So I mean here, the cautious of you will notice that this is a little bit more expensive than before, right? You have to take n steps in order to take one step. So essentially what we did was to trade the fine-tuning efficiency against the need to store data. But typically, if you do fine-tuning, you don't need that much fine-tune anyway. So that's something that we are typically willing to sacrifice. So just quickly on the results, we have here a toy example where we are trying to fit a distribution, a two-dimensional distribution, like original data, new data, and we want to train on this new data without forgetting. So in the end, we want to model this full data set distribution. And if we were to do it on original data, we get something like this. And you'll see that fine-tuning on head only or the full model will give you something substantially worse than what we get with our fine-tuning approach. So which is also reflected in the quantitative measure. So we applied this on some other benchmark task as well. So this is CIFAR. This is a CIFAR variant that's targeted for long tail distribution. So there are a lot of, there's a huge label imbalance in the CIFAR example. You have the old task. So we decided to just treat the common classes as the old task and the long tail classes as a new task. And in that way, we have this kind of continual learning setup with long tail classes. So what we can see is, we also played with the imbalance ratio, which is how tiny the long tail classes are compared to the common classes. And we see consistent improvements over all kinds of fine-tuning approaches that people typically do. Now, the last task was self-driving. I mean, we're a self-driving company, so we have to apply it for self-driving applications as well. So here is a prediction task where the old task is to do motion forecasting on vehicles, and the new task is to do motion forecasting for pedestrians. So we want to train one model that does both at the same time. And we first trained it on cars, and then we wanted to extend it to pedestrians. And again, we see kind of consistent improvements of this. So the baseline here are the fine-tuning baselines, and good fit is the model that we have. So the cars would be the performance on the old task, while the bottom ones are performance for the new task, and we can see consistent improvement as well. All right, so just to wrap up today's talk, so I highlighted a few. First, I highlighted a few research opportunities for industry and for academia. I hope to inspire some of the future works from all of you. I highlighted 2 works on proactive risk mitigation and continual learning. And I think there are still a lot of challenges. In particular, I really like the line of foundation model and generative AI. And the challenge I see here is that people typically talk about precision. So when ChatGPT gives you a result, you just look at, is this feasible? Does it make sense? But there's a lack of study on kind of model distribution. So people don't question, okay, what other explanation are there? I think, Alex earlier talked about a few examples where he asked ChatGPT how to drive. Actually, we've tried that too. And a lot of times it doesn't give you the right diversity of answers. So I'll wrap up here. We're still hiring. And if you want to tackle some of these challenges with us, we'd love to hear from you. All right, thank you.
Sake of time, we will take one question. Yes.
Thank you for your presentation. Give us the practical situations. May I ask you a question? Because right now the car industry, they are thinking about the software-defined vehicles. So is any particular situation you need to think about the different structure? So how to use the traditional data to fit in the new structure?
Sorry, may I clarify a little bit? What does software defined?
Because
structure?
right now they use the like as before they for the automotive electronics they just use ECU, so they can 1-to-1. But right now they are going to another structure, so domain structure. So if they use a domain structure, maybe they use 6 domains. So one is for the navigation. So I don't know if we use a domain like a traffic situation. So they will use this kind of data to fulfill the real situation for the new cars structure.
Are you asking how we are trying to extend to multiple platforms or?
Yes, because you mentioned about we need to use a new structure data, but how can we collect because we accumulated the traditional data for a long time. So if we want to fit in the new car structure, so is any particular things we need to solve the traditional data structure going to the new data structure?
There's probably some domain adaptation and sim to real situation to handle. But overall, I think it has been studied before, and this is something that we can all try the baselines on first.
Okay, thank you.
All right, thank you.
All right, let's welcome our panelists to come to the front, and we'll start our panel discussions.
One more.
Can we turn on the projector?
Oh yeah, of course.
All right, welcome everyone, and welcome our panelists. Before our panel discussion start, I will briefly, introduce our panelists again. And we have Professor Sergey Levin from UC Berkeley, and we have Professor David Remnant from CMU, and we have Alex Kendall from Wave, who is the CEO of Wave. And we have Yuning Chai from Cruise. Yeah. All right. So now we will start our panel discussions. The form of our panel discussion will be, we'll prepare a few questions to ask our panelists, and then we can also have our audience to ask a few questions that which you believe that is important for self-driving vehicle research. All right. So now let's start. The first question is related with our topic, the major topic today, end-to-end autonomous driving. So as we may know that most of the product system now still is based on modular autonomy pipeline. So may I ask, what's your opinion about how far are we from fully deploying end-to-end models in real-world driving product? Could we entirely get rid of modular pipelines in future? Who wants to take the question?
Sure, I'll take this. Hey, so I think what I showed in my talk and what we'll be able to show at Wave with end-to-end learning is I think it's really stretching the boundaries of what's possible in autonomy. But just to ground ourselves on where we're at today, I'd call us GPT 0.5. We are, we are just at the beginning of this journey. I expect everything we're seeing, there are parallel results in end-to-end learning for driving that you tend to see when we've scaled up machine learning applications for other areas. Like, let me reference the GPT example again, and I expect we'll see similar results as we scale up the size and capacity as well as the data. I can't think of a reason why there would be a glass ceiling for this approach. I certainly wouldn't be betting against machine learning problems today. And if there's anything I think the last couple of years should be teaching us is that these methods are by far the most powerful at solving really complex high dimensional problems. If you have those foundations of data, a fast feedback, an effective feedback signal, and sufficient compute, I think we're getting close. Would anyone like to follow?
Yeah, I guess, I mean, maybe I'm biased, but I still feel like I guess I am biased for being a vision person, where I think most of the challenges from my experience somehow are perception related. So from that perspective, it seems natural to me to kind of focus on that with more sort of aggressiveness. But it's true that this kind of believe that the trend of even in the perception stack, it tended to be like highly modular to little pieces. First you would detect, and then you would track, and you forecast, and it seems like maybe there's ways we can make that more end to end. So I guess it moves in this direction that it seems like integrate everything makes a lot of sense, but at least from my time in sort of actually in industries, it seems super important to have not just a solution, but like a slight there. So my guess is it's going to be like gradually becoming more end-to-end-ish, if that makes sense. Go for it.
I think I might be the least qualified on this panel to answer this when it comes to actually deploying things, since I'm, not in the business of deploying autonomous driving systems. My sense is that for navigation that is not driving, like for example, sidewalk robots, that sort of thing, like the kind of stuff I showed in my talk, I think that's very, very close. But I think that the driving stuff, my somewhat uninformed opinion is that it might be tough, not so much just for technological reasons, but also partly for like kind of pipeline engineering culture reasons, in the sense that like, any autonomous driving system requires a lot of work, a lot of engineering, regardless of how it works. And there are good engineering pipelines and good engineering teams around kind of the more modular method. And it may be that the end-to-end stuff, well, maybe in the long run, it's easier and better and has a lot of benefits, but it doesn't dispense with the need to have solid engineering and all that stuff. So if I had to guess, and my somewhat uneducated guess on this would be that it may actually be that the barrier is like developing all the right kind of engineering discipline kind of stuff around the very different way that we have to work with end-to-end things. But that's just a guess.
All right. So yeah, I think as I had a slide talk about this before. Yeah, I wouldn't bet against like end-to-end system either. I think there's certainly, even when we look at today's stack, even for the major players, right? I mean, again, right, this is no big secret, as you said yourself, right? This is a lot of players still use a more modular stack. I think when you look at even now, there are situations, unfortunately, I can't share more, but there are situations where an end-to-end stack is certainly more appropriate. And I think this is something that, and I think with time, it's possible that for a lot of situations, an end-to-end stack is perfectly fine. Although having said that, I'm still worried for, like if you work in this domain, if you see all the long tails I talked before, and as we know, machine learning models are really not good at long tail situation. They're really good at modeling the general.
Another question is related with today's hot topic that is called a word model. It's very surprising, not surprising, but it's really fantastic to see quite a few talks that covers the word model. And we are trying to perceive our word and understand its dynamic behaviors within it. My question is related with, based on different talks, we see different form or different representations of our word. There are some of the word model leading towards more explicit, interpretable representations. Some are entirely neural network, which is implicit. My question is whether explicit representations is necessary, because whenever we have an objective function, we basically distort our focus towards, distract our focus from, active data, right? So I'm wondering whether you have some insights towards that.
You can start. Oh, yeah, you start.
All right. One of the questions I grappled with for many years was, if you're building a scene representation, should you use a global representation, an implicit representation, or should you have a representation on a per object basis? You could think of a vector representing the whole scene or a vector per object. And, if you are able to discretize the world into objects, it can be much more efficient to explicitly represent those. I think when you start to again get to the long tail and self-driving, one of the challenges actually in discretizing out objects, the thing that's been really interesting for me to watch, if you look at the more modular based self-driving stacks, particularly the vision only stacks. We saw some presentations today on those approaches. There's been this transition over the last few years from, the battleground a couple of years ago was really who could build the most robust cuboid detector for around objects and lane line detectors. And then once you have those two, then you can put a planner in place. The work we've seen presented today from some of the talks was who can build the best voxel occupancy detector. And the reason being that voxel occupancy is more flexible than cuboids. If you're opening a car door, or if you have an articulating truck or something like this, then you can represent them. And so there's been this push to more and more flexible object representations. And if you move to, say, a vectorized representation, then it can learn whatever you want. I think that's great. But ultimately, there's going to continue to be edge cases. And so while I think for practical reasons, perhaps a hybrid method, or, if you look at our world model KO1 that we presented today, a lot of the scenes are, when you explore them, they are very consistent. The static world, doesn't change. And so representing the static and dynamic world and focusing more signal, in a foveated way on the things that move that are really more interesting to model, might come with benefits. But at the limits of compute and data, I would argue that if you take away those engineering hurdles and as this scales, I do think an implicit end-to-end representation will win out. It just might, a hybrid solution might be a shortcut to get there.
Yeah, I think my answer to this would be somewhat similar to Alex's, actually, that basically representations for prediction are really, really important. Like we know from psychological studies on humans that people's representations are dynamic. They change with the tasks they're trying to do. They focus on things, ignore other things. And it seems kind of strange that if we want to do, if we want to use learning to, let's say, like acquire a perception system, because it's difficult to do it any other way. Well, if acquiring the right representation for things like prediction is such a complex and tricky problem and such an important one, shouldn't we be using learning for that as well? Shouldn't we be figuring that out from data? And I think there are many different ways that could be approached, right? So we could imagine just like directly predicting raw pixels. Even then, there's choices to be made that affect representations. You could, for example, you would get one representation if you try to predict outcomes of different actions. You would get a different representation if you try to predict the outcomes of different closed loop strategies. A very simple example is if I gave you a sequence of motor commands, like literally like nerve activations that my body was going to execute for the next 2 hours and ask you where I'll end up in the world, that would be a very difficult prediction problem. But if I tell you that I'm trying to go to the coffee shop at the corner of that street and that street, and I ask you where will I be an hour from now, well, you probably have a pretty good guess, right? So and that's just on the strategy layer. Then there's the question of what you predict, whether it's pixels, whether it's locations, whether it's something more implicit, like the information that is necessary to take some future action. And all these things will affect representations. I think there's a lot to explore there. I think we can likely acquire much better representations that way implicitly than what we could design ourselves.
Got it. Maybe I'll throw in one more kind of I guess color to the discussion, which is it does seem like maybe one bet that I'd be willing to make is that I would suspect the representations have to have sort of some spatial structure and have it be some form of 3D or 4D. And maybe I would state that because it seems like while the world does have spatial structure, and the world does have temporal evolution in time. And so one of the questions I wrestle with is that, do humans have sort of metric spatial representations? And there's a lot of evidence that that's not really the case. And so maybe there's a way of doing this without going all the way to this explicit, metric reconstruction of what's going on. But it feels like right now, to me, that's such an attractive way to pursue, because while we have this, revolution in data-driven self-supervised learning, which I think, very naturally applies to temporal sensor streams, we also have this revolution in 3D modeling. And so it feels like it's so natural to try to integrate those things in, because the current stacks we know are all, very fundamentally have 4D explicitly encoded. So it seems like that's such an attractive way to try to go forward.
Just ask a question. Do you think there's a need for metric space reasoning? Because in navigation, for example, a lot of it is simply topological. Like in driving, you don't care about, is that car 5.38 meters away? Is it there? And
yeah, no, I completely agree. So I sort of wrestle with this as well. Like another example I always kind of try to self-intuit is, all right, so how does a dog navigate? I don't think it's doing metric scale reconstruction, but at that level, it seems like it's much more about sort of motion and flow and time to contact. And so it could be that those are representations that are more natural rather than metric scale. So that's why I leave the possibility open that if you do something truly data driven and learned, it could be those things emerge. I guess it's more of a practical bet that I would make now, just given the tools that we have available. Yeah.
Can I ask a follow-up question?
Yeah, go ahead.
Alex, sorry. Maybe one thing there is we still want to inject some information, like if someone is doing it first time, well, then we take one. We don't have a way to prove that learn behavior. You're not going to drive out but if you can inject some information, maybe I'll give an example of the safe that probably I would try that. So things along those lines. Probably in interaction with the network representation and the injected information, it needs to somehow happen at some level. Maybe from that perspective, still those are explicit representation or we need to find the other way, like in injecting the explicit information in a left way, so they interact in a more interesting. So what are your thoughts now?
I think something that I think multiple speakers here said before is something to the effect of, like, in the short term, explicit representations seem more approachable than in the long term. So I think definitely in the short term, I would agree with you, but I think that longer term, it's not at all clear to me for the following reason, that I think, like, clearly safety is very important and it's a major challenge for learned models, but at the same time, it seems like many of the trickiest cases in safety have less to do with imposing well-understood constraints and more to do with grounding constraints in messy edge case situations. So you could say, like, well, you have a constraint like, the car should not geometrically intersect a pedestrian, like a pretty obvious constraint, right? The trouble is that you might be in a situation where understanding what is a pedestrian or whether you're about to hit them is itself the difficult part. So it's grounding the rules, not describing the rules. And if we need the most powerful and most generalizable model we can get to ground those rules, it seems pretty likely to me that in the long run, such a model would actually kind of be powerful enough that we wouldn't need the explicit part anyway. I'm not sure of that. I think this is kind of a guess, but that's why it's not at all clear to me. Exactly, because I think that the toughest cases for safety are exactly those that nothing else can solve anyway. So we need the most performant thing possible to address those. And if that's going to be a learning thing, well, then it's got to be implicit.
Yeah, I just wanted to add, first, I totally agree with, the rest of the panelists here. Just one thing I wanted to add is that the world model we're building for self-driving needs to be application driven. It varies a lot whether we are building this for model test for validation of our stack versus if we were to do it for training. For example, for validation, you need the interpretability. Maybe something explicit is more suitable, right? Or if you don't, then, well, the only chance you have is to train a model to interpret your word model. And then, we know that this model can hallucinate and all this stuff, and this might be difficult to deal with as well. But if we were to do it for training, we might just want to optimize for, the gain in the model itself. Say we have another way to evaluate the system. So ultimately, I think we just need to be really, be careful, what we're aiming for, whether training or evaluation, whether we are trying to improve the end-to-end system, whether we want to train offline reinforcement models. So, depending on the application, we'll need different things.
Great, very insightful discussions, and it's great to see we have different opinions. And the next question is also very exciting because that really brings new opportunities to the domain of self-driving. That thing is called foundation models. In today's, talks, we have seen very different form of usage of foundation models, starting from generative AI to large language model to help driving, to foundation models for multimodality word modeling and so on. So I think this is actually a one opportunity for our panelists to share their research philosophy about, what they believe about, foundation models for self-driving, what is the killer, usage or killer applications for us to be able to push foundation models in self-driving vehicles. And that will be also share some, insights to our grad student to come up with the next wave of ideas. Yeah.
So I'll start first this time. So yeah, I talked a little bit about foundation models earlier, and I think I still struggle a little bit. I think there are certainly foundation models that we can use as it is today, right? We talk about CLIP, we talk about SAM and so on. I think I personally struggle a little bit more with how to deploy them directly to self-driving car. I think maybe Alex has a different view. We also try to ask ChatGPT how to navigate certain situations. I remember we had a construction scenario. We asked ChatGPT, what should we do next? ChatGPT said, wait for the construction to finish. Well, it does solve the problem to some extent, but then it's very difficult to kind of, constrain. I know there are a lot of work on kind of query engineering and so on, but it's still very difficult to kind of constrain and to have it produce something that the planner can then understand. For me, the most exciting thing about foundation model is really the journey. When I look at the GPT literature, the journey that they took from GPT-1 all the way to GPT-4. And I think this is fascinating to me. They started with a very simple model, right? When you read the GPT-1 paper, start with it. They identified they had to work on scaling law, right? Identifying that, and then to predict how much will we gain if we were to further scale our models, right? This step-by-step evolution is what really inspires me personally, and this is hopefully something that we can. It's kind of almost like we can obey to this evolution as well.
Sergey, how did you define a foundation model in your talk? I think you called it a really big or a really awesome model. Very good model. So under that definition, I think there's a really important use for foundation models in self-driving. Just make them better and bigger.
What's the data? And so How do we wrestle with that? And so that's one place where, so I guess current text-based foundation models are trained on trillions of words. I don't think we're there yet for images. I think people are trying, it's just difficult to pull off. So then the sense of, can we actually do that in terms of sort of driving, streaming sensor footage, I think is still an open question. So there's that aspect. And I think that's also one of the really big difficulties with end-to-end as well. Because then if you really have to validate that at that scale, that seems like a big challenge. So one approach that we're sort of thinking about is maybe the right way to deal with the sort of safety issue is it's almost more of a data characterization approach. Like sometimes it's even described in terms of an ODD, an operational design domain. So this thing has been trained on these kinds of weather conditions and these geographic locations, and so we'll issue a certificate that it can work in these conditions. But then what's interesting about that is I think that certificate is somehow human interpretable, maybe even with language. It's a characterization of where this thing can be trusted. So I think that could be an interesting place where these kind of multimodal models that have both sensor representations as well as language ones that are interpretable. So that might be useful for even like making a safety case.
I think the other panelists have said a lot of things that I was going to mention too, but I think I want to zoom in on the language model stuff because that's maybe like one of the fuzziest and perhaps most tantalizing, but also most unclear places where foundation models can make an impact on autonomous driving. And I wanted to say something about robotics in general. I mean, autonomous driving is, of course, a robotics problem, but I think this is a general statement about the interplay of robotics and foundation models that maybe to kind of torture a JFK quote is maybe we shouldn't ask what foundation models can do for robotics, but ask what robotics can do for foundation models, in the sense that the places where these language models really seem to struggle are exactly these like very grounded, very physical things, counterfactuals, longer horizon planning type problems. These are all the problems that we encounter when we start working on robotics challenges. And perhaps what we should really be thinking about is how to develop better reasoning and sequence models that are everything that language models are and more by incorporating embodied experience, which should really be possible. In some sense, if you imagine how a person solves the problem, maybe at some level you solve the problem with your notion of intuitive physics by thinking about, how things look, how they move, or maybe you think about it in terms of semantics, and you kind of go up and down those levels dynamically. So if you want to, build a tower out of blocks, maybe at some level you see it as a grounded physical problem with divorced from any semantics, but then maybe you remember that like, hey, maybe the metal parts are slippery and that's a semantic fact, whereas the wooden parts are less slippery. So maybe you'll use the wooden parts because they're less slippery and they'll stay together better. So we use all of those layers, and perhaps robotics problems give us an opportunity to study these kinds of very deeply multimodal foundation models. And I think driving is a particularly appealing setting in which to think about that because it's one of the settings where there is ample data. Certainly like folks here might say, oh, hey, we don't have enough data, but you guys have way more data than any other robotics field. And certainly in terms of the number of cars there are on the road, like, hey, if using lots of data was the thing to make multimodal foundation models work, probably the driving domain is much closer to enabling that research than anything else.
I think the trillion data point question is an interesting one. I guess my question would be, what percentage of those trillion data points is going to be driving video data? I think that if you then consider internet scale, language and imagery can be part of that. If you consider simulation and synthetic data, I think that trillion data point number becomes a lot more realistic and feasible. I expect that's the way we'll go.
Right, speaking of data, so I do want to ask another question regarding simulation. So simulation seems to be perceived to be important in self-driving vehicles. I just want to ask, the panelist opinion about, how simulation could be playing in critical roles in the self-driving stack, whether it's more like providing tons of, training data or actually using simulation to validate some of the cases that we might not be able to validate in the real world. Which one is more important, and whether, we should push forwards more, leveraging real data to build a better simulator. Yeah.
Well, I guess that's $1 million question here. So yeah, I mean, you phrase it as if we are not using simulation. I think a lot of players these days, we are already using simulation to, I mean, for behavior evaluation. We listened to Motional earlier. You need simulation to be able to evaluate. Otherwise, other agents are just either on rails or you have an open loop evaluation that's just unreliable. So it's already playing a critical role. The question is not when. The question is how much can we extend it, right? I think there's a question on do we really need simulation to, for example, to generalize to long tail, like really find long tail cases. That's basically what I talked about earlier. And I think definitely yes. There's also the question on, okay, do we need closed loop simulation in the vision environment, in the LiDAR environment, or can we still split the two as we do with some of the stacks? But yeah, I think that's things that we'll definitely need to figure out. I think as for training and evaluation, I do think validation, we always start with validation. If you can't validate something, you can't train against it. So validation is certainly important, but training is also important. The only thing to remember is that we should not use it for both at the same time. Then we are just, fooling ourselves.
I think building simulation and autonomous driving is the great chicken and egg problem. If you have a perfect simulator, I think you've solved the problem. I mean, you can think of, if you have a perfect world model or a perfect simulator, then essentially you can look at the problem like a tree search problem. And if you look at what AlphaGo achieved, with what the game of Go has, was it 10 to the power of 160 states? It's extraordinarily complex. And when you can perfectly model and simulate or create a game environment, then that problem is solved. And I think if we had a perfect world model or perfect simulator, then self-driving could go the same way. And so building a simulator is a little bit like building the ship as you're flying it for self-driving. And I think, what I've seen in the last couple of years working on this is it's a real arms race between the simulator and the AI. As the simulator gets better, it allows the AI to improve, and then all of a sudden it hits limitations in the simulation platform. And I think that's an effect that, an adversarial effect that can be really helpful if you get it in the right cadence. But the other interesting thing we've seen is this shift from different modes of simulation over time. We have a portfolio of simulation approaches at Wave, from a procedurally generated virtual world to world modeling to NeRFs to log replay to other synthetic data forms. And it's been interesting to see how each has their pros and cons, with where they excel, where they fall down in a sim to real gap or something like that. But importantly, they complement each other. And so it's been interesting to see how their successes have played out as as we've grown the intelligence of our driving AI.
I guess maybe one thing I'll add is that it seems like the promise of simulation still has yet to be fulfilled. And so the question is, what is the way to get there? And from my experience, again, one of the crucial things is that it's really important to have like a smooth incremental flight path. And so one of the places that I would think simulation can first kind of rear a benefit is almost maybe through the lens of data augmentation. You can think about, we already do that. We take existing data and we manipulate it. And it seems like we should be able to manipulate it in sort of 3D viewpoints, and maybe even move, if we do have sort of object-centric representations, move actors around. So I guess that would be my bet on the way that it's going to materialize.
So again, I think as the person on this panel who has the least experience actually deploying things or making things work, I think my answer would probably be the most idealistic. But I think in the short term, simulation serves a really important role. And certainly, like, it's very difficult for me to imagine a development process for any robotics technology, including autonomous driving, that doesn't heavily make use of simulation for validations, testing as part of the development process. But at the same time, I myself, in terms of the research, I'm very optimistic about methods that use real data. Not so much because I think that something about simulation is bad, but because I think real data is so good, in the sense that if you have robotic systems including cars, that are actually deployed in the real world at scale. Like think about how many cars there are on the road. If all of them are collecting data, it really seems like you should be getting everything you need from that experience to build a working system. Now, it may be that you still will be actively using simulation as part of the process of developing that system, or even the process of bootstrapping it to get it past that initial activation energy so that it actually works well enough in the real world to be deployed at scale. But once it's there, it seems like you ought to be able to make use of the data that's coming in and do a lot better. One way to think about this is if you have a particular system where parts of that system improve as you get more and more experience, then eventually any part of the system that does not improve with experience becomes the bottleneck to performance, which means that if you're strongly relying on a hand-designed component for something to work, eventually that hand-designed component is the weakest link. Now, this is a much more kind of further out there kind of comment. And I definitely recognize that in the short term, I think it's really essential to have the right tools to allow us to iterate rapidly and also to iterate safely. But I think in the long run, I'm very optimistic about methods that largely make use of real world data for this reason.
I guess maybe I'll just add one color to that. It seems like we could use the term simulator in very different ways. There's kind of like the like manually designed kind of carless simulator, and then there's the sort of data driven. You could think of a world model as a simulator. So in that sense, I think I don't know, maybe you could still have it be sort of faithful to the data, or at least try to.
Great. One last question from the organizer. So that is on behalf of our grad students. So from grad student perspective, we have limited resources in terms of data, in terms of access to closed loop environment, in terms of access to vehicle platform, maybe one or two in maximum per each university. With those resources limitations, do we have any suggestions about how, as a grad student, we can contribute to the community?
It's a good question. I think maybe like one bit that comes to mind that I might mention here is I think it's very tempting looking at the kind of results, especially those that are very publicly visible, to think that kind of all there is to do in especially for robotics, autonomous driving, computer vision, is to basically implement, scale up, and operationalize the kinds of ideas that already work. And I think there's actually a lot of value in doing that kind of stuff. And I think that is something that even students could do with the limited resources available at a university. But at the same time, I think it's important to remember that there are also a lot of very difficult and unsolved more conceptual algorithmic problems. For example, a lot of the challenges we encounter in robotics, especially in autonomous driving, have to do, for example, with things like counterfactual inference, figuring out, given the data that you've seen, what will be the outcome of a completely different or new intervention, a new action. Problems that have to do with dealing with compounding errors in prediction and imitation learning. There are a lot of deep algorithmic questions that are actually unsolved, and I think that it's actually kind of an unknown the degree to which current efforts to scale up and operationalize existing ideas are simply trying to brute force challenges that are better off being solved in more nuanced ways. So I think it's important not to get distracted by the kind of results that end up showing up in the media and think that all there is left to do is scale up big transformers. There's a lot more to it than that. Of course, if you do just want to scale up big transformers, more power to you. That has value too.
So I guess the flavor of the question was how should students kind of view getting into this game when they might not have access to crazy infrastructure. I guess that's certainly true in general of like many AI questions. I don't know if it's reasonable for a student to get into training a foundation model that tries to compete with OpenAI. One thing that seems kind of healthy from the AV community, which I wouldn't have expected going into this. So there seems to be this sort of healthy sort of data release and benchmarks, and we've seen a lot of them today. And so that's clearly one way for students to continue to get engaged. And so as long as companies like you folks, if you continue, if we convince you to kind of engage
Well, someone came up to me after my telling me that they had a data set 10 times larger than mine. So presumably if they send it to me, then I'll need to figure out how to train a model that's 10 to 100 times larger. I mean, I think the real answer is I don't know, but I also kind of suspect that, you know, we have conversations like this year after year in terms of parameter size and compute and so on, and yet things somehow work out. It's always difficult, it's always annoying, and yet somehow, you know, these days, someone wouldn't bat an eye about training a model the size of AlexNet, but in 2012, people were like panicking, like, oh, how do I train big convents? It's like, it's hard, it's not trivial, but people manage, so you can actually make progress. What you can make progress on, if you don't have the resources, is competing entirely on scale. If that's the only thing you're competing on. If you have resources, then you can, but if you don't, then that's, you pick some other axis, but I don't think it's that bad.
I agree that there's so many gains to be made with algorithmic advances. I think the interesting thing we're seeing though is that even at small scales, you can predict the performance at really high scale. But the question is, how do you increase the gradient of that scaling curve? I think there's tons of opportunity there. I think, you know, ourselves and many others are very open to collaborations, whether it's around data, experimentation, or these kind of things. And I think partnering is a great way to get access to some of the resources that we have in industry. And then the final thing I'll say is actually, there's a lot to be gained from working with released large-scale models. You know, the results we showed today for the first time, bringing in large language modeling capabilities into a driving AI. You know, we didn't train an LLM for scratch. You know, they cost millions of dollars to train, and actually, a lot of these results were enabled by taking open source LLMs like Llama and you know, fine tuning or generalizing them into autonomous driving data. I think there's tons of opportunity there.
Yeah, may I clarify the question? Was the question about end-to-end or AV in general?
It's about AV in general.
Okay, so yeah, I mean, otherwise I would have said just, yeah, give up end-to-end, no chance. No, just kidding. So regarding AV, I think orthogonal to other panelists' answers, I think there are actually areas that as a company is very difficult to work on. So one example is collaboration, right? Think about, you know, when you have a lot of self-driving cars from multiple companies, how can you develop something where, you know, these cars, I mean, this will be the future, that these cars will collaborate with each other. So to make everybody safer and to actually also accelerate the time to arrival for each cars. So I think, you know, I have other ideas, but probably not easy to publicly share. But ultimately, there are indeed areas that as a company is very difficult to venture into, and as an academic, especially as a university academic, that's you know, those are unique opportunities.
Great. Now we have time for 2 questions from our audience. Who want to take questions? I'm a little bit far away. Could come here. Thank you.
Hey guys, thanks so much for the sharing. I'm just curious, what would be one thing that you really believe in the field of autonomous driving that you think most of your peers will disagree with you? Yeah, something controversial, I guess. Yeah. Thanks.
Well, I don't know about this crowd, but I would guess that actually most folks would disagree with my answer regarding the safety thing, which is that I think it's actually entirely possible that the way that we're going to address safety critical systems is by completely not worrying about the problem and just building better, more performance systems. I wouldn't like kind of go to bat on that being like 100% certain, but I think it's entirely possible that in the long run, the way that we'll get safety to work out really well, especially for edge cases, is just by having systems that are trained on enough data that, you know, essentially the long tail is sufficiently well represented. I think it's a very distinct possibility. And I see some people like very visibly disagreeing with me in the audience, which means that I answered the question correctly.
Almost, yeah. I don't know, I'm still thinking, I can't think of anything.
All right, we can move on. And any Any other questions?
Oh, come on, guys.
Okay.
So I guess if I claim that Cruise is the best autonomous driving company there is, I guess Alex would disagree with me. But I think in seriousness, right? I'd say that this incremental approach that we several larger companies have been approaching the problem. I think this is a right call to kind of scale from a very small one and learn from and iterate to through the expansions. And I think, yeah, overall, this has been working very well for us. Hopefully that's the right answer.
Alex?
Sure. I mean, the strange thing for me and for us at Wave is that for the last 6 years, almost everything we've been doing has been quite contrarian in the industry. I think the feedback we've been getting in the last year is that I think that's becoming less true as more people are looking at end-to-end learning methods for driving. And look, we've had a whole discussion on this today. I think some of the things that I've observed that could be interesting to call out, I think there was this big race in the late 2010s that if you solve perception, you solve driving. And I think as an industry, we learned the hard way that perfect perception does not equal perfect driving. I actually share that I think safety is all about performance. And I think the idea that you can put a really transparent system around it to validate safety is, at the end of the day, you build trust by setting and meeting expectations, and that comes with performance. And then, thinking that NLP in the language field would actually be able to advance autonomous driving is something that I would have laughed at 2 years ago. And now I have deep conviction that multimodality and foundation models are going to be enormous here. So I think those are some of the some interesting contrarian things I could call out. Go on, you got to throw something in the mix.
Yeah, I mean, I guess this is not really contrarian, but maybe this is me sort of thinking out loud from recent exposure of being involved in efforts that weren't successful, which is, it seems like the question that I would have is, at what point does the technology become scalable or good enough to actually turn a profit, versus, which is a different question than, at what point is it solved? There are deployments already, but clearly the inflection point that everyone's waiting for, I guess the $1 million question we're always asked is, is when is this going to happen? And of course, there's been, a history of like sort of over promising and under delivering. So something I always wrestle with myself is what is it going to take? What kind of investment and time is going to take to sort of see this all the way through? And so I guess we're all here because we're all optimistic, and I would say I'm optimistic as well. But I don't know, maybe that's not, I'm kind of curious if the general public views it that way. Because I get the sense that there's a bit of fatigue in the promise of self-driving. So in some sense, maybe we're being contrarian by being here. So that's my sneaky way of answering.
One more question. Yes.
Yeah, hi. If you had to bet which approach would get us to AGI point, like 0.1, autonomous vehicles or large language models, which approach would get us to generalized intelligence first?
So I firmly believe that to build there's a debate on the first part of this debate is how do we define AGI, but if we take what we might all, I assume we might all assume for that, I think to build a system that has that level of intelligence, I think you have to have a world model, you have to have a predictive model inside it that can really understand and predict the implications of actions, likely explicitly, but maybe you could do it implicitly. And I think it depends on the motivation of what you're building. If you're building an LLM for a chat application, that may not be necessary. And self-driving, building a world model is fundamental to solving the problem. And so there's quite a, I think one argument I'd put forward is there's a really strong incentive to build that. I suspect, though, the answer is that we will build the most intelligent system by putting as much data and experience as we can around it. And as the answer is, it's going to be both. It's going to be bringing together a multimodal model across both applications that has the really high signal to noise ratio of text that I talked about today, plus the physical interaction and dynamic nature of robotics. And I think they both bring complementary skills. You can look at experiments of people or animals that are born or grow up paralyzed and don't get to interact with the world, and how that really stunts learning, or vice versa with interacting with text. And I think both play a really important role in the development of an intelligent machine. If that's allowed, both is my answer.
I pretty strongly believe that we need to have embodied learning systems if they are to acquire the ability to interact with the real world in ways that are as flexible and sophisticated as humans and animals. And I think that there's actually something about language models that slightly puts the cart before the horse, but kind of tricks us into thinking that they're actually a lot smarter than they really are. So it kind of comes back to like very basic information theory. Like if you communicate information to somebody, that's what language is for, right? Language is communicate information. It's only worthwhile to communicate stuff that the other person doesn't already know, right? Like if the most efficient communication channel, you're aware of somebody's prior, and you just communicate those bits that they can't already get from their prior. And that means that we're generally not going to be communicating things that everybody is good at. Like you rarely go and tell somebody, hey, here's how I move my muscles to get out of bed in the morning. Like, no, that's not very interesting, because most everyone can do that, right? And those that can't, it's not because they don't know how, it's because the physical limitations, right? So language models kind of trick us a little bit because they're entirely all about language, and language is the modality we use to communicate things that we don't already know, which means that they're going to sound like they know things that we don't already know. Whereas if you have a robot that performs some physical tasks that's actually very difficult, but that each of us can do easily, it doesn't look so smart. So I think for that reason, actually, there's perhaps a lot more intelligence wrapped up in embodied systems, biological embodied systems, that is, even ones that don't have language, like animals, than we might intuitively kind of appreciate. So I think there's actually a lot more depth to intelligence, and a lot of that will come out of embodied systems.
All right, that wrap up today's panel discussion. Thank you so much for the insightful discussions, and thank you for the meeting talks. Also, thank you for the audience who participate. Really appreciate that. All right, let's wrap up today's workshop. Thank you.
Thank you. Thank you. Very informative. Yeah. Yes, I would consider like read something today. Right.